For more videos like this for Discrete 1, you can check out Sarai Studies, link is in the description box below. Now this video comes with a corresponding post, which is this last one right here. If we click on it, you'll see if we scroll down, we have the grammar section, finite state machine section, and the Turing Machine section. If you click on the grammar section, you'll have a direct link to the grammar section part of this video, and for each example you have a direct link to that as well. And then below those examples you have similar practice problems with video solutions so that you can try them on your own. Same thing with the finite state machines. If you scroll down, you'll have an example for a finite state machine, and then you have practice questions that have video solutions. Now we're ready to start. The last topic covered in Discrete 1 was a little intro to theory of computation. And the big picture, or the big question we're trying to answer, is can a problem be solved using a computer? Take this scenario for example. Let's say you have a problem and you want to solve it. So you go straight to your computer and you're going to start writing some code trying to find an algorithm that solves this problem. But it's taking you days and days and days, and it's taking a really long time. So what if instead of going straight to trying to solve the problem, trying to find an algorithm that solves this problem, what if we save time by finding out if this problem could be solved in the first place? And if the answer was no, we know that the problem cannot be solved. So we know not to spend any time writing code trying to find an algorithm that solves this problem because we know that that algorithm doesn't exist. And if the answer was yes, then we know that the problem can be solved. So we know it's worth it to spend time writing code trying to find an algorithm that solves this problem because we know that algorithm exists. So you can imagine how useful it is if we could actually answer this question for any problem. Now I want to note that the problems we'll be focusing on are called decidable problems, meaning they're problems we can answer with yes or no. For example, is the number even? Is spring a season? Is 7 an even digit? Is green a primary color? Are the Lakers an NBA team? Is Princeton an Ivy League school? Is Google in the S&P 500? These are all yes or no questions. These are all decidable questions, or yes or no problems. So keep that in mind, that these are the types of problems that we're talking about. Now we're going to see if we could actually answer this question at the end of this video series, because to actually answer this question we need some basic skills. And the way we're going to develop those basic skills is by focusing on a specific problem. For example, the problem could be, is n even? Is any number I give you even? It's a yes or no question, and let's see how we can solve it. And by solving it, we're going to discover some tools or some skills that we will need to ultimately answer this question here at the end. We can look at this from two different point of views, from the practical point of view and the theoretical point of view. From the practical point of view, you can just write a program, plug n into that algorithm, that program, and get an answer. From a theoretical point of view, you can ask yourself if n is in the set of all even numbers. In other words, we want to think of problems in terms of sets. That is the key idea here. So if my question is 2 even? So 2 is my n. Instead of plugging it into an algorithm and getting an output of yes or no, from a theoretical perspective, we can think of the set of all even numbers, so that would be s is equal to 2, 4, 6, 8, 10, and so on, and ask ourselves, is 2 an element of the set s? And we know it is, so the answer is yes. And we can do this for all of the problems we've just mentioned. For example, another question, is green a primary color? Well, you consider the set of all primary colors, so that would be red, green, and blue. And the way to answer this question is by asking, well, is green an element of this set? And green is indeed an element of this set S. It is an element of the set of all primary colors, so the answer to that is yes. Another question, is 7 an even digit? We'll consider the set of all even digits. That would be 0, 2, 4, 6, and 8. And we can answer this question by asking ourselves, well, is 7 an element of this set, of the set of all even digits? And the answer to that is no, I don't see 7 in this set. So 7 is not an even digit. In fact, we already know that 7 is odd. So you can see the pattern on how we're converting a yes or no question to a set membership problem. The problem being, well, is an element in the set? That's a set membership problem. Which is why we focus on problems that can be yes or no questions, so that these yes or no questions really become questions about sets, aka languages, which we will soon cover. But for now, we're going to focus on this problem here. Then two questions arise. The first one is, how do we generate all of the elements in the set? And the second one is, how do we recognize that an element is indeed inside of a set? The answer to this one is using grammar, and the answer to this one is finite state machines. So we're going to start by covering what grammar is, and then we'll talk about finite state machines, and then at the end, we're going to put everything together, and I'm going to show you how to design a grammar that will generate the set of all even numbers, and I'll show you how to design a finite state machine that will recognize recognize if any number n is in that set of even numbers. But again, first, let's introduce grammar. If you think about it from third grade basics, it is used to construct languages. And languages are made up of words or sentences, right? The English language is made up of the words I'm saying now, or the sentences I'm saying now. So really we can think of a language as a set of words or sentences. So a language L can be the set of word 1, word 2, or sentence 1, sentence 2. But in Discrete, we usually call these words or these sentences strings. So our language can be equal to the set of string 1 and string 2. Maybe an example would be string 1 is hello, string 2 is my name is Sarai. So these strings are generated or structured using grammar. So think back to third grade, you learned grammar so you could structure sentences. So same thing, you learn grammar here so you can structure these strings that make up a language. But in Discrete, we define grammar, G, to consist of 4 things. The first one is V, which is the vocabulary or the alphabet. So this is a set of all symbols or all variables that you will be working with. Then T is what we call the set of terminal symbols. You will also see this notation. Garcia sometimes uses the sigma notation for T. But the idea is that whatever symbols or variables our string contains, so this string contains the symbol H, E, L, and O, will only be made up of the symbols in this set. Think terminal for N, so at the end of the day, your strings will only have symbols, variables that are in this set. Then S is our starting symbol, and P is our set of productions, in other words, rules to follow. So symbols, variables, same thing. So H is a symbol, E is a symbol, variable. So keep that in mind. Now, before we move on to our first example, I want to make clear the connection between grammar and our intro. We introduced a new concept called languages, but if we just look, languages are just sets that contain elements. Just like this is a set that contain elements. Specifically, these elements, we call them strings, and we use grammar to generate or construct these strings. So the goal eventually is to, instead of thinking of these as just numbers, let's think of them as strings and be able to design a grammar that will generate all of the strings that are even numbers. In other words, it will generate the language of all even numbers. So that is our goal eventually. But first, let's go ahead and build up our skills in grammar with our first example. Given G, so a grammar, generate 3 strings in the language of the grammar. Okay, how do we start? Well, our grammar tells us that the starting symbol is S, so we start with S. Now, where do we go from there? Well, our productions tell us where to go. From S, we can either go to 1S, or from S, we can go to 0, so we have 2 options. It says to generate 3 strings, so it's up to us where we want to go. So let's say I pick this one. I'm going to name these productions. I like to call them rules. So this is rule number 1, rule number 2, or production 1, production 2. So here I'm going to choose production 1, which means that S becomes 1S. Now, is this a string in the language of the grammar? No, because I still have a symbol, I have a variable that's not terminal. I don't see S in the set of my terminal symbols. Remember that all of the strings in our language should only be made up of terminal symbols, terminal variables. This cannot be a string in our language because it contains a non-terminal variable. It contains S, that's not in our terminal set. You have to keep going. Where do we go from here? Well, you go to your productions. Your productions tell you where you can go. So again, I have the option to go from S to 1S, or to go from S to 0. Let me try this rule now. So I'm going to go use rule number 2. S becomes 0. And what you do as you go through is you collect your terminal symbols. So in this line, our terminal symbols were 1, 1. And in this line, our terminal symbols are 0. Now, am I done? Yes, because I ended up with a terminal symbol. I can't be like, where do I go from 0? No, 0 is terminal. It's the end. You can't go anywhere from 0 or from 1 because they are terminal. So you're done. So this here is a string in the language of this grammar. So it's 1, 1, 0. That's one string. Let's try to generate another string. So we start always at the starting symbol. This time, let me start with rule number 2. So using rule number 2, S just becomes 0. Am I done? Yes, because 0 is terminal. I can't go anywhere from 0. Besides, if you tried to, there is no production that says, oh, from 0 goes somewhere else. The left-hand side of a production should always be non-terminal symbols. It will never be terminal symbol and it will tell you, oh, from 0 go to 1 or something. No. So again, you collect your terminal symbols. 0 is a terminal symbol, so at the end of the day, this is another string. 0 is part of the language of the grammar. Let's try to generate one more, so I start with S. At this point, you realize if I try to do this again, well, it's going to be the same thing. I can't go anywhere from there, so I'll try this one again. Production number 1. It says that S becomes 1,1S. Again, I'm not done because I still see a symbol that's not terminal, but I will collect my terminal symbols. 1 is a terminal symbol, so far, the string I've generated has 1, 1. Right now, I'm doing the same thing as here, and from here, I chose production 2. Let's say I choose production 1 again, just to be different. That means that S becomes 1,1S, so now we have 1,1S. I collect my terminal symbols, so far, I have another 2 1s. And let's say for the fun of it, I choose production 2 now, so S becomes 0. 0 is a terminal symbol. It's in my terminal set, so I collect it. So far, my string is 1, 1, 1, 1, 0. And I know I'm done because I don't have any more non-terminal symbols. But notice, overall, V is the alphabet, is your vocabulary. It contains all of the symbols you're going to deal with. It includes all of the symbols from T, from the set of terminal symbols. So T is a proper subset of V. I wouldn't say it's a subset of V, because this suggests that they could both be equal, but T will never be the same as V, because V contains symbols that are non-terminal, that could never be terminal, so they wouldn't ever be in this set. So T is properly a subset, contains only some of the elements of V. So we use the proper subset symbol instead of the general subset symbol that says they could be equal to each other, the same size. I like to think of this as less than. So without the equal means, okay, this set is always going to be smaller than this set. It will never be the same as this set. But here, I like to think of this as less than or equal to. It could be smaller and equal to, but that's false. Because again, these sets can never be the same as each other, so you're just left with using this symbol here. Your terminal symbols will only have symbols that your strings will contain at the end of the day. So notice our strings only contain zeros and ones, zeros and ones. It doesn't contain S. So far we can say that the language of this grammar is equal to this string, 0. You can write it without the strings. 1, 1, 0, and 1, 1, 1, 1, 0. Right here, and then so many more. We just haven't done them. Now here's a very important part of vocabulary. For your productions, when you have one single non-terminal variable or symbol on the left-hand side of your productions, which is what you will usually see in this class, that means that the language is context-free. These are the languages we will be working with in this class with Garcia. There are some productions have like SA or S0 and whatever. These are not context-free languages. You can only have one variable on the left-hand side of the production. That's what makes it context-free. Another type of question they can ask you is this string in the language of the grammar? To answer this question, you start with your starting symbol S, and then you try to see using your productions if you can get to this string, if you can collect all of these symbols. Well, let's see. The first symbol I would want is a 1. So from S, I can either go to 1, 1S or 0. Which one of these is going to give me a 1? Well, this one. So I'm going to use rule number 1. So rule number 1 means that S is going to become 1, 1S. And then as you go, you want to collect your terminal symbols. How do I know they're terminal? Because 1 is in the set of terminal symbols, so you collect the 1s. So far I have 2 1s. I know I have to keep going because this is non-terminal. It's not in this set, so I'm not done. So where can I go from here? Your productions tell you you can either go to 1, 1S or 0. But where should I go if my goal is to generate this string? Well, here there's another 1, so it wouldn't be smart to pick this one because if I pick this one, then I would be done. That's one problem, and second, it wouldn't be a 1, it's a 0. So I would pick this one because this one gives me a 1. In fact, it gives me 2 1s, which is perfect because I have another 2 1s that I want. So using production number 1, S becomes 1, 1S. And again, you want to collect your terminal symbols, so you have 2 more 1s. And you can notice the pattern. I want another 2 1s, I want another 2 1s. So using production number 1 again is going to give me another 2 1s. So these 2 1s are these ones. Then using production number 1 again gives me another 2 1s. So these 2 1s are these ones. And finally, I'm still not done because I see a non-terminal symbol, a symbol that's not in the terminal set. So where can I go from here? Well, I can go to 1, 1S or 0. But where should I go if my goal is to generate the string? Well, I should use a production that's going to give me a 0. Which one of these is going to give me a 0? Well, if I choose this one, S becomes 1, 1S is not going to give me 0. It's going to give me 2 1s and also not going to be done. And I know I have to be done after the 0. And if I choose this one, S becomes 0. So using rule number 2, S becomes a 0. 0 is a terminal symbol, right? It's part of the terminal set here, so you collect it. So I have the 0. In other words, I managed to generate the string 1, 1, 1 1 1 1 1 1 0 using this grammar. So the language of this grammar contains this string as well. So we would just add that over here and so many more. So the answer is yes, this string is in the language of G. Given this grammar, what is the language of the grammar? They're basically asking you what is the set of strings that you get by using this grammar. The set of strings makes up the language of that grammar. If the set is short, you can actually just list out all the strings that make up the language that you can generate using this grammar. If the set is really long, we can describe the set using set builder notation. And the best way to start is to get an idea of what types of strings this grammar can generate. So where do we start to do that? The starting symbol S. So we start with S, then from S, we know we have to keep going because S is non-terminal. It's not in this set. So we can't end with it because remember, terminal means end. We can only end when we only have terminal symbols left. S is not one of them. So where do we go from there? Well, your productions tell you, and I like to label my productions. So this production says that S can go to A. So I'm gonna label this production number 1, and this is production number 2 or rule number 2. So let's say I use rule number 1. Well, that means that S becomes A, and already I'm done. How do I know I'm done? Because I'm only left with a terminal symbol, a terminal variable, or a terminal character, whatever you want to call it. Terminal means end. So I'm good to end. I can end it here because I can't go from a terminal symbol to someplace else. Even if you try to, if you go to your productions won't have a terminal symbol goes to someplace else. No, because the left-hand side of the productions are always non-terminal symbols. They're never going to be symbols from the terminal set. So the string we generated here is just A. This is our only terminal symbol. Well, let's try using production number 2 this time. So we start with S, and if we use production number 2, it says that S becomes AB. Notice that both A and B are terminal symbols. We don't have any other non-terminal symbols like S where we can go someplace else, so we are done. We can end here because we're left with only ending symbols. So the string I managed to generate this time is AB. And you'll see that if we start with S, these are really the only 2 options that we have, because so far we start the same way. Here we choose production 1 and we come to a dead end. Here we choose production 2 and we come to a dead end. And since these are the only productions we have, both productions lead to different dead ends. These are the only dead ends that we'll have, the only strings that we'll have. So the language generated by this grammar is equal to just this string A and this string AB. You can write it without the strings, that's fine. And that's the language of the grammar. Another skill you need to know is, given a language, how can you construct a grammar that will generate all the strings in that language? So here we're told to give a phrase structure grammar, so that's just the long way of saying grammar, that generates the set, and then they give you this set. This here is a language. What this is saying is that the language made up of this grammar is equal to the set containing the strings made up of 1 0 followed by 1 n number of times. And that n could be 0 times. So that means you would just have 0 followed by 1 0 times. So that would just be the string containing 0 because you used 1 0 times. But n could also be 1. So that would mean you would have 0 followed by 1 time. So that would be another string. N could also be 2. That means you would have 1 0 followed by 1 2 times. But n could also be 3. So that means you would have 1 0 followed by 1 3 times. And you can see how n can be any number. So you can have 0 followed by 1 as many times as you want, and so on. So notice that the n is applied only to the 1. You always have to have that 0. So what they're asking you is, can you define a grammar that will construct all of the strings in the set? So you have to remember that a grammar is defined by V, which is the alphabet or the vocabulary. It's a set of all symbols that you'll ever use in the process. It is also defined by sigma, also known as T. This is the set of all terminal symbols, T for terminal. Remember that terminal means end. So the set of terminal symbols contains all of the symbols that your strings are made up of at the end of the day. So if you look at all of your strings, they only contain the symbols 0 and 1. So in this case, our set of terminal symbols will only be 0 and 1. But we'll get to that. Next, grammar is defined with a starting symbol and then a set of productions. The easiest thing you can do is find the set of terminal symbols. Remember that the set of terminal symbols includes all of the symbols that your strings are made up of at the end of the day. So if you look at these strings, the only symbols they're made up of are 0s and 1s. So your set is going to contain the symbols 0 and 1. Remember that your vocabulary is a set of all symbols you're ever going to use. So that includes all of the symbols that your strings are going to be made up of. So it includes 0 and 1 as well. And the starting symbol, we can just call it S, as we always do. So we could also add that to our vocabulary, the set of all symbols we're ever going to use in this process. Now, P's are a set of productions or a set of rules. So the question is, well, what are the productions? Well, a great place to start is by finding out what rules you would need to generate these strings. And where do you start? You start at the starting symbol, which is S. And then from here, you ask yourself, okay, how can I generate this first string? Just focus on one. What rule would I need? What production would be convenient to have to generate this string? Well, if I had a production that said I can go from S to 0, then look, I managed to generate this string. So that's a production I would want to have. But what if I wanted to generate this string? Well, I start at my starting symbol. From S, I already have the production that I can go to 0. So I already have this 0, but I also want a 1. But the problem is, there's no non-terminal symbol that forces me to keep going because I can't end with it because it's non-terminal. So I'm just left with this 0. That's all I could ever do with this production, just generate 0. So what I need here is a non-terminal symbol that forces me to keep going because I can't end with it. It's non-terminal, non-ending. Now you might propose to use S because S is non-terminal, right? It's not part of the terminal set. But if we use S, keeping in mind that we have this rule, that means that we can go from S to 0. And that would be a problem because now we have 2 zeros and we could only ever have 1 0. So we cannot use S again. We need a new non-terminal symbol. So let's say we use A. In order to do this, that would mean we would have a production that says we can go from S to 0A. And because A is a new symbol, we have to add it to be part of our vocabulary, the set of all symbols we'll ever use in the process. We don't add it to the terminal set of symbols because we don't ever want to end with A. It's not terminal. In other words, our strings are not going to contain A in the same way they don't contain S. They only contain 0 and 1. Well, from here, what would be a convenient production to have? Well, remember that my goal is to get this 1 here. So if I already have a 0, I want to be able to go from A to 1. So a nice production would be go from A to 1. So now I've collected 0, 1, so that means I managed to generate this string 0, 1. But what if I wanted to generate this string 0 with 2 1s? Well, I could start from my starting symbol. If I use this production, I'll just be stuck here because there's no non-terminal symbol that forces me to keep going. This is the only other production I can use. So let's say I go from S to 0A. Okay, I already have my 0. That's done, but I still need 2 1s. Well, then from A, I can only ever get 1 1. And so I'm only stuck being able to generate 0 1 or just 0. So another production that would be convenient to have would be if I could have a 1, so A could go to 1, but be forced to keep going. So have another non-terminal symbol that forces me to keep going, and let's say I use A again. So then the production that I would love to have would be A can go to 1A. Because that would allow me to either end it there and use this one and say, okay, A can go to 1 and just end it there. Or use this one over and over again. 1A, then 1A again. A can go to 1A again. And you can see how I can do 1 as many times as I want, which satisfies this little condition here. And then I could just end it with the last one. So to generate this string, I start with my starting symbol. I want to have a 0. There's 2 ways I can have a 0 from S, but if I use this one, then that's all I could ever do, just a 0, so I don't want to use that one. This is the only one I could use, so 0A. So I have collected this 0 so far, but now I want a 1. So from A, I have 2 choices. I can go to just 1 or 1A. If I just go with 1, I'll only ever have this 1, and I can never get this one. So I'll choose this one. I'll say from A, I can go to 1A. So far, I have another 1. And finally, I want this last one. So from A, I have 2 choices. I could either do 1 or 1A. If I choose this one, A goes to 1, I've collected 0, 1, 1 as my string, and I managed to generate this string. If I had chosen this one, 1A, I would be forced to keep going because I can't end with a non-terminal symbol. And so we managed to design a grammar that generates all of the strings in this set. And as a side note, instead of doing S can go to this and then S can go to that, you could say S can go to 0 or 0A. And then instead of writing A can go to 1 or A can go to 1A, you can just say A can go to 1 or 1A to keep it short. So the symbol, this little bar here, means or. In the next part of this video series, we're going to talk about BNF, which is Backus-Naur Form, and it's just a more concise way to define a grammar, but it's used specifically to design a grammar for the syntax of programming languages, like Java. So here's an example. Sometimes when you're dealing with a grammar, you'll be given the productions in what we call Backus-Naur Form, or BNF. This would be the same thing as a non-terminal symbol like S. This is the same as the arrow, and it's saying that this can either become this, or this plus this, or this times this, or just a variable. And when they're telling you to find a derivation tree for this, they're just saying is string in the language of the grammar, of this grammar using these productions. So we know that a grammar consists of an alphabet V, terminal set of symbols, starting symbol, and a set of productions which are given. So we already know that these are productions. Our alphabet or our vocabulary is going to be the set of basically all of the symbols that we see. So we see this as a symbol, so that's expression. We see this as a symbol, so that's a variable. And then we also see X and Y, so X and Y. Our set of terminal symbols is going to be everything that's not on this side. So it can't be expression, it can't be variable, so it's only X and Y. Because remember that the left-hand side of the arrows have to be single non-terminal symbols if we're working with context-free languages, which is what Garcia focuses on, only context-free languages. So then if these are non-terminal, then they won't be included in the terminal set because they're non-terminal. Then my starting symbol, if they don't specify, then it's going to be the first non-terminal that you see on the left-hand side, on the first production that you see, so that's just going to be expression. And then again, we already know that these are productions. So we start with our starting symbol, which is this, so we start with an expression. Then from here, I like to number my productions or my rules. So this one says expression can go to expression, I'm going to call this number 1, or it can go to expression plus expression, so I'm going to call this rule number 2, production number 2, or it can go to this, so that's 3, or it can go to just variable, so that's 4, and I'll call this one variable can go to X or Y, 5, 6. So start like an onion, you peel the outside first. So the big picture is you want two things added together. So you want to go from an expression to two things being added together. So that's production number 2, rule number 2. So I'm going to use rule number 2, which says that expression right over here, this is the same thing as an arrow, can go to either expression or expression plus expression. So I'll have expression plus expression. Then I know I have to keep going because these symbols right here are not in the terminal set. They're not terminal. They're not ending worthy, so I can't end with them. I have to keep going. So these two have to become something else. Well, look back at what you have. This expression represents the left side. This symbol represents this side. So let's start with the easiest, most simplest thing. This has to eventually become X. We know to get an X, we need to have a variable. But right now we're here, we're at expression. So from here, can I get a variable? Yes, I can just use production or rule number 4, which says this can go to a variable. So then that would be production number 4 that says this can just go to being a variable. Now I know I have to keep going because variable is not in my terminal set, so I can't end with it. I have to keep going, and I know that I want X, so I can use production number 5 that says I can go from this symbol variable to X. Again, this double dot equal sign is just the same thing as an arrow. So using production number 5, variable becomes X. Now I know I'm done here because I don't see any non-terminal symbols. I'm only left with a terminal symbol because it's in the terminal set, so I can end with it. In fact, if I thought that I wouldn't be able to end with it, if you try to go somewhere from here using your productions will not tell you that because your productions will never have a terminal symbol like X or Y and say, okay, from X you can go here and from Y you can go here. No, your productions tell you where to go to if you have non-terminal symbols. So you wouldn't see from X you can go to somewhere. So you know you're done here. So we managed to get this side and we can drop this plus sign down each step. Now I need to get this to somehow give me this. Well, at the end of the day, I want two things being multiplied together, but I have expression right now. So from expression, how can I get two things being multiplied together? Well, I could just use rule or production number 3 that allows me to multiply two things together. So that's production number 3. That gives me expression times expression. But again, I know I have to continue because these symbols are non-terminal, so I can't end with them. And I know at the end of the day, I want this to become an X and I want this to become a Y. But in order to do that, in order to get an X and a Y, I have to have this symbol first. So then the question is, how can I go from this symbol, which is this one right here, to variable? Well, that's production number 4. So I can use production number 4 on both of them. That allows me to have these go from expression to variable, go from expression to variable, and then the multiplication sign drops down. Great, I know that I want this variable to be x and I want this variable to be y, and I know I have to keep going because variable itself, that symbol, is not in a set of terminal symbols, so I can't end with it. But to get this to be an x, I will use production number 5 that allows me to go from variable to x. So production number 5 allows me to go from variable to x, and then to get this to be a y, I'm going to use production number 6 that allows me to go from variable to y. So production number 6 allows me to go to y, and you can just drop down the multiplication symbol, drop down the plus sign, drop down the x, and here we have what we wanted in the first place. We managed to generate this string using this grammar by using a derivation tree. And that is BNF form. It's just a different way of writing productions. So we just finished learning about grammar, and now we're going to learn about finite state machines. To remind you of why we're doing this, we're eventually trying to see if we could answer this question for any type of problem. And we said we were going to answer this question at the end, because to answer this question, we need some skills, and that includes grammar and finite state machines. And to teach you both of these skills, I decided to take a specific problem, like is any number I give you even, to show you how you can use grammar and finite state machines to answer this question. So again, we learned about grammar, now we're moving on to finite state machines. But for finite state machines, we can break them up into two categories: finite state machines without output and finite state machines with output. The finite state machines without output are DFAs and NFAs, and the ones with output are Mealy and Moore machines. So really, when I said that finite state machines are what we use to recognize if an element is inside of a set, I specifically mean finite state machines without output. And the reason why is because these machines are what we call recognizers, and these machines are what we call transducers. So these here are designed to take in an input and recognize if that input, let's say it's an element, is inside of a set or not. So it either accepts or rejects that element. So these are literally designed to answer this question, but these here are what we call transducers. They take in an input and give you an output. For example, you'll learn this in Compark, but when you're trying to find the ones complement of a binary number, so let's say this is the binary number, the ones complement is just literally you flipping the zeros and ones. So 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, that's the ones complement of this number. So the input in this case would be 0, 1, 0, and then the output would be 1, 0, 1. It's not a yes or a no, it's not an accept or rejection, it's more like convert or translate this input into an output. Which is why we'll focus on these first, because these are actually designed to answer this question, and we'll talk about these later. And so the idea is we'll have a machine, again, a finite state machine without output, so either a DFA or an NFA. And since these machines are recognizers, they're designed to take in an input, let's call it W, so let an element be W, and they're either supposed to accept or reject this input. So these machines have a language that they're supposed to recognize, and we call it the language of the machine, and it consists of all of the strings that machine is supposed to recognize, that it's supposed to accept. For example, if the strings were A, B, and D, if I pass in A into the machine, then this machine is supposed to accept A because A is an element of this set of the language that the machine is supposed to recognize. But if I pass in cat as a string, this machine is supposed to reject this input because cat is not an element of this set of the language of the machine. You didn't see cat here. You saw A, B, and D. You didn't see cat as an element. Now I'm going to formally introduce finite state machines, and we'll focus on DFAs first, but my suggestion to you is casually watch this part of the video, just skim through it, but really go and try the examples that are coming after this, and then come back and watch this again to reinforce what you've practiced and any doubts that you may have. Because obviously this is new to you, so you might not understand something I'm talking about until we actually practice it. So that's my suggestion. Now DFAs stand for deterministic finite state automata. Automata means machines. So we have deterministic finite state machines. And by the way, NFAs stand for non-deterministic finite state automata or non-deterministic finite state machines. So we have deterministic versus non-deterministic. And we'll get into depth about these two vocab words later. But really a DFA is called deterministic because we're always able to determine exactly where we're going. But with an NFA, it's non-deterministic because we're not always able to determine exactly where we're going. Because we might be able to go to two places from one place versus a DFA where from one place we can only go to exactly one place. So for a DFA, we always know exactly what the possibilities are. It's just one possibility, so it's deterministic. You're able to determine that, but for an NFA, we could either go here or here, so it's non-deterministic. And the special characteristic about a DFA is that every state, we'll talk about what states are, needs exactly one, no more, no less, transition for every symbol in the alphabet, and we'll talk about what the alphabet is. So a finite state machine, M, no matter if it's a DFA or NFA, is going to consist of Q, which is a set of all states, and states are just circles, and you can label them, call them a state as 0, so S for state, or Q0, or even A, B, whatever. It consists of sigma, which is a set of all input symbols, also known as the input alphabet, or just the alphabet. So when you have states, let's call this state as 0, what you're doing in a machine is reading in inputs at a current state. So let's say at this state you're reading in a 1, and let's say if you read in a 1, you come back to this state. And then let's say if you read in a 0, you go to another state, let's call it S1. And so the set of all input symbols are all of the symbols that you've been reading in that are inputs into your machine. So that would be 0 and 1. And then you have delta, that's the symbol here, and that's the transition function. And this tells you which states to transition to given the current state that you're in and the input that you're reading. So you saw how we had state as 0, and then if I read in a 0, I went to state S1. Well, how do I know that when I read in a 0, I go to state S1? The transition function tells you that. So the way that you read this is, given a state from the set of all states and given an input from the set of all input symbols, the transition function will tell you which state to transition to next, and that's going to be one of the states from the set of all states. So notice how these are the same, so that next state that you can transition to could be the same state or it could be a different state. For example, let's say that you have states S0, 1, and S2. So your set of all states, Q, consists of S0, S1, and S2. And let's say that your alphabet is just the set of 0 and 1. And let's say that it looks like this. This is what we call a state diagram, and I'll talk about that later. The way you read this is, okay, I'm at state S0. So that's my current state. It's one of the states, it's one of the elements from the set of all states. So that's this element right here. And I'm reading in a 1. So an element from this set, one of the inputs from the set of all input symbols, so that's this element right here, where do I go to? Well, it's going to be one of the states from this set. In this case, if I look at the diagram, it says I go to state S1, so that's S1. And so you can see how it's one of the elements in the set of all states, it's this one, but it could have been this one as well. If I drew it as S0, if I read in a 1, I stay at the same state, so then it would be S0 would be the state. If I read in a 1, it will transition me. The next state I'm going to go to is the same state as 0. So that would be this picture right here. So that's the idea. Now, it's important to understand it this way because this is a transition function for a DFA, but the transition function for an NFA is you just adding a P. So now it's the power set of Q instead of just the set Q. So in the same way, you read this as given an element from this set and given an element from this set. So given a state from the set of all states and given an input from the set of all input symbols, the transition function tells you that you will transition to one of the elements from this set, one of the elements in the power set of Q. But I don't want to say it's going to be one of the states in the power set of Q. Because the power set of Q, remember, it's not just single elements where you could say, oh yeah, it's just state S0. A power set of any set is a set of sets. So it literally contains sets. So this goes to show that an NFA is more flexible because now when you're at a state, you can transition given a certain input, let's say 1, to a set of states like S1 and S2 now, like S1, S2. So you can transition out to a set of states instead of just one single state, which is what you had in Q. You could only transition to this one or this one or this one, exactly one, no more, no less. But with the power set, you can transition to multiple ones. Let's do an example. Let's say that Q is S0, S1, and S2. And so then the power set of Q, remember that a power set is just all of the ways that you can use these elements to put them together in a group. And that includes using none of them. So if you use none of them, well, that would be the empty set because you use none of them. That would include using just this one in a group. So that would be S0. Or using just this one in one group, so that would be the set containing S1, or using just this one as a group, so that would be containing S2 only, or using these two together in a group, so that would be S0, S1 in one group, or using S1, S2 in one group, or using S0 and S2 in one group, or using all of them and putting them together in one group, so that would just be the original set Q, and this is the power set of Q. So here's the beauty about this. For a DFA, you can only transition to one of the states from this set, one of the elements from this set. So that includes S0, S1, S2. But for an NFA, you can transition to any of the elements from this set, from the power set of Q, and that includes all of these. So you can transition to no states if you read in an input. So let's say you have state as 0 and you read in a 1, you just don't have to have a transition for 1. You don't have to have an arrow for 1. No need, that's fine for an NFA. You can transition to exactly one state, just like a DFA. So notice how where a DFA can transition to is inside an NFA, but everything else that an NFA can transition to is not inside what a DFA can transition to. But the point is, if you read in, let's say, a 1, you can transition to state S1, or you can transition to state S1 and S2. So we're transitioning to a set of states, so more than one state. If you read in a 1, that's allowed by an NFA, but not allowed by a DFA, because for a DFA, every state needs exactly one transition for every symbol in the alphabet. So I can't have more than one transition here. I have 2 transitions for 1. 1 is part of my set of input symbols. Let's say it's 0 and 1. I have 2 transitions for 1, I can only have exactly 1. So it can't be a DFA, but this is acceptable with an NFA. So you can see how an NFA is more flexible than a DFA in terms of construction. So we can conclude that for an NFA, we can have exactly 0, 1, or more transitions for every symbol in the alphabet, the set of input symbols, which is what we saw in the power set. We saw the empty set, so the set of next states we can go to is none. We saw that we could go to exactly one state, and we saw that we could go to more states, so a set of states. So to be specific, every state needs exactly one transition for every symbol in the alphabet. The definition of a DFA is inside the definition of an NFA, meaning that every DFA is already an NFA, but not every NFA is a DFA, because you could have NFAs with states that go to no places or more than one place when you read in an input symbol, and that's not allowed for a DFA. And that's a little rant on that, but we'll actually have a whole section dedicated to DFAs versus NFAs so you can get more comfortable with it, but I wanted to get it all out here so you know what you need to know. But moving on, we have a Q0, which is a starting state. So again, if we have a diagram that looks like this, S0, S1, if we read into 1, we go to S1. It doesn't really matter. The point is we need to start somewhere. And so they will always specify where you need to start by putting an arrow like this or an actual arrow next to the state that they want you to start in. So in this case, the state we started in is S0. And then we have big F, which is a set of final, or also known as accepting states. So if you have something that looks like this, you have states that are double circled. These are your accepting states. And what they mean is, if you end in an accepting state when reading in an input to the machine, then that means that your machine accepts that input because it ended in an accepting state. And you can have more than one accepting state. That's why it's called a set of accepting states, while you just have one starting state. Now, a note on notation, this is the notation Garcia uses in class, but your textbook, the Discrete Mathematics and its Applications textbook, instead of Q, they use S, so S for states. They use I for the set of all input symbols, so I for input. They use little f for the transition function, so little f for function. They use S0 for the starting state, so again, they use S for state, and then they still use big F. Additionally, sometimes Garcia will use T from the grammar world instead of sigma to represent the set of all input symbols. Because after all, if T is a set of all symbols that our strings are made up of, and these are the strings that we're passing into our machines, and our machines will only input all of the symbols in these strings, of course assuming that the string that the machine is reading is a string that the machine is supposed to accept, because it's designed only to read symbols that it's supposed to accept. Then the set of all input symbols is the same as the set of all symbols that make up the string. So he uses these interchangeably. Now this is what we call the formal description of a finite state machine, and it's exactly the same for a DFA and an NFA. The only difference is the transition function. And this is one out of the 3 ways we can represent finite state machines. The other ways are state diagrams or a transition table, also known as a state table. For our first example, we're told to provide a formal description. In other words, we're supposed to define each and every single one of these. For the deterministic finite state machine, so the DFA, represented by the state diagram below. So if you haven't seen one before, this is a state diagram. Why is it called that? Because every circle is a state, and from one state we can go to another state depending on whatever the input is. The state diagrams for finite machines without output always tell you where to start and which are your accepting states, your final states. This is my starting state because I see a little arrow. Sometimes you'll see this or this. And this is my final state, my accepting state, because it's double circled. The way you read this is you start at state Q0, and if I read in a 0, that means I go to state Q1. But if I'm at Q0 and I read in a 1, that means I go to state Q3. So that's a bit on how to read a state diagram, but let's focus on what they want us to do. They want us to provide a formal description. That means we have to define all of these. So recall that a machine consists of Q, the alphabet, the transition function, the starting state, and a set of final states. Q is a set of all states. What are the states in the state diagram? All the circles. So we have Q0 right here, Q1 here, Q2, and Q3. Those are all of our states. Our alphabet sigma consists of all of the symbols, or all of the variables, or all of the characters, these all mean the same thing, that are on top or at the bottom of the transition lines. All unique symbols, so I only see 0 and 1. I'm not gonna repeat 0 and 1 again. So it's 0 or 1. Because remember that the alphabet is a set of all input symbols. These are our inputs. If we're at state Q0 and our input is 0, we read in a 0, we go to Q1. Next we have the transition function. If you have a hard time writing it, it's like an 8, but you just don't do this part, so you stop here. So since we don't really know what the function was, we can use a transition table to describe the transition function. So your table starts with one column, and in this column you're always putting your states. So you have state Q0, Q1, Q2, Q3. Then after that, you're going to have one column for each of your input symbols, for each of the symbols in your alphabet. So one column for 0 and one column for 1. And now you just read your state diagram. If you're at state Q0 right here and you read in a 0, so if I read in a 0, where do I go? What's my next state? State Q1, so you write Q1 here. Now if you're at state Q0, but you read in a 1 instead, well that means you go to state Q3, so you write Q3 here. If you're at state Q1 and you read in a 0, well if you read in a 0, you transition to state Q2, so you write that here. But if you're at state Q1 and you read in a 1 instead, you transition to state Q3. Now if you're at state Q2 and you read in a 0, well if you read in a 0, you go back to state Q2, so you stay where you are, so you write Q2 here. Now if you're at state Q2 and you read in a 1 instead, well if you read in a 1, you stay where you are, at state Q2. Now if you're at state Q3 and you read in a 0, well if you read in a 0, you stay at Q3, so you write Q3. But if you're at state Q3 and you read in a 1, well if you read in a 1, that means you stay at state Q3, so you write state Q3 here. So the transition table just tells you where you're transitioning depending on what your current state is and your input. So see how it makes sense? Depending on what your current state is and your input, the transition function tells you your next state. So these are my states, these are my inputs, and these are my next states. Now 2 things we're missing. With the transition table, you always have to find your starting state and your final state. So let's actually do those first. So Q sub 0, which is our starting state, our state diagram tells us that we start at this state because of this little arrow. So our starting state is state Q0. And then a set of final states, F, is just all of the double circled states. So this is the only double circled one, so it's just state Q2. So again, it's a set of final states because you can have more than one final state, more than one accepting state. So if this was double circled, then the set of final states would be Q1 and Q2, but that's not the case. So using this information, you want to specify in your transition table which is your starting state. Well, the starting state is Q0, so you put a little arrow next to it. And which are your final states? Your only final state is Q2, so you put a star next to it. So if you're just given the transition table, you can draw the state diagram and you can provide the formal description because these are your inputs. These tell you all your states. The arrow tells you your starting state. The stars tell you all the states that go inside F. So you have everything you need here. And that's it. This is the formal description for this DFA. Regardless if you have an NFA or a DFA, a finite state machine M consists of the set Q, which is a set of all states, the alphabet sigma, which is a set of all input symbols, your transition function delta, Q0, which is your starting state, and F, which is a set of all final states or accepting states. So Q, which is a set of all states, is just going to be all your circles. So that's going to contain S0 as a state, S1 as a state, and S2 as a state. Your alphabet is going to contain, again, all of your input symbols that are being given into the machine, and the only input symbols that I see being read into the machine are 0 and 1. So this is going to be the set containing 0 and 1. Q0 is your starting state. This arrow says that S0 is my starting state, so that's going to be there. And F is a set of all final states or accepting states in your state diagram. Those are the double circle states. So there's 2 double circle states, state S0 and state S1. As for a transition function, we can represent it using a transition table or a state table. You start by having one column, and you're going to put all of the states from Q, so S0, S1, S2. And then while you're here, specify your starting state. Your starting state is S0, so add a little arrow there. And specify your final states, adding a star next to them, so you'll add a star next to S0 and S1. And then for every symbol you have in your alphabet, you want to make a column for each and every single one of those. So 1 for 0 and 1 for 1. And then go through the transitions. If you're at state S0 and you read in a 0, well, if I read in a 0, where do I transition to? State S1. But it's not just state S1. It's the set containing state S1. Because remember that the transition function for an NFA is the exact same thing as a DFA. It's saying pick a state from the set of all states, so one of these, and given an input from the set of all input symbols, so one of these, where you transition to next will be one of the elements of the power set of Q. For a DFA, it's just Q. It's saying where you're going to transition to next is going to be one of the elements from Q, so it's going to be either this state, or this state. But an NFA says it's going to be one of the elements of this set, and you're going to remember, well, a power set of any set is just a set containing sets. It's not going to contain like state S1, S2. No, it contains sets of elements. It contains the set of no elements. It contains a set of all of the elements of Q, so S0, S1, S2. And then it contains all of the elements of Q in their own sets, and so on. So where you will transition to given a state and a current input is going to be one of these sets of states. Either no states, you can transition to all of the states, you can transition to one specific state, like you would in a DFA, but with the NFA you have the option to transition to all of the states or just two states, and so on. So Garcia actually omits the sets, and so if you are at a state and you're reading an input, and you happen to transition to two states, like let's say S1 and S2, then he'll just write it like this when it's supposed to really be in sets. And so that's fine as long as you remember that it's really a set of states that you're going to. It's not just going to be S1 and S2. I'm going to use the proper notation just so you don't forget. But anyway, if we keep going, if we're at state S0 and we're reading in a 1, well, if I read in a 1, I transition to state S2. So the set of next states I'm going to is just going to be the set containing state S2. Now, if I'm at state S1 and I'm reading in a 0, well, notice that there's no transitions for 0. There's no arrows for 0. So when I read a 0 at the state, I can't go anywhere. I can't transition to any other state. So the set of states that I transition to is the empty set, the set with no states because I can't transition to any state. And we denote the empty set with the phi symbol. Now, if I'm at state S1 and I read in a 1, well, if I read in a 1, I stay at state S1. So I transition to state S1. So the set of states that I transition to is going to contain just state S1. Now, if I'm at state S2 and I'm reading in a 0, well, if I read in a 0, I transition to state S2. But also, if I read in a 0, I can transition to state S1. So the set of states that I transition to is going to contain state S2 and state S1. Now, if I'm at state S2 and I'm reading in a 1, well, if I read in a 1, I stay at state S2. So the set of states that I transition to is just going to contain state S2. For our second example, we're told to draw the state diagram for the DFA where all of the components of the DFA are defined as such. First thing I want to know is how many circles am I going to need? How many states? So I look at Q, I have 2 states, so I'll have 2 circles, one for Q0 and one for Q1. The next thing you can do is identify where your starting state and your final states are. You can either look at your transition table or this right here. This tells you that your starting state is state Q0. So for state Q0, you're going to put an arrow next to it, either like this or like that. And it says that your final state is state Q1. So you're just going to make state Q1 a double circle. If this weren't given to you, this arrow tells you that Q0 is your starting state and this star tells you that Q1 is your final state. Now the rest comes from the transition table. You just read it. If you're at state Q0 and you read in a 0 as an input, where do you go? Well, you stay at state Q0. So you stay at state Q0 if you read in a 0. Remember that this is your transition function. It tells you all of your next states given your current state and your current input that you're reading. So if we're here at state Q0 and we read a 1, we transition to state Q1. Our next state is state Q1. So we go to state Q1 if we read in a 1. Now if we're at state Q1 and we read in a 0 as our input, we transition to state Q0. So from state Q1, if we read in a 0, we go to state Q0. Then if we're at state Q1 and we read in a 1, we stay at state Q1. We're here and we read in a 1, we stay right here. And this is your state diagram that represents this DFA. Another question they can ask you is, what is the language of the machine? Remember that the language of the machine is just a set that contains all of the strings that the machine recognizes, that the machine accepts. If the machine just accepts a small amount of strings, then you can just list them. But if the set is really long, then it's kind of hard to list all of them, especially if there's infinite amount of strings that the machine accepts. So you would use set builder notation, which brings me to the point that there are different ways to describe the language of a machine. The first one is to literally list all of the strings that are in the language that the machine recognizes. If there's too many to list, then you use set builder notation to describe that set of strings. Another way is by just using words, and another way is using regular expressions. I'll cover these 3 now, And this we'll cover later, because to understand this, you would have to know what a regular language is in the first place, which we'll get to. A good way to start is to look at some of the strings that you can accept. So we start here at state Q0. At this state, we can read in as many zeros as we want, but in order to get to the accepting state, we need at least 1. So already I know I can have 0, 0, 0, 1, so as many zeros as I want, and then 1, and then I'm at the accepting state, and I can stop here, that's fine. Or I can do 1 as many times as I want. I can add 1 as many times as I want. As long as it's a 1, it's good. As soon as I read in a 0, it goes back to a non-accepting state, to Q0. And from here, I can do 0 as many times as I want, but in order to finish, I need a 1. What this tells you is 2 things. The first, you're going to have infinite amount of strings that this machine accepts, because again, you could do as many zeros as you want, this amount of zeros, this amount of zeros, this amount of zeros, but you need at least 1 to go to the accepting state, and then from there you can do as many 1s as you want, and so that's just an infinite amount of combinations. You can't physically sit here and list out all the strings. The second thing this tells you is, if you notice the pattern, the only way to get to the accepting state, or to stay at the accepting state, is if you have a 1. In other words, using words, the language this machine recognizes is the set of all strings on 0, 1, so the alphabet, that end with 1. So all of the strings in the language of this machine have to end with 1. That's the only way the machine will accept any string, if it ends with 1. So that's using words. With set builder notation, we can describe this as the language of the machine is a set of all strings, we're going to call the string W, such that you can literally just write W ends with 1. That's it. For this question, they're asking us, is this string containing 1, 1 a string in the language of the DFA below? So the DFA is the machine. So we're trying to see if this string is in the language of this machine. Similarly, they're asking us, is this string containing 1, 1, 0 in the language of the machine? Let's start by answering the first question. All you really have to do is trace. Where do you start? Well, your DFA tells you where to start. This arrow says, hey, start at state Q0. So at state Q0, I'm reading in a 1. So if I'm reading in a 1, that means I'm at state Q2 now. At state Q2, the next symbol that I have to read is a 1. So if I read in a 1, that means I'm at state Q1 now. Because I'm done reading the string and I ended up in an accepting state, in a final state, then this machine does accept this string. So the answer to this question is yes. Is 1, 1, 0 in the language of the machine? Well, you start at state Q0. The first symbol or character or variable you're reading in is a 1. So if I read in a 1, that means I'm at state Q2. At state Q2, I read in a 1. So I read in a 1, that means I'm at state Q1. And at state Q1, I'm reading in a 0. So if I read in a 0, that means I am at state QD. Because I'm done reading the string and I ended up in a state that's not accepting, that doesn't have a double circle, that means that this machine does not accept this string. So this string is not in the language of the machine. It's not in the language that this machine accepts. So it's a no. Now here's the thing. Notice how I showed no work. I just traced. But even if you're taking an exam and like you draw lines, it's kind of like your professor's not going to know what your thought process was. So what they do is they ask you to show your work using instantaneous configuration, or in other words, tracing. But we're writing it down. And this is how we do it. We start with a bracket. We start with our starting state. Your diagram will always tell you where to start. That's whatever state the arrow is pointing to, so that's state Q0. And because this is where you're starting at, you're going to write the entire string. So we're going to be doing this one first. That is 1, 1. And then you do an end bracket. And the idea is that you're at state Q0 and you're reading in a 1. So because you're reading in a 1, you are at state Q2 now. How do we write that here? Well, we use this symbol. It means this yields or this gives. So what does this give? What does this yield? Well, being at state Q0 and reading in a 1 leads you to state Q2. So now I have state Q2 and all I have left to read is just this one over here. You don't have to write the quotes, by the way. You could just leave it like that and that's fine, whatever you please, at least for Garcia. So now that we're at state Q2 and we're reading in this 1, so we're at state Q2 and we're reading in a 1, it yields state Q1, so this yields state Q1, and we have no more characters to read in. We just read this character, so now we're left with an empty string, and there's a special symbol for an empty string. So an empty string can be written as this. The symbol is called the epsilon. So we can replace this empty string with the epsilon symbol. And the idea is once you're at a state, in this case we're at state Q1, and you have no more characters, no more variables, no more symbols to read in your string, you just have an empty string. If that state is an accepting state, then the machine will accept this string. Now let's see what this looks like for this string. Where do we start? Where your diagram tells you to start, at this state Q0. When we start, we have yet to read the entire string, so that goes here, 1, 1, 0. Again, you can put the quotes, you don't have to. So at state Q0, we're reading in this first symbol. So here we're reading in 1, so that leads us to state Q2. And since we read this 1, we're only left with needing to read 1, 0. And then at state Q2, we read in the next symbol, which is 1. So I read in a 1, that brings us to state Q1. At this point, because we read this 1, we only have a 0 left to read, so we put a 0 there. And then at this state, since that's the only thing we have to read, we read it. We read in a 0, that means we go to state QD. So that's where we're at. And if I read this, then I'm left with no other symbols to read in the string. So that's an empty string, which we represent using the epsilon symbol. And once you see the symbol, check the state that you're in. Is this an accepting state? Well, QD is not an accepting state. How do I know? Because it doesn't have a double circle. So because you ended and the state you ended at is not accepting, then this machine here will reject the string you tried to read, this string. So again, the key is once you get to this symbol, look at the state you ended with. It has to be an accepting state, means it has a double circle in order for the machine to accept the string that you were reading. Otherwise, it will reject the string that you were reading. And this is the idea that I drew before. In this first case, 1, 1 was the string W. It went inside the machine, and the machine accepted 1, 1 because it was an element of the language of the machine. The set of all of the strings the language accepts. In this case, 1, 1, 0 was our W, was our string. It went inside the machine. This is our machine. We started reading 1, 1, 0, and at the end of the day, this string was rejected because 1, 1, 0 was not an element of the language of the machine. It was not one of the strings in the set of all the strings this machine recognizes. And again, showing the work is called instantaneous configuration or tracing. Here we're asked, is this string made up of A, B, B? So our alphabet is just going to consist of A and B. This is our set of input symbols, all of these symbols that we could ever read in. So is a string in the language of the NFA below? So instead of a DFA, this time we're given an NFA, and I know it's an NFA because for this state you can see that there's 2 arrows for an input symbol A, 2 transitions for an input symbol, but we know that's not allowed in a DFA. A DFA only allows exactly 1 arrow, no more, no less, for every input symbol. So nevertheless, it's an NFA, and it's the same process. You're at state S0, so you have a bracket, the state you're in, and you start with the entire string. You want to read in A, B, B. Again, you can put the string if you want. You don't have to if you have Garcia. Then from here, I want to read in this first symbol. So if I'm at state S0 and I'm reading in an A, well, if I read in an A, I actually can go to 2 places. I can stay at state S0. So I stay at state S0, and then at that point, I only have A, B, B left to read. Or go to state S1. So I go to state S1, and at that point, I have A, B, B left to read. So notice how it's already different. We're not doing this linear pattern of saying, okay, this yields the next state S0, A, B, B, because it's not linear. It goes to 2 places. So that's why we kind of do it as this vertical tree. So what I like to do is just pick one and expand it. So I'll pick this one. At this point, we're at state S1, and we're reading in the next input symbol, that's A. So if we're at this state and we're reading in an A, well, that means I go to state S0. There's no other transition for A. So from here, I go to state S0, and I'm left with reading BB. At this point, I'm at state S0. Next input symbol I have to read is B. So if I'm here and I'm reading in a B, well, notice there aren't any transitions. There aren't any arrows for B. We just have one for A. We have another one for A. There's no transition for B. So because we actually cannot read in a B here, this is a dead end. So in other words, the string would be rejected if it takes this path. But luckily for us, we have another path to explore. At this point, we're at state S0, and we're reading in our next input symbol, that's A. Well, if I read in an A, right over here, I could stay at state S0, and what's left to read is BB. Or if I'm at this state and I read it in A, I go to state S1, and what's left to read is BB. Again, just pick one of these to explore. I'll pick this one. If I'm at state S0, the next input symbol is B. That's what I'm reading. But again, there is no transition for B. I don't see any arrows for B. So it's a dead end. And because of that, if we take this path, the string will be rejected. Now, finally, we have this one to expand. At this point, we're at state S1, and the next input symbol is B. Well, if I'm at state S1 and I read in a B, I go to state S2, and what's left to read is a B. Now I'm at state S2 and I'm reading in a B. Well, if I read in a B, I can either stay at state S2, and remember that this is a string containing B. And if we're done reading B, then we're left with the empty string, and we denote that using the epsilon symbol. So we're left with an empty string, the epsilon symbol here. But if we're at state S2, not only can we stay at state S2 if we read B, but we can also, if we read B, go to state S1. So we go to state S1, and again, if I read this, there's nothing left, so it's just an empty string. And it's the same idea. As soon as you reach this epsilon symbol, you're done reading the string, you want to check which state did you end up in. State S1, if you look at it, is not an accepting state. So if you're done reading the string and the machine hasn't accepted it by now, well, there's nothing more to read. You're done. So at the end of the day, the machine will just reject that string. Here we ended up reading the string and we ended up in state S2, which if we go look is an accepting state. Why? Because I see the double circles. So if I'm done reading the string and my machine decided at the end of the day, okay, yeah, I'm going to accept it, well, then we're going to accept that string. We're told to construct a DFA, so a finite state machine, that recognizes or accepts the set of all bit strings that begin with 0 or 1, 1. So our finite state machine will be reading in a bunch of bit strings. The bit in bit strings means that your strings will only contain 0 and 1 as the input symbols or the characters or the variables in the string. So you won't see a string that's like 0, 1, A, B, C, D. Because again, the input symbol should only be 0 and 1, not something like A, B, C, D, and so on. So this machine should accept all bit strings that start with 0 or 1, 1, meaning a string that looks like this starts with 0, the machine should accept. A string that looks like this, the machine should accept because it starts with 1, 1. A string that looks like this, 0, and then anything that comes after, it doesn't matter. It could be 1, 0, 1, 1, 0, 1, whatever. The machine should accept because it starts with 0. Any string that starts with 1, 1, and then whatever comes after, doesn't matter. The machine should accept. If you have a string that starts with 1, 0, the machine should not accept that because it doesn't start with 0, nor does it start with 1, 1. If you have 1, 0, anything that comes after that, again, the machine should not accept that. So we're trying to construct a machine that follows these rules, that will either accept or reject one of these bit strings. So we want to define this type of machine, and we define our finite state machines by specifying the set of all states, our alphabet, our transition function, Q0, which is our starting state, and F, which is the set of final states. Something that I already know because of the information given in the problem is the alphabet. Recall that our alphabet is a set of all input symbols, all of the symbols that we can possibly read from a string. Because all of the strings that the machine is reading are bit strings, meaning they only contain zeros and ones, then the only input symbols we'll ever have are 0 and 1. So I already know that my alphabet is equal to the set containing 0 and 1. Everything else I don't know yet, because I don't have any states, I don't have any states to transition to, I don't have a starting state, I don't have final states. To get the rest of this information, we should start thinking about what the machine should look like, and a good place to start is a starting state, which we know is just a circle, like any other state is, and we can call it state Q0, you can call it whatever you want, S0, S for state, you can call it A, it doesn't matter, but what you do have to do is emphasize that it's a starting state by drawing a little arrow right next to it. So at this state, whatever bit string is going inside the machine here, if it starts with 0, then this machine should accept that string. In other words, if we're at the start state, and the first symbol we read is a 0, that should transition us to an accepting state. We can call it state Q1, and to make sure that it's an accepting state, we have to double circle it. Now at this state, you've already read a 0, so your string could look like 0, 1, 0. If you're at this state, you read in a 0, so you read the 0. No matter what comes after, whether it's a 0 or a 1, you stay at the accepting state, because this string has already been accepted because it started with a 0. Now recall, for a DFA, every state needs a transition for every symbol in the alphabet. Our alphabet contains 0 and 1, 2 symbols. If we go back to the state, we only have one transition. We only have one arrow, so you can use transition and arrow interchangeably, for 0. But we don't have one for 1. In order for this to be a DFA, this state has to have an arrow for both 0 and 1. So then the question is, if we're at this state and we read in a 1, do we stay at this state or do we transition to another state? Well, there is a special condition where if the string that you're reading starts with 1, 1, then that should take you to an accepting state. But let's start step by step. If I'm at this state and I read in a 1, let's say I transition to another state, call it Q2. But if I'm at state Q2 and I read in a 1, that means at this point I've read in 1, 1, and then another 1, and so I should transition to an accepting state. Because no matter what comes after, 0 or 1, it could be 0, 1, 0, 1, 1, 1, it doesn't matter. The string started with 1, 1, so this machine should recognize that string, it should accept that string. So after reading 1, 1, it should transition us to an accepting state. I could have gone here and made another accepting state, but that would be redundant because I already have an accepting state. Now again, if this is a DFA, every state needs to have an arrow, needs to have a transition for every symbol in the alphabet. Right now, this state only has an arrow for 1, but it doesn't have an arrow for 0. So what happens at this state if I read in a 0? Well, if I'm at this state, it's because I've already read in a 1, this 1 here. If I read in a 0, I already know that this machine here cannot accept this string, because we can only accept strings that start with 0 or 1, 1. This does not start with 0 and it does not start with 1, 1. So therefore, if I read in a 0, I don't want to transition to an accepting state. So we have something special called a dead state, and it's a state that once entered, you can't transition to any accepting state after that. You're just stuck there. It's a dead end. In other words, the machine will never accept that string. So we can say if we read in a 0, we can transition to a state and we can call it QD. You don't actually have to call it D for dead. You could just call it Q3, doesn't matter. But it's just another state. You're just saying, hey, if I'm at this point and I read in a 0, there's no way that this machine should accept that string. So transition to a dead state. And so no matter what you read after that, whether it's a 0 or a 1, you're going to stay at the dead state because there's no way you're going to get out and transition to an accepting state because you just cannot accept that string. And we can test it. Let's test 0, 1, 0. We start at the starting state. You read your first input symbol, that's 0. If I read in a 0, I'm at this state. I read the next input symbol, that's 1. So if I read in a 1, I stay at this state. I read my next input symbol, that's 0. If I read in a 0, I still stay at this state. Because I finished reading the string in an accepting state, this machine will accept this string, which makes sense because it starts with 0, so it should. Let's try 1, 0, 1. Again, we start at the starting state. We read our first input symbol, that's 1. So if we read in a 1, we're now at state Q2. We read in our next input symbol, that's 0. So if we read in a 0, we're now at state QD. We read in our next input symbol, that's 1. So if we read in a 1, we are now back at state QD. Because we're done reading the string, and we ended up in a state that's not accepting, this machine will not accept the string. It will not recognize a string. No matter if you read in a 0 after that or another 1 after that, you're just going to keep coming back to here and you'll never get out to an accepting state because this string does not start with 0, nor does it start with 1, 1. Now that we have our state diagram, we can define what our states are, our transition function, our starting state, and our final states. Now we can define Q, which is a set of all states, as a set, and then just write down all your states. So your states are circles. You have Q0, Q1, Q2, and QD. Q0 is just our starting state. This stays our starting state. Why? Because there's an arrow there. So Q0 is our starting state. And then F is our set of final states. We only have one final state, one double circled state, so that is Q1. As for our transition table, as always, just make a column. In this column, just list your states. So you have Q0, Q1, Q2, and QD. Specify your starting state. Your starting state is state Q0. So next to Q0, draw an arrow. Specify your final states. We only have one final state, that's Q1, so next to Q1, draw a star. And then on this side, you want to have a column for every symbol or every element in your alphabet. So 1 for 0 and 1 for 1. The values that are going to go here are your next states. And the state you go to next, the state you transition to next, hence the transition table, depends on the current state you're in and the current input you're reading. So let's go through this. If we're at state Q0 and we read in a 0, if we read in a 0, that means we're at state Q1, so I write Q1 here. If we're at state Q0 and we read in a 1, if I read in a 1, I transition to state Q2, so I write Q2 here. If I'm at state Q1 and I read in a 0, if I read in a 0, I stay at state Q1, so Q1 goes here. If I read in a 1, I also stay at state Q1, so Q1 goes here. If I'm at state Q2 and I read in a 0, well, if I read in a 0, I transition to state QD, so I write QD here. And if I'm at state Q2 and I read in a 1, well, if I read in a 1, I transition to state Q1, so Q1 goes here. If I'm at state QD and I read in a 0, well, if I read in a 0, I stay at state QD, so state QD goes here. And if I'm at state QD and I read in a 1, if I read in a 1, I stay at QD, so QD goes here. So these are all of the next states, the states that I'm transitioning to given all of the states and whether you're reading a 0 or a 1. And that's it. We managed to construct a DFA that recognizes, accepts all of the bit strings that start with 0 or 1, 1. But what if it told us to construct an NFA? Well, this actually already is an NFA. So here's a fact. Every DFA is an NFA. Why? Because the condition for a DFA is that every state needs exactly one transition, so I should add that, for every symbol in the alphabet. But for an NFA, it says the exact same thing. You can have exactly one transition for every symbol in the alphabet. So this is already an NFA. The definition of a DFA is inside the definition of an NFA. But an NFA is more flexible because not only can you have exactly one transition for every symbol in your alphabet, but you can have 0 or more transitions. So if we could have 0, if this told us to construct an NFA, then for this state, we didn't need to have a transition for 0 because we could have 0 transitions for this symbol. So we could have erased this and that would have been an NFA, but it wouldn't be a DFA. Because in a DFA, every state needs to have exactly one transition for every symbol in the alphabet. So one arrow for 0, one arrow for 1. This state has one arrow for 1, check, but it has 0 arrows for 0. You don't see any arrows for 0. So it's not a DFA, but it is an NFA because an NFA allows you to have 0 arrows for any symbols in your alphabet. And you can see that here, 0 transitions for every symbol in your alphabet is not inside the definition of a DFA. So not every NFA can be a DFA. Now in the next section of this video, I want to finally dedicate a bit of time to discussing the differences between DFAs and NFAs in more detail. In a DFA, for every state that you have, for all inputs in your alphabet, so the set of all input symbols, let's say that set only contains 0 and 1, there should be exactly one transition. So let's say I have 2 states and this is the final state, the accepting state. If this were to be a DFA, then for every state that I should have exactly one transition, one arrow for 0 and for 1. So for this state, I should have exactly one arrow from 0 to another state or itself. So I could have this as well. And then I should have exactly one transition for 1 to another state or itself. In this case, it goes to itself. In other words, for every state, I should have exactly one arrow for each one of my inputs. No more, no less. But that has to be true for every state. So for this state, I should also have exactly one arrow for 1 and exactly one arrow for 0. A simplified version of that is just one arrow, 0, 1. So this is what we would call a DFA. If let's say this is state Q0 and state Q1. What wouldn't be a DFA is if I had more than one transition, more than one arrow for an input. So for example, if I read in 1, it transitions to the same state. But also if I read in 1, it can transition to this state. This is not a DFA because it violates the rule that each state should have exactly one arrow, one transition for each of its input. In this case, 1 has 2 arrows, 2 transitions, so that is not a DFA. Now if we remove this transition for 1, this is also not a DFA because for this state, I'm missing exactly one transition for 1. I should have a transition for 1. Either it goes to itself or it goes to another state. What this would be is an NFA. So let's talk about what an NFA is. For an NFA, for every state that you have, for all of the inputs, so for 0 and 1, there is either 0, 1, or more transitions. So this is fine for an NFA because for this state, I have 0 transitions, 0 arrows for 1, which is acceptable by an NFA. I have 1 transition, 1 arrow for 0, which is acceptable by an NFA. And if I had something like this, then that's also an NFA because for this state, I have more than 1 or 0 transitions for my input 0, which is perfectly fine for an NFA, but it is not for a DFA. And this reinforces the naming of DFAs and NFAs. DFAs are deterministic, so that D stands for deterministic because we're able to determine, given a state and an input, exactly where we're going next. But NFA is the opposite. It's non-deterministic because we're not 100% of the time always able to determine where we're going next, because for some states, sometimes we'll have 2 next states given a certain input. And we can't predict the future. We're not able to determine with 100% which path is going to be taken. It's non-deterministic. Now let's go ahead and practice. Is this a DFA or an NFA? Well, I try to see if it's a DFA first. So for every single state, I'm looking for only 1 arrow for each input. But in this case, I see 2 arrows for the same input. So it's definitely not a DFA, so it's an NFA. Here, for every single state, I see exactly 1 arrow for each of the inputs. So it's a DFA. For this state, I see 1 arrow for 0 and another arrow for 0. For a DFA, there's exactly 1 arrow, 1 transition for each input. So this is an NFA. Here, I see an arrow for 0, an arrow for 1. Here I see an arrow for 0, an arrow for 1. Here I see an arrow for 0 and for 1, so this is a DFA. Here I see an arrow for 0 and 1. Here I see an arrow for 0 and 1. Here I see an arrow for 0 and 1, so it's a DFA. Here I see an arrow for 1 and for 0. Here I see an arrow for 1 and 0. Here I see an arrow for 1 and for 0, so this is a DFA. Here I see an arrow for 1 and I see another arrow for 1. So it's not a DFA, so it's an NFA. Here I see an arrow for 0 and for 1. Here I see an arrow for 0 and for 1. Here I see an arrow for 0 and 1. Here I see an arrow for 0 and 1. Here I see an arrow for 0 and for 1. And here I see an arrow for 0 and 1. Exactly 1 arrow for each input in every state, so it's a DFA. Here I see an arrow for 1, but not for 0. I'm missing an arrow for 0. So it's not a DFA because for this transition, I have 0 transitions, 0 arrows for 0, and I need exactly 1, no more, no less. So I can't have 0 transitions. So already I know it's an NFA. Another way I know it's an NFA is that this state only has a transition for 0 and has 0 transitions for 1. So again, it has 0 less than 1 transitions for an input, so it's not a DFA. so it's an NFA. For this state, I see exactly one arrow for 1 and 1 for 0. For this state, I see one arrow for 0 and another arrow for 0. So it's definitely not a DFA, because for a DFA, we would only have one arrow for 0, so it's an NFA. Another way I would know it's an NFA is because for this state, I have one arrow for 0 and I have another arrow for 0, so again, it wouldn't be a DFA, so it would be an NFA. For this state, I have exactly one arrow for 0 and for 1. For this state, I have exactly one arrow for 0 and for 1. For this state, I have exactly one arrow for 0 and 1. And for this state, I have exactly one arrow for 0 and 1, so therefore it is a DFA. So what conclusion can we draw from this? Well, as we went through these, you might have been like, wait, this is a DFA because for every state you have exactly one arrow, one transition for each of your inputs, one for 1, one for 0. 1 for 1, 1 for 0, 1 for 1, 1 for 0. But isn't that also an NFA? An NFA for every state, for all inputs, so in this case for 0 and 1, you have exactly 0, 1, or more transitions. But you can have exactly one transition for each of your inputs in an NFA. So the definition of a DFA is inside the definition of an NFA. So therefore, we can say that every DFA is an NFA, because look, this exactly one is inside the definition of an NFA. So all of these machines that you see here that are DFAs are also NFAs. But we cannot say that every NFA is a DFA. That is not the case. Because if you take a look at this NFA, can we say it's a DFA? No, because for this state, we have one arrow for 0 and another arrow for 0, and a DFA only allows exactly one arrow for 0. So this NFA would not be a DFA. So we cannot say that every NFA is a DFA. We can only say that every DFA is an NFA. But if it is the case that you have an NFA that's not a DFA, if they can be different, then can one of them recognize more languages than the other? And the answer is no. They both recognize the same languages. But how? Even though they may not be the same machines, for any given NFA, you can find an equivalent DFA. We say equivalent, as in they're not the same machines, it's still not going to be the same machine, but it will accept the same language as the NFA. So how can we do that? Notice how I don't say, given a DFA, you can find an equivalent NFA, because by definition, a DFA is already an NFA, so you already have the equivalent, in fact, the exact same machine as an NFA. So it's kind of trivial, nobody would ask that question. What they will ask is, given an NFA, that's not a DFA, obviously, can you find an equivalent DFA? So find a completely different machine, but it accepts the same language. That's why they are equivalent. Not the same, equivalent. So again, the question arises, how do we do that? So here's an example. We're told to use a technique discussed in class, which is the one I'm going to show you right now, to find a DFA equivalent to a given NFA. So this is our given NFA. The first thing you want to do is make a transition table for this NFA. So our delta, our transition table, by the way, if you have trouble writing this symbol, it's like an 8, but you just don't do this part. So it's like this. You stop here. So it's like that. So for a table, what's going to go in the first column are states. So each circle is a state, so we have S0, S1, S2. So S0, S1, S2 are going to be our states. And then every column after that is going to be one for every input symbol we have. So the only inputs we have are 0 and 1. So we're going to have a column for 0 and a column for 1. And this is how we read it. Given that we're at state S0, we're reading in a 0, where are we going? Well, when we read a 0, we go to state 1. So we go to state 1. Now, why do we write it in a set? Because with NFAs, remember, we can go to more than one state. In this case, it was just one state, but sometimes we can go to a set of state, either state 1 and state 2, which we'll see right now. If we're at state S0 and we're reading in a 1, notice that we go to state S1, so we write S1, but we also go to state S2 because we're reading in a 1. So this is a perfect example that given a state and an input, we can go to a set of states. We can go to multiple states. So that's why we use sets. When we're at state S1 and we read in a 0, well, in this state, we actually don't read anything. There's no transitions for 0 or 1. So the set of states that this combo goes to is empty because there's no transition. So how do we describe the empty set? With this symbol. Same thing here. If we're at state S1 and we're reading in a 1, well, there's no arrows with a 1. So we don't go anywhere. So the set of states that we go to is empty, which is the symbol here. If we're at state S2 and we're reading in a 0, well, if we read in a 0, we're now at state S1. So the set of states that we go to just contains state S1. If we're at state S2 and we're reading in a 1, well, if we're reading in a 1, we stay at state S2. So the set of states that we go to just contains state S2. Now we also want to label the starting state and the accepting states or final states. The starting state is S0, so we put a little arrow next to S0. And the accepting states or the final states are the ones that are double circled. So those are S0 and S1, so we put a star next to S0 and S1. And that is our transition table for an NFA. Now the second step is to find the transition table for the equivalent DFA. But you might be like, well, I don't have the state diagram for the equivalent DFA, so how am I supposed to find the transition table? Also, isn't that what I'm trying to find in the first place, the equivalent DFA? So what do you mean? Well, you can actually get to the transition table by just using this table. So from here, you want to copy the same template where you have a column for each of the inputs that you have here, and here will be all of your states. Now, where do you start? You start by copying the first row. The only difference is you're adding curly braces to this state right here. So everything should have curly braces. Everything should be in a set. Now, the first thing that's different is that anytime you see something that you haven't seen before in the entire table, because before adding these, the table just consisted of this set. So these are two new things. You want to add those as a new state. So I haven't seen this before, so I'm going to add it as a state. I haven't seen this before, so I'm going to add it as a state. Then you can start. You basically ignore the fact that there's curly braces there, and it's the same thing. You read it the same way. If you're at state S1 and you're reading in a 0, where do you go? Well, that table tells you if you're at state S1 and you're reading in a 0, you go nowhere. You go to no state, so that's the empty state. So you're just going to write the empty state. Wait, this is something I haven't seen before in the entire table, so I'm going to add it as a state. Moving on, if I'm at state S1 and I'm reading in a 1, where do I go? Well, this table tells you if you're at state S1 and you're reading in a 1, you go to no states. So that's the empty state, so you write the empty state. So we're using the same state diagram. But instead of going through it again and be like, oh, if I'm at state S1 and I read in a 1, where do I go? There's no transitions, I go nowhere. We already figured all that out, and we have that information here. That's why we make the transition table for the NFA. So it could help us over here. Now, I've already seen this in my table. I've seen it here, so I'm not going to add it as a state. Moving on. Now, this is a second thing that's different. This says, find the set of next states if I'm at state S1 and S2 and I'm reading in a 0. So all you do is look at the states in here, S1, S2, highlight them here. What's the input? 0, highlight that here. Take the intersection of these, so that's these two, and you're taking the union of those. So you're taking the union of the empty set, which is literally an empty set, and the set containing S1. Now remember that union means you're bringing all of the elements in both of these sets in a union. You're bringing them together. So the result is just going to be all of the elements in this set, which is no elements, so you're adding nothing to the set, and all of the elements in this set, which is just S1, so you add S1 and you're done. So in general, when you have the union of an empty set and another set, the resulting set is just going to be this other set because there's nothing to add from this set. So therefore, the set of next states that we go to is S1. Visually, what's happening is you're saying if I'm at state S1 and I'm at state S2 and I'm reading in a 0, where do I go? Well, if I'm at state S2 and I'm reading in a 0, I go to state S1, so I go to S1. If I'm at state S1 and I'm reading in a 0, I go nowhere, to no states, so you just add nothing. So really the set of next states that you go to is just S1, so that's what we have here. Now, I have seen this before in the entire table. I've seen it here, so I'm not going to add it as a state, and I'm going to move on. So now if I'm at state S1 and S2 and I'm reading in a 1, what's the set of next states that I go to? Well, instead of going to the diagram and probably making mistakes because you're going too fast, just look at the states that are here, S1, S2, highlight them. What input are you working with? 1. Take the intersection of these, so these two, and take the union of them, right? Again, we know that the union of the empty set and any other set is just going to be that set itself, so that's why we have the set containing state S2. Now, we haven't seen this in the entire table yet, so we're going to add it as a new state. Now, if I'm at no state, because that's what this means, there's literally no state, and I'm reading in something, well, it doesn't matter what I'm reading, I'm literally at a state that does not exist. So I'm going to go nowhere, which is also the empty state. Anytime you see this as a state, you're going to the same place across the board. It's just going to be the empty state. Now, if you're at state S2 and you're reading a 0, where do you go? Well, your table tells you that if you're at state S2 and you're reading a 0, you go to state S1, so that's what you put here. I've seen this before in the entire table. I've seen it here, so I'm not going to add it as a state. If you're at state S2 and you're reading in a 1, where do you go? Well, your table tells you that if you're at state S2 and you're reading in a 1, you go to state S2, so that's what you're going to add here, state S2. And I've seen this before in the entire table. I've seen it here, so I'm not going to add it as a state. And because you ran out of states, you are done. This is a transition table for the equivalent DFA, and so using this, you can draw the equivalent DFA. But there is one more thing you want to define, and that is your starting and final states. Now, the rule is the starting and final states for the equivalent DFA are the exact same ones from the NFA. So in the NFA, if your starting state was S0, then in the DFA, the set containing S0 will also be your starting state. In the NFA, if your final states were S0 and S1, then in the DFA, any set containing S0 and S1 will be your final states. So this set contains S0, it's a final state. This set contains S1, it's a final state. This set contains S1, so it's also a final state. And now you're really done and you're ready to draw the state diagram for the equivalent DFA. So it's the same way we did as before. These are states. You have 1, 2, 3, 4, 5 states. So you're going to have 5 circles and you're going to label them as you see over here. So this is going to be the state, the set containing S0. Here we're going to have the set containing S1 as a state. Here we're going to have the set containing S1 and S2 as a state. Here we're going to have the empty set as a state. And here we're going to have the set containing S2 as a state. And then you just do what your transition table tells you. It says if you're at this state and you're reading in a 0, you go to this state. If you're reading in a 0, you go to this state. If you're at this state and you're reading in a 1, you go to this state. So if I'm reading in a 1, I go here. I'm done with this row. If I'm at this state, right over here, and I'm reading in a 0, I go to this state. So that's right here. If I'm at this state and I'm reading in a 1, I go to this state. So both 0, 1 goes to this state. I'm done with this one. If I'm at this state, which is right here, and I'm reading in a 0, I go to this state. So that's reading in a 0, I go here. If I'm at this state and I'm reading in a 1, I go to this state. So if I read in a 1, I go here. If I'm at this state, and I'm reading in a 0, I stay at that state, and if I'm reading in a 1, I stay at that state. So that's going to be an arrow, 0, 1. If I'm at this state, which is right here, and I'm reading in a 0, I go to this state. So reading in a 0 takes me here. And if I'm at this state and I read in a 1, I stay in that same state. If I read in a 1, I stay in the same state. And again, this state is a starting state, so I'm going to put an arrow. It's also a final state, so I'm going to double circle it. This state is also a final state, so I'm going to double circle it. And this state is also a final state, so I'm going to double circle it. You can see why we call it equivalent, because these machines are literally not the same. You can visually see that here we have 1, 2, 3, 4, 5 states, while here we have 3 states. They are literally not the same, and yet both of these machines recognize the same language. Now let's go back to the formal definition of a DFA and an NFA. Remember that they are exactly the same. The only difference is the transition function. For a DFA, we said given a current state and the current input that we're reading, we're going to get another state Q. That's our next state, the state we're going to transition to. But I think a better way to say this is, really, this is the set of all states. And this is a set of all input symbols. These are sets. Let's say that Q is a set containing S0 and S1. So these are states. We have 2 states. And our alphabet is a set containing 0 and 1. So 0 and 1 are our input symbols. What we're really saying is given an element, a state from the set of all states, so it could be this one or this one, and given an element from the set of all input symbols, so it could either be 0 or 1, we're going to get an element from the set of all states. So we're going to get either this one or this one. For example, let's say that this is our DFA. What this is saying is we're starting at this state as 0. So given one of the states from the set of all states from Q, in this case it's S0, given the input that we're reading, so we're picking one of the elements from the set of all input symbols, so let's say that it's 0, we are going to get an element from this set as our next state, as a state we're going to transition to next. And in this case, if we're at S0 and we read 0, we actually go to S1. S1 is an element of the set of Q. So we get S1 here, given that our current state was S0 and our input was 0. And this is a good way to think about this, to phrase this, because when we look at the NFA, it says given one of the states in this set, and given whatever input you're reading, so one of the elements, one of the inputs in this set, we're going to get an element from this set. This is the power set of Q. Remember that a power set is an actual set. It includes all of the possible subsets of Q. In other words, all of the possible groups that you can make from all of the elements in this set when you're putting these elements together. So the power set of Q can include the possibility of you putting none of these elements together in a set. So that would just be the empty set. Another possible subset you could have is a set that just contains S0 by itself. Another one you can have is one that contains S1 by itself. Another one that you can have is one that contains S0 and S1 together. In that case, that would be the original set, Q. And so this is the power set of Q. And it actually makes sense that the transition function for an NFA, given a state in this set and given an input in this set, the state that you will transition to, because that is what the transition function tells you, is going to be an element in this set, in the power set of Q. So it's going to be either one of these. And that makes sense for an NFA, because with an NFA, given a current state and the input that you're reading, you don't just have to transition to only one state like you did with a DFA. You can transition to 0, that explains the empty state, no states, to one state, so that explains these, or to more than one state, so that explains this. For example, let's say that this was our NFA. What this is saying is, okay, let's start at state as 0. So S0 is an element of the set of all states. So let's say this is S0. So given S0, and then let's say we're reading in a 1 as our input. So 1 is an element of this set of the alphabet. What is going to be the next state that we transition to? Well, it's going to be one of these. That's what the transition function says. It's going to be one of the elements of the power set of Q. In this case, if we start at S0 and we read in a 1, we don't just go to one state. We go to a set of states. We go to state S0, because if we read in a 1, we come back to S0, but we also go to state S1. So we actually have a set of states that we're transitioning to next. We're transitioning to S0 and S1. And that's only possible with an NFA, because with a DFA, we can't have this, nor can we have this. For every input symbol that you have, we can only transition to one state, which is why we don't bother with the power set, and it's just Q, a DFA. All the possible states that we can transition to next is just going to be one of the states. We can't ever transition to multiple states given the same input with a DFA, because for every state, you can only have exactly one transition for every symbol in the alphabet. So if I pick 0, for a state, I can only go to one place. I can't go to another state. I can't go to multiple states. At the same time, if I'm working with 0 as an input for the state, I can't just have no transitions. Like, I have to go to exactly one state, either another state or the same state for 0. So the fact that my next state can't just be no state removes the need for this one, and the fact that my next state can't be multiple states removes the need for this one. So at the end of the day, the sets that I can transition to are just single sets. They're just one set, which is why at the end of the day, we only need Q, because that's what this is. We don't need to do the power set of Q or DFA. So if we go back to this, where they mentioned to use a technique discussed in class to find a DFA equivalent to a given NFA, that technique has a name. What we just did has a name, and it's called subset construction, also sometimes known as power set construction. And that makes sense because all of the states for the equivalent DFA, all of these states come from the power set of the original set of states, Q. So Q was made up of these states, state S0, S1, and S2, and the power set of Q is all of the subsets of Q, which included all of these states. That's why it's called subset construction. Because at the end of the day, if you look at the state S0, if we read in a 0, we go to state S1, which is what we have. But if we read in a 1, we don't just go to state S1, but we also go to state S2. How does that translate to the DFA? Well, instead of saying, okay, if we read in a 1 for S0, we go to two places, S1 and S2, they say, okay, we have this state, and instead of going to two places when I read in a 1, I'm just going to say when I read in a 1, I'm just going to go to a set of states, S1 and S2. And so it's still saying the same thing, S1 and S2, but it's following the rule of a DFA that says for every state, I can only have exactly one transition, one arrow for every input in my alphabet. So in this case, for 1, I can't have two arrows, I can only have one arrow, and it's still saying the same information. It's like saying if I'm at the state of sleeping, I'm sleeping, right? But I wake up. 1 means wake up. I either yawn or I put the blanket over my head because I'm tired still. So that's another state. But this is saying the same thing. When I'm sleeping, when I wake up, I either yawn or put the blanket over my head. So it's still saying the exact same thing while following the rules of a DFA. So at the end of the day, the states that we are constructing are subsets of the original set of states. And the reason why sometimes people write it as 2 to the cube, that's because that's the cardinality. Because remember that if you have 2 elements in your original set, then the amount of elements you're going to have in this set is going to be 2 to the number of those elements you had in the original set. So 2 squared is 4, which is why we have 1, 2, 3, 4 elements. If we had 3 elements like S2, so we had 3 states, then it would be 2 to the third, right? 2 to the q, the number of states. And so that would be 8. We would have 8 possible subsets. So that's why you'll see 2 to the q sometimes. But really, 2 to the q is you taking the power set of q and calculating the cardinality, the size, the number of elements in this set, and that will be 2 to the q. Now, what's an application of knowing this fact? How can you use it? Well, if we go back to the previous problem where you're given an NFA and told to find an equivalent DFA, if you know that the states of the equivalent DFA, when you're converting from an NFA to a DFA, can only be one of these, one of the elements in the power set of Q, then the maximum number of states that this DFA can have is the maximum number of elements in this set. So we can generalize and say, given any NFA, the equivalent DFA will have a maximum of 2 to the q states, where q is the cardinality or the size or the number of elements in q in the set of original states. Sometimes you'll see 2 to the n. It doesn't matter what variable they use, t, v, doesn't matter, as long as you understand that this variable is supposed to represent the number of elements in the set of states in the NFA, so the original q. So if we go back to this question, what they could do is they can give you an NFA and ask, given that NFA right here, what is the maximum number of states that the equivalent DFA built with subset construction, which is a technique discussed in class, can have? And so we know from what we just talked about that the maximum number of states that any equivalent DFA can have given an NFA is 2 to the q, where q in this case is the number of elements in the set of original states q, or the cardinality of the set of all states. So in this case, 2 to the q is going to be 2 to the number of states in our original set of states q. So that's just our circles 1, 2, 3. So this is our set q. There's 1, 2, 3 elements in here. So that's 2 to the third power. And 2 to the third power we know is 8. So what this is saying is, without even having to do the work, we already know that the maximum number of states that we could have over here in this column is 8. We can't have more than that. The maximum number of states that we could have in the equivalent DFA state diagram is 8. So something like this. And again, the math behind that is that we know all of the possible states that could be in the equivalent DFA come from the power set of Q. So the power set of Q, remember, power set is just all of the possible subsets. In other words, all of the ways you can group the elements of Q, and Q, remember, is just a set of states. So we have S0, S1, and then S2. So we can group these 0 ways, so that would be the empty set, also denoted with the symbol phi. We can group S0 in one subset. We can group S1 in one subset. We can group S2 in one subset. We can group S0 and S1 together. We can group S0 and S2 together. We can also group S1 and S2 together in one subset. And we can also group all 3 of them together, which in that case would just be the original set Qs, S0, S1, and S2. And how many elements do we have in this power set? Count. We have 1, 2, 3, 4, 5, 6, 7, 8 elements. So all of the states that could ever be here, all of the circles that we could have, are one of these elements from this set, which is why the maximum number of states that we could have in this column are 8. And you can see we have the empty set as one of the states, that's this one. We have the set containing S0 as one of the states, that's this one. We have the state containing S1, that's this one. We have the state containing S1 and S2, that's this one. We have the state containing S2, that's this one. So notice an interesting thing, the maximum number of states that we could have is 8. It's all of these states, and yet we don't have all of them. This equivalent DFA, in fact, has only 1, 2, 3, 4, 5 out of these 8 states. So we can generalize and say, okay, just because I can have 8 states doesn't mean I will. The maximum number of states is 8 in this case, but I can have less. So if they ask you, given the NFA above, how many states does the equivalent DFA built with subset construction have, you would actually have to go through and find out how many states. This is not a theory question. This is not, can I guess? You have to go through the process, find out how many states you're going to have, count them. So in this case, it's 1, 2, 3, 4, 5 states. So even though we could have had 8 states, some are just not needed or some are unreachable. And we ended up with 5 states, which you can see 1, 2, 3, 4, 5 states. We have 5 states in this column. And so the application of knowing that the maximum number of states your equivalent DFA can have is 2 to the q is not just answering this question, but also when you're answering this question, you can check your work, because if you get 9 states, you know that you're wrong because you know that the maximum number of states you could have in this case is 8. So having 9 states is impossible, so you know you did something wrong, you check your work, and find the right answer. NFAs can have what we call E-transitions, meaning you can have, let's say, a state Q0, an accepting state Q1, and let's say these are still our inputs. You can have a transition for 0 that goes to the state. You can have a transition for 1 that goes to the state, or not, because it's an NFA, you can do whatever. You can also simply have a transition that goes to another state without reading anything, without reading an input. So that's what we call the empty string, because you're reading literally nothing. That's something we can do. Those are called NFAs, which we, again, did not cover in this semester, but I just want you to be aware of that. At this point, we've covered grammar and we've covered finite state machines without output, so DFAs and NFAs. But why did we learn this skill? Why did we just spend so much time learning these skills? Because it helps us answer these questions. Why do we want to answer these questions? Well, let's go back to the big picture. At the end of the day, we're trying to answer the question, can a problem be solved using a computer? And as for what problems am I talking about, well, I'll give you an example. One problem is an even, is any number that you can think of even. Well, we said we could just plug n into an algorithm, like your friend can code up an algorithm where you plug in n. If n can be divided by 2, then it's even. Otherwise, it's not even, so you'll get an answer. Or, theoretically, we can think of a set that contains all possible even numbers in the world, and all we really have to do is find if n is in that set, because if it is in the set of all even numbers, then it is even. And so if the question is 2 even, so if n is 2, all I really have to do is ask myself, is 2 in this set of even numbers? And yes, it is. And so we managed to do this by hand, but how can we automate this? Well, the first question is, how do I get all of these numbers in this set? These numbers are elements of this set. So really, we're trying to answer the question, how do we generate all elements in a set? And the answer to that was using grammar. So we spent time learning grammar. Then the second question comes up, once we have the elements of the set, how do I check if something is an element of that set? In other words, how do we recognize that an element, like 2, is inside of a set? And the answer to that was using finite state machines without output. So we spent some time learning that skill. So now that we have these two skills, let's try to put everything together by designing a grammar that will generate all of the elements in the set of all even numbers, in other words, generating all even numbers and putting them in a set, and designing a finite state machine or a finite state automata without output, so either a DFA or an NFA, that will recognize if a number is inside that set of all even numbers. We're told to design a grammar that will generate all even numbers as its language. So we know that a grammar is made up of an alphabet B, which holds all symbols we're going to use, T, which is a set of terminal symbols, and this holds all of the symbols we're going to end up with at the end of the day in all of our strings. So terminal for end. These are the ones we're going to see in our strings at the end of the day. Then S is our starting symbol, and P is a set of productions or rules to help us generate the strings. In this case, the strings are numbers, all even numbers. So I always like to start with, what do I want to see at the end of the day? So that's my terminal set. Well, at the end of the day, all of my numbers, even though they're even, 2 is even, 284 is even, 68 is even, they're made up of the digits 0 to 9. So therefore, at the end of the day, all of my symbols are going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 9. Then my vocabulary or my alphabet is going to contain all of the symbols in my terminal set, so right here, because remember that T is a subset of V. So everything in T is going to be in V, which is why all of these elements that are in T are also in V. And then our starting symbol is going to be S. And actually it could be any letter you want. It's just convention that you use S for start. Remember that we always have to start somewhere. So S for start, but remember also that this is just a tool to get started. It's not something that we want as a digit in our even number at the end of the day. First of all, it's a letter, not even a digit. So it shouldn't be here. Like, this is not a number. So we don't want this S to be in the set of terminal symbols of all of the symbols that we're going to end up with. So we don't want it to be part of T, but we are using it at some point, so it has to be part of the set of all of the symbols we ever use at some point, which is V. That's why we have it here. And we cannot start with a terminal symbol, so we need another symbol, and that is S. Now for our productions, that's a set of rules that we use to go from our starting symbol to someplace else. Our goal is to have an even number here. So the most basic production we can have is have S either be 0, 2, 4, 6, or 8, because those are all of the even numbers between 0 to 9. So our first production or first rule could be that S can go to either 0, S can go to 2, S can go to 4, and so on, but instead of writing this 5,000 times, we can just use the OR symbol, so 0, or 2, or 4, or 6, or 8. So at the end of the day, S can either be those numbers. But the problem is 0, 2, 4, 6, and 8 are not the only even numbers. We're trying to generate all even numbers. But right now, our production says that S can only go to these numbers right here. But note that 284 and numbers like 192 are even numbers because they end with even digits, and yet with the rules that we have so far, we can't generate these numbers. Right now we can only generate 0 or 2 or 4 or 6 or 8. So if I want to generate 192, notice that I'll have to generate odd numbers, and right now I can only go from S to an even number. So if I want to go from S to 1, well then I need a rule that says I can go from S to 1. So then I could say, okay, from S, I can go to 1. But then the problem here is 1 is a terminal symbol. It's a symbol that we can end with. You see 1 right here. So what this is telling me, I can end here, but that's a problem because this grammar is supposed to only generate even numbers, and just having 1 is not an even number. Meaning we cannot allow the grammar to end here. So we have to force a non-terminal symbol, like S. Because S is non-terminal, it's not in the terminal set, meaning we can't end with it. We're forced to keep going, and that allows us to never stop at 1. So a rule should really be 1S. So now that I can go from S to 1S, if I want to generate the number 192, well, I need 9 next. So from S, I want to be able to go to 9, so I have to add that rule. From S, I want to go to 9. But again, I collect 1, I collect 9, so far I have 19. 19 is not an even number. I can't end here. So you have to force a non-terminal symbol so that you're forced to keep going because you can't end with a non-terminal, a non-ending symbol. So the rule shouldn't be S goes to 9, it should be S goes to 9S. And so notice the pattern that anytime you have an odd number, you can't just have the odd number. You have to put a non-terminal symbol next to it so you're forced to keep going and not end with an odd number because your goal is to generate even numbers. So we should have S goes to 3S. S goes to 5S, S goes to 7S. Anytime we have an odd number, we can't end with it. We have to put a non-terminal symbol, in this case S, that will force us to keep going. That will make sure we never end with that odd number. And then finally, to finish it off, we want a 2, and we already have a rule that says S can go to 2. So S goes to 2, and we collected the number 192, and that is even. What if I want to generate the number 1922? Well, the first symbol I want to generate is a 1. The only rule that allows me to generate any type of 1 is S goes to 1S. So S goes to 1S. I can't end here because this is a non-terminal symbol, a symbol I can't end with because it's not in the terminal set. So I have to keep going. So far I've collected 1, but I want 9 next. Is there a rule that generates a 9 from S? Well, yeah, from S I can go to 9S. So there we go. Now I have a 9. Can't end here because it's a non-terminal symbol. I have to keep going. The next number I want is a 2, and there's a rule that says I can go from S to 2. Great, so I've collected a 2 now. And so far I have the number 192. But the question is, how can I get this last 2? Note that the only time we can ever keep going is if there's a non-terminal symbol. But right now, there isn't a non-terminal symbol, and because there's no non-terminal symbol, we can't use any of the rules to get somewhere else, because in context-free languages, the rules only tell you how to go from a non-terminal symbol to something else. It's never going to say from 2 we can go somewhere else because 2 is a terminal symbol. It will only tell you, hey, from non-terminal symbols like S, we can go someplace else. So really what we want here is an S. We want that non-terminal symbol because that forces us to keep going. So what you have to realize is, not only did we want a non-terminal symbols next to the odd numbers because we don't want to end at these odd numbers, but we also want a non-terminal symbols next to the even numbers because sometimes we don't want to end with just that even number. We want to have another even number after that. Because if we had an S here, then we can say, okay, we can't end there, and I want a 2. Is there a rule that gives me just 2? Yeah, S goes to 2, so I could have 2 here, and then I would be done. So to conclude, we want the option to keep going even if we already have an even number. Just because we encounter an even number doesn't mean we want to end. Just because I see this 2 doesn't mean I want to end. Sometimes I want to keep going. So to add to our production, we can say S can go to 0S, or 2S, or 4S, or 6S, or 8S. And since these rules are very similar to each other, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we can put it all in one line to keep it clean. We managed to design a grammar that will generate all even numbers as its language. Now let's design a finite state machine that will recognize all of the even numbers that you input. So if you input an even number W into the machine, it will either recognize it / accept it if that number is in the language of the machine, or it will reject it if that number is not in the language of the machine. So this machine, this finite state machine, should see if n, or w in this case, or n, whatever you want to call it, is in a set of all even numbers. That is the language of the machine. So how can we do that? Well, I always like to start by just drawing the state diagram and then translating that into the formal description later. But the whole idea is, let's say I have a state Q0. I know even numbers have to end with an even digit. So I'll have another state, let's call it Q1, and have this be my accepting state. And the only way I can go from my starting state, let's say it's Q0, to Q1, which is my accepting state, is if I have an even number. So that would be 0, 2, 4, 6, 8. Otherwise, if I have 1, 3, 5, 7, or 9, I stay in the same spot. But let's say I start and I only put in the number 2, but I don't want to end with the number 2. Let's say I want to do the number 234. If at this point I need to read in a 3, well then I can't stay here because this is the accepting state, and the accepting state will only recognize even numbers, those that end with even digits. So I would have to go back to the starting state. So I would do a transition here so that if I want to read 1, 3, 5, 7, or 9, it will go back to the starting state, and the only way I can go back to the accepting state is if I read in an even number. But if I happen to have the number 22, I start here, I read in a 2, so I go this way, and I want to read another 2, well that's fine, I can stay in this state because this is still an even number. This is an even digit. So I would loop back over here if I read 0, 2, 4, 6, or 8, if I read in any even digit. And so I managed to create a DFA. Why? Because every state has exactly one arrow, one transition for each of its input symbols. This state has exactly one arrow for each of its input symbols. So now I have to give a formal description of this machine. Remember that a machine consists of Q, which is a set of all states, the alphabet or the set of all input symbols, the transition function, the starting state Q0, and the set of final states F. So Q is a set of all states, so every state is a circle, so Q0 and Q1. These are my states. My alphabet, sigma, is the set of all input symbols, so those are all of the numbers you see on top of the lines, the transition lines. All unique numbers, so I see 0, 2, 4, 6, 8, and I see 1, 3, 5, 7, 9. So basically all of the digits from 0 to 9, I'm just going to do 0 to 9 like that, little shortcut. Q0 is my starting state, the arrow tells me that's Q0, and F is a set of my final states, but I only have one final state, which is Q1. And then my transition function delta, again, the table has one column for each of the inputs that you have. So we can do 0, 1, 2, 3, blah, but I'm just going to do, let me zoom in here, 0, 2, 4, 6, 8, and on this side I'll do 1, 3, 5, 7, 9 as a shortcut. And then over here you put all your states, so that's Q0 and Q1. You define that Q0 is your starting state, Q1 is your final state with a little star. And then to fill in the table, just read a state diagram. What does it say? It says if you're at state Q0 and you're reading either 0, 2, 4, 6, 8, then you go to state Q1. So you write that. If you're at state Q0 and you're reading 1, 3, 5, 7, 9, then you stay at Q0. If you're at state Q1 and you're reading in 0, 2, 4, 6, 8, then you stay at Q1. And if you're at state Q1 and you're reading in 1, 3, 5, 7, 9, you go to state Q0. And that's it. That's your transition table. This is the formal description for the finite state machine that recognizes all even numbers. And we can test it. Let's say that the number is 552. This is an even number because it ends with an even digit. So this machine should accept this number. So we always start with the starting state. I'm reading in a 5. So if I read in a 5, I stay at the starting state. Then I'm reading in another 5. I read in another 5, I stay where I'm at. But finally, I read in a 2. So if I read in a 2, I go to state Q1, which is an accepting state. I'm done reading the entire string, because this is a string, even though it's a number. So once I'm done reading the string, I have nothing else to read. So I ended in the accepting state, in the final state. So therefore, this machine accepts this number, which it should because it's an even number, and this machine should accept all even numbers. Now, what if I did the number 55? Well, I start at my starting state. I'm reading in a 5. If I read in a 5, I stay at the starting state. I'm at the starting state. I read in another 5. If I read another 5, I stay at the starting state. I'm done reading every single symbol. There's no more symbols in this string. So because I'm done reading the string and I'm not on an accepting state, then this machine does not accept the string, which it shouldn't because it's an odd number, and this machine only accepts even numbers. We have one more thing to cover in terms of finite state machines. So far, we've been talking about finite state machines without output, and these machines have been DFAs and NFAs. What do I mean without output? Well, when we have a state, all we really care about is what's the next state given a certain input, whether it's 0 or it's 1. What's the next state? Where are we going next? if we stop reading inputs, is that state an accepting state or not? But there's a whole other category, which is finite state machines with output, meaning instead of going from one state to another just by reading an input, not only do we read in an input, but we get an output. Sometimes you'll see a slash or sometimes you'll see a comma. So this would be input, this would be the output. But it depends on which machine you're talking about. There's two, so there's a Mealy machine and there's a Moore machine. The difference between these two is that the output for Mealy machines depend on the current state and the current input, while the output for the Moore machine depend only on the current state. We focus more on Mealy machines in Garcia's class, but this is more apparent with a visual example. This is a state diagram for a Mealy machine. Notice how on top of our transitions, we don't just have one number that stands for, oh, if we're at state 0 and we read in a 0, then we go to state 1. No. This says if we're at state 0, we read in a 0, we go to state 1, but the output is 1. So now we have input, output, and they're separated by a comma, or sometimes you could do a slash, so 0/1, that's fine. Whereas in a Moore machine, the output only depends on the current state. So you know that the state diagram represents a Mealy machine because you see your outputs on top of the transitions, on top of the arrows. And you know that this state diagram represents a Moore machine because your output only depends on the current state, and so your outputs are literally only on the states. 1 is the output of state 0, 1 is the output of state 1, and 0 is the output of state 2. It does not depend on the transitions. Now here's a big question. Why didn't I talk about these finite state machines when I introduced these? Because these had nothing to do with the problem we introduced in the beginning, which was, can we find something that is able to recognize any string, any element in a set? That something was a finite state machine, but only finite state machines that can actually accept or reject an element. That's the whole goal. These machines can't accept or reject anything. They just care about output. So DFAs and NFAs have accepting states. Mealy and Moore machines do not have accepting states. We just care about what's the output that we're getting. So these machines were more useful in terms of using them to take in a string W, here's the machine, and then either accepting or rejecting, accepts if W was in fact in the language of the machine, or it rejects if W was not in the language of the machine. That's what these machines did. Because they have accepting states, they are useful to determine whether something is in a set in the language of the machine or not. But if you notice, these machines, they have a starting state as 0, but they don't have accepting states. You don't see any double circles because, again, Mealy and Moore only care about outputs. And I didn't want to ruin the flow of the lesson because these really have nothing to do with answering the question from the beginning, so I'm introducing them to you now. So if we go back to answering this question, how do we recognize that an element is inside of a set? When we said finite state machines, I really meant finite state machines without output, so DFAs and NFAs, because, again, Mealy and Moore are not useful to answer this question since they don't have accepting states. They don't have final states where you can use to accept or reject an element, let's call it W, inside a set. So that's the idea. Now let's talk about the formal definition of these machines, and then we'll practice some questions. The formal definition of a machine with outputs, so both Mealy and Moore, consists of Q, which is a set of all states, sigma, which is a set of all input symbols, we also call sigma the alphabet, delta, which is a transition function for the next state, so depending on your current state, whatever your input is, that's going to give you your next state, U sub 0, which is your starting state, O, also known as lambda, is a set of all output symbols, and G is your output function. So if you have a Mealy machine, your output depends on the current state and the input. We discussed that here, current state and input. If you have a Moore machine, your output depends on just the current state that you are in. So that's really the only difference between Mealy and Moore in terms of a formal description, and we already discussed the differences graphically. So let's go ahead and practice. So this is Mealy stuff, this is Moore stuff. We're told to draw the state diagram for the finite state machine given the state table, so this is the state table, also called transition table, and find the output generated from the input string, this right here, using the state table. So not the state diagram, but we'll do both. So I like to start with my states. I have 4 states, so I'm going to have 4 circles. Then I'll label my states. The starting state, they don't have an arrow to define what the starting state is, but if they don't give it to you, you can just assume it's the first one, so S sub 0. And as for the final states, again, there are no final states, no accepting states in Mealy and Moore machines, finite state machines with outputs, because all we care about are outputs, not whether something you input is accepted or not. And now we just read, if we're at state S0 and we input a 0, then we go to state S1. So if we read in a 0, we go to state S1, but when we read in a 0, our output is 0 as well. So we could do 0, 0 or 0/0. I'm just going to do comma for now. If we're at state S0 right here, but we read in a 1, 1, we go to state S0. So we stay at state S0 if we read in a 1. But if we're at state S0 and we read in a 1, that's our input, our output is 0. So we also have to write that down. Now, if we're at state 1 and we read in a 0, where do we go? State 2. So if we're at state 1 and we read in a 0, we go to state 2. But we also have to consider the output when we're at state 1 and we're reading in a 0. What's the output? It's 1. So we do 0, 1. So again, these represent the inputs, the first values, and the second values represent the outputs. Now, if we're at state 1 and we read in a 1, we go to state 0. So we go back over here. If we read in a 1, we go to state 0, but what's the output? Well, when we're at state 1, the output, G, when we read in a 1, is right here, 1. So 1, 1. I'm actually going to write it up here. Now, when we're at state 2 and our input is 0, the next state is state 0. So from state 2 and our input is 0, the next state is S0. But then when we're at state 2, our output, G, when our input is 0, is 0. So we put 0, 0. Now, when we're at state 2 and we read 1 as our input, we go to state 3. So we're at state 2 and we read in 1, we go to state 3. But then what's our output? Well, when we're at state 2, our output, when our input is 1, take the intersection of these two lines, is 1. So we put a 1 here. And finally, when we're at state 3 and our input is 0, take the intersection of these two lines, we go to state S1. So state 3, our input is 0. I'm going to put it right here. We go to state 1. But then what's our output when we're at state 3? Our output, when our input is 0, take the intersection between these two lines, is 1. So 0, 1 right here. And finally, when we're at state 3 and our input is 1, take the intersection between these two lines, our next state is state 2. So we go right back over here when our input is 1, but then what's our output? When we're at state 3, our output, when our input is 1, take the intersection between these two lines, is 0. So we put a 0 in here. And that is the state diagram for our Mealy machine. Now we're told to find the output generated from this input string. So really it's a string. So if we input this, what's going to be our output? Let's go ahead and zoom in here. They're telling us to use a state table, so we'll do that. If we start at state 0 and we read in a 0, our next state is state S1, but our output is 0. So we're at 0 and we're at state S1. So now we're at state S1 and we're reading in a 1. So if we're reading in a 1, our next state is S0 and our output is 1. So our output is 1, our next state is S0. So now we're at S0 and we're reading in another 1. Well, if we read in a 1, our next state is S0, so we stay at S0. But our output when we read in a 1 is 0. So this output's 0. So we use this and this. Now we're at state 0 and we're reading in another 1. So if we're at state 0 and we read in a 1, next state is still at 0, output is still 0. So there's another 0, still a 0. And finally, we're at state S0 and we're reading in a 0. So if we read in a 0, our next state is S1, but if we read in a 0, our output is 0. So our output is 0. We don't really care about our next state. We got our output when we read in 0, 1, 0, it's 0, 1000. That's our output using a state table. But let's also use the state diagram. I start at S0, I read in a 0. So if I read in a 0, that means I go to state 1. My output is 0. So I'm collecting this 0. So this is done. Then I'm here in state 1 and I'm reading in a 1. So if I read in a 1, I'm back at state 0, but the output was 1, so I'm going to collect this 1 now. Read this. Now I'm here, and I'm reading in another 1. If I read in a 1 as my input, I stay here, but my output was 0. So I'm going to collect this 0, add that to my output. Then I read in another 1, but I'm here. If I read in a 1, that takes me right back to here, but I get to collect this 0 again, so that's another 0. I read this one. And finally, I'm still here, but this time I read in a 0. So if I read in a 0, that takes me to state 1, but the output I get to collect again is 0. So I'm at state 1, that's where I left off after reading this entire string right here, and the output that I got after reading this entire string was 0, 1000. Let's try this one now. Give the state table or the transition table for the finite state machine below and find the output string generated by the machine. I had a typo earlier. When you input 0, 1, 1, 1. So this is a Mealy machine because the transitions, on top of the transitions, you have the input and the output. It would be a Moore if inside the states or right next to the states, you had the outputs for those states. So if they want a state table, I know that on this side, it's always the states. So I have 1, 2, 3, 4 states, S0, S1, S2, S3. And then you have two things you care about, the next state, and you also care about what the outputs are. And those both depend on your inputs. So 0, 1, and 1. Here we'll talk about the next states. Here we'll talk about the outputs. So if we're at state S0, we do an arrow to say, hey, we start here. And we read in a 0. If we read in a 0, our next state is state S1. If we're at state S0 and we read in a 1, well, if we read in a 1, our next state is state S2. If we're at state S0, we read in a 0, what's our output is 1. If we're at state S0 and we read in a 1, so if we read in a 1, what's my output? It's 0. If I'm at state S1 and I'm reading in a 0, if I read in a 0, that means I go back to state 0. If I'm at state 1 and I read in a 1, well, if I read in a 1, I go to state 3. Now, what are the outputs? Well, when I'm at state 1 and I'm reading in a 0, so I'm not saying that these are my outputs and these are my next states. These are my inputs here. I'm saying these are my outputs, these are my next states. So if I'm at state 1 and my input is 0, so I'm reading in a 0, my output is 1. If I'm at state 1 and I'm reading in a 1, yeah, my next state is state S3, but my output is 0. If I'm at state 2 and I'm reading in a 0, if I read in a 0, I go to state 3 and my output is 0. If I go to state 3 and my output is 0. If I'm at state 2, I read in a 1, I go to state 0 and my output is 0. So state 0 and my output is 0. If I'm at state 3 and I'm reading in a 0, I read in a 0, I go to state 1 and my output is 1. State 1 and my output is 1. So you're just putting it in the same position. And finally, when I'm at state 3 and I'm reading in a 1, if I read in a 1, I go to state 2 and my output is the number right next to it, it's 1. And that's my state table or my transition table for this Mealy machine. Now, they're asking us find the output string generated by the machine when you input 0, 111. Okay, let's do it with the state diagram. Let me zoom in here. I start on this state. I'm reading in a 0, so if I read in a 0, I'm at state 1 now, and my output is 1. So far, we have 1. I'm done reading this number. I'm at state 1, and I read in a 1. If I read in a 1, I go to state 3, and my output is 0. So I've collected a 0. And I read this one. Now I'm at state 3 and I'm reading in another 1. So if I read in another 1, I'm at state 2. My output is 1, however, so I collected a 1. I'm done with this one. And finally, I'm at state 2 and I'm reading in this one right here. So if I read in a 1, it tells me go to state 0 and my output is 0. So I've collected 0. I'm done reading this in. Output is 10, 10. And that's our answer. Finally, let's answer this question. We're told to construct a state table for the Moore machine below. How do I know it's Moore? They don't have to tell me, because if I zoom in here, I see that the outputs are either inside or right near the states. And I know that outputs depend on the states only when it's a Moore machine. I like to remember it, by the way. Let's go back here. I like to think more is less. So the Moore machine depends on less things. So it depends on only the current state. Well, the Mealy machine depends on both things, current state and input. So more is less, depends on less things. Again, the state table, we know that on this side, it's just the states. I have 3 states, S0, 1, and 2. So I'll write S0, S1, S2. These are the states. So I've done the same thing here. These are the states. And now the output is easy. Output is G. Just find what the output is for each state. For state 0, the output is 1. For state 1, the output is 1. For state 2, the output is 0. And then to find the next states, depending on what the input is, either 0 or 1, just read the diagram. If we're at state 0 and we read in a 0, we go to state 1. So we write state 1 here. If we're at state 0 and we read in a 1, that tells us we go to state 2. Now if we're at state 1 and we're reading in a 0, if we read in a 0, we stay at state 1, so that's state 1. If we're at state 1 and we read in a 1, if we read in a 1, that tells us, hey, go to state 0. And we're at state 2 and we read in a 0. If we read in a 0, we go to state 1. We write state 1. And finally, if we're at state 2 and we read in a 1, well, if we read in a 1, we stay at state 2. And that is our transition table or state table for the Moore machine. Notice how there's one output that corresponds for each of the states. So each state has its own output. The output depends only on the state, where here in a Mealy machine, the output, G, so these are all of the G values, they depend on whether the input is 0 or 1. So it depends on the input and the current state, right? Because the input could be different here depending on whatever state you are. So it depends on whatever the input is and the current state. Now at this point, we've covered finite state machines without output and with output, but I want to go back to finite state machines without output, DFAs and NFAs, because we have some vocabulary to talk about. So let's get started. All languages accepted by a DFA or an NFA are called regular languages. And here's a fun fact, we can operate on these regular languages, because what are languages if not sets? And after all, we know how to operate on sets. Now going back to this point, a language is a set, but specifically it's a set of strings. And intuitively you can think of the English language. What is the English language if not a collection, a set of all of the strings of all of the words that make up the English language, like a, be, cat, word, and so on. In what we've been working so far, the language of a machine is just also a set of strings that the machine accepts, like 0 or 1. So we're saying if you can construct a machine, either a DFA or an NFA, that recognizes this language, in other words, that recognizes or only accepts strings that are either 0 or 1, then we call this language a regular language. And we can operate on that regular language. We can operate on the set that just consists of 0 and 1 as strings. And not only can we operate on a single language, but we can operate on multiple languages. Let's call it L1, L2, L3. And by performing operations on these languages, we'll get another language. We'll get another set. Let's call it L0. And that will be a regular language also. Because if what you're operating on are all regular languages, then your result will also be a regular language. For example, consider the regular languages L1, which consists of the set containing 0 as a string, and L2, which consists of the set containing 1 as a string. But again, you don't have to actually write the quotation marks. And this is over the alphabet 0, 1. This just means that these languages, L1 and L2, are made up of strings that only use 0 and 1 as the symbols. So this is a string, it only uses 0. This is a string, it only uses 1. We could have had another language, L3, that could have been the set containing the string 0, 1, 1, and that would also follow the rule that all of the strings in this language, in this case there's only one string, are made up of only the symbols 0 and 1. So you don't see something like 0, 1, 1A, because A is not part of the alphabet, it's not part of all the symbols that make up these strings in the languages. The first operation is the union, which we're very familiar with from set theory. You're just putting all of the strings in L1 and L2 together in one set. So if you have the union of L1 and L2, that's going to be the set containing all of the elements from L1, which is just 0, and all of the elements from L2, which is just 1. You're just putting all of the elements in both sets together. Now if L2 was the set containing 1, 0, then the union of L1 and L2 would be all of the elements from L1, which would be 0, and then all of the elements from L2, which would be 1 and 0. So you would add 1, but because 0 is already here, you don't want to add it again, because remember, the definition of sets say that all of the elements in a set are supposed to be unique. You can't have them repeat, so I can't have 0 again. The second operation is what we call concatenation. It's where you have all of the possible strings you can create by taking a string from L1 directly followed by a string from L2. For example, if I'm asking you to concatenate L1 and L2, it's basically the same process as the Cartesian product. You want to take the first set, which is L1, which is just this set, put it here at the top. Then you take the second set, which is L2, and you put it here at the bottom. And then for every element in the first set, you want to pair with every element in the second set. So in this case, we just have 0 paired with 1. So L1 concatenated with L2 is going to be 0 paired with 1. So we're not doing tuples, we're not doing commas like we do with the regular Cartesian product. You just pair the symbols together. And to give you a better example, let's say that L1 was 0, 1, and L2 was 2, 3. If you want to find L1 concatenated with L2, then you put L1, which is this set at the top, 0, 1. Then you put L2, which is this set, 2, 3. And so then L1 concatenated with L2 is going to be 0 paired with 2, 0 paired with 3. Then you move on to the next, 1 paired with 2, and then 1 paired with 3. If I want to find L1 concatenated with L1, well, you take L1, which is this set, and then you take L1 again, which is this set. And for every element in this set, you pair it with every element in this set. But since there's only one element, it's just going to be 0 paired with 0. So you'll have 0 paired with 0. If I want to find L2 concatenated with L2, then you take L2, which is just this set, and then you take L2 again, which is just that set, and you pair 1 with 1. So you have 1 paired with 1. If I want to find L2 concatenated with L1, then I take L2, which is this set at the top, and then I'll take L1, which is this set at the bottom, and then I'll pair every element on the top set with every element in the bottom set, and so we'll have 1 paired with 0 as one string. So this is string 1, 0. This is string 1, 1. This is string 0, 0. This is string 0, 1. So think of the Cartesian product process. And you can see how the first numbers in the string are all from L1. And by L1, I mean the first set. So the sets don't necessarily need to be called L1 and L2. It could have just been A and B. You would just have to know, okay, it's talking about one set and then another set. And so then they're directly followed by a string from L2. So these here, the second ones, are all from the second set. The next operation we have is called the clean start. This is an operation we can apply to only one set, not multiple sets. And so if we take set L1, for example, if we apply the clean star on it, what it's saying is, hey, find the set of all possible strings that you can create by using or not using the strings in that set. In this case, L1. If you recall, L1 is just a set containing 0 as a string. There's only one string. So what we mean is we want to find all of the possible strings that we can create by using 0, by using this string, or not. So the or not means, well, I can just create a string that doesn't use this string, so that would be the empty string. But I could use 0 once, or I could use it 2 times, or I could use it 3 times, or I could use it 4 times, or I could use it 5 times, and so on. And all of these here are strings that I've created by using the strings in this set, in L1. And you can see how this is not a finite set. It goes on forever because I could do 1, 2, 3, 4, 5, a billion zeros, and that's still a string that I created by using the strings in L. But what if instead of L1 being this, L1 was a set containing 2 and 3? Then L1 star would be the set of all the possible strings that I can create by using or not using the strings 2 and 3. So I could use none of them and have an empty string. I could use just 2 and create the string 2. I could use 3 and create the string 3. I could use both of them together and create 2, 3. I can use 2 times and then 3 one time. I could use 2 3 times and then 3 one time. I could use 2 a billion times and then 3 one time, or I could use 3 a billion times and then 2 one time. And you can see how this is infinite. Like, you could literally create any strings. So you can think of 2 and 3 as being your building blocks. Like if you're building Legos, you have an infinite supply of 2s and 3s and you can just use them over and over again as many times as you want. And so this says just basically all of the pieces that you can make by doing so. In this case, there was only one string, so this was our only Lego piece, but you have infinite supply of it, because you could use it as many times as you want. So you build this piece, then this piece, then this one. But you could also not use it and build nothing. Now this is the way you can intuitively think about clean star. But mathematically, if you apply clean star to a language, let's say it's L1, then clean star is actually defined as the union of the concatenation of all of the strings in L1. What do I mean by that? Well, to get this empty string, that means you had to use all of the strings in L1 0 times. See, you didn't use any of the strings here because you have nothing in there. And so we define this as L1 to the 0 power because we used all of the strings in L1 0 times. Now to get this string, that means I had to use all of the strings in L1 one time, because to get this 1, 0, I had to use the 0 one time. So we define that as L1 to the first power because we used the strings in L1 one time. To get this string, we had to use all of the strings in L1 2 times because I had to do 1, 0 and another 0. So this is L1 to the second power. And so then this would be L1 to the third power, this would be L1 to the fourth power, and this would be L1 to the fifth power, and then it would be L1 to the whatever power to the infinity, hence the L1 star. Now this is where everything connects. Remember in math class we learned that a squared is equal to a times a, so a together with a. So in the same way, we can write that L1 squared is equal to L1 together with L1. But that's interesting. What does this look like? Well, this looks like concatenation. And we know how to do concatenation. We take the first set, which is L1. It's a set containing 0, put it at the top. Then we take the second set, which is the same set. So we put that set at the bottom. For every element in this first set, we pair with every element in the bottom set, so there's only one element, it's just 0 paired with 0. So at the end of the day, 0 concatenated with 0, L1 concatenated with L1, which is L1 squared, is equal to the set containing 0, 0 as a string, which is what we have right here, 0. So L1 squared is not actually just the string 0, 0, it's actually the set containing the string 0, 0. Similarly for L1 to the third power, L1 to the third power is L1 concatenated with L1 concatenated with L1, so L1 3 times. We already know that L1 concatenated with L1 is L1 squared, and then we can drop this down. And then we already know that L1 squared is a set containing 0, 0 as a string, and L1 from over here we know is just set containing 0 as a string. And so we have to concatenate these two sets, so you take the first set, put at the top, second set, put at the bottom. Remember, these are strings here, so every element from the first set you want to pair with every element in the second set. There's only one element in the first set, so it's just 0, 0 paired with 0. So then at the end of the day, 1 cubed is the set containing 0, 0, 0. So at the end of the day, 0 concatenated with 0, L1 concatenated with L1, which is L1 squared, is equal to the set containing 0, 0 as a string, which is what we have right here, 0. So L1 squared is not actually just the string 0, 0, it's actually the set containing the string 0, 0. Similarly for L1 to the third power, L1 to the third power is L1 concatenated with L1 concatenated with L1, so L1 3 times. We already know that L1 concatenated with L1 is L1 squared, and then we can drop this down. And then we already know that L1 squared is a set containing 0, 0 as a string, and L1 from over here we know is just set containing 0 as a string. And so we have to concatenate these two sets. So you take the first set, put at the top, second set, put at the bottom. Remember, these are strings here. So every element from the first set, you want to pair with every element. The second set, there's only one element in the first set, so it's just 0, 0 paired with 0. So then at the end of the day, 1 cubed is the set containing 0, 0, 0 as a string. So L1 cubed is not the string 0, 0, 0. It's actually the set containing 0, 0, 0. So then the question is, well, if L1 cubed is the set containing 0, 0, 0, and L1 squared is the set containing 0, 0, so all of these are actually sets, then how did we end up with these not in sets? Well, we just took all of these sets, because that's what these are, and then we took the union of all of them, which means, hey, take all of the elements in this set, which is just the empty string, take all of the elements in this set, which is just this string, take all of the elements in this set, which is just this string, and put them all together in one set, which is what we call L1 star. Which is why I say that clean star on a language L is really the union of the concatenation of all of the strings in that language. Now, instead of L1 being the set containing 0 as a string, what if L1 was a set containing 0, 1 as a string instead? Well, then to find L1 star, well, you would follow this definition. We would first have to find L1 to the 0 power, which is just saying, hey, take all of the strings in L1 and use them 0 times. What string does that make? Well, that just makes the empty string, because you're using 0 and 1 0 times, so you just have nothing at the end of the day. Then we do union with L1 to the first power. That means take all of the strings in L1 and use them 1 time. What are the strings that gives you? Well, L1 to the first power is just L1, so it's this set right here. So that's just going to be the set containing 0, 1, and you see how you use 0 1 time and 1 1 time. Great. Then you do union L1 to the second power. So this means you're using all of the strings in L1 2 times. And you don't have to think about this again, because you could just do the math. L1 to the second power is just L1 with L1. That's concatenation. You take the first set, which is L1, we know is 0, 1. Take the second set, which is the same set, put it at the bottom. For every element in the first set, you pair with every element in the bottom set. So 0 paired with 0 is 0, 0. So now we have 0, 0 as a string. Then we have 0, 1 as a string. Then 1 paired with 0 is 1, 0 as a string. And then finally 1 paired with 1 is another string. So this set right here is equal to L1 squared. And then you can do the union, find L1 cubed and L1 to the 4th and L1 to the 5th, and continue on forever. So you can continue on forever. But at the end of the day, when we take the unions of these sets, we're just putting each and every single one of these elements into one huge set. So we take the empty string, that's one element. We take 0, we take 1, we take 0, 0, then we take 0, 1, then we take 1, 0, then we take 1, 1, and we keep on going forever. And this is what we end up with here. And you can see how it makes sense. Here we used all of the elements in L1 0 times to get the empty string. Here we used all of the elements in L1 1 time to get 0 and 1. Here we used all of the elements in L1 2 times, so 2, 2, 2, 2. Those are all of the ways we could use the elements in this set L1 2 times. You could either pair 0 with 0, 0 with 1, 1 with 0, or 1 with 1. And then it will just go on forever. And again, remember all of these are strings here. So string 0, 0, string 0, 1, string 1, 0, string 1, 1, and so on. And finally, we have parentheses. These are used to group these operations and control the order that they are applied. So we're going to look at L1 concatenated with L1 union L2, but with parentheses applied in different places. So in this case, we have L1 concatenated with L1 parenthesis union L2. Parentheses tell us, hey, do this first instead of doing this first. So this, we already know from here that it's the set containing 0, 0. And then we have union with the set L2, which we know is the set containing 1. And then at this point, it's a simple union. We know that means, hey, take all of the elements in this set and in this set, put them together in one big set. So this is the string 0, 0 that goes here. This is the string 1 that goes here. And that's it. Now, what if the parentheses weren't here, but instead they were here? And it's the exact same thing. We have L1 concatenated with L1 union L2. The only difference is that the parentheses are here, which tells you to do this operation first. But we can just put out what L1 is. L1 we know is a set containing 0. And then L1 union L2, we already know what that is because we did it up here. It's a set containing 0, 1. So these two sets are just next to each other, which means concatenation. So you take the first set, put it at the top, and you take the second set and put it at the bottom. And for every element in the top set, you pair with every element in the bottom set. And you put those pairs in a new set. So 0 paired with 0 is 0, 0, and then 0 paired with 1 is 0, 1. And again, notice how concatenation is kind of similar to the Cartesian product, where the first numbers of these strings are from the first set, and the second numbers of these strings are from the second set. So it's all of the possible strings we can create by taking a string from L1 from the first set, directly followed by a string from the second set. So those are the green ones right here. And so notice it's the exact same thing, the parentheses are just placed in different places, and that gives you different results. Now, if we remove the parentheses, we only had L1, L1 union L2, then these numbers tell you the order of precedence. So parentheses come first, then clean star, then concatenation, then union. So in this case, you would do concatenation first, L1 with L1, and then the union. So this union L2. But because parentheses come first, in this case, you did a union first instead of concatenation because I put parentheses around the union. So we've done two things so far. We've gotten used to working with languages in terms of sets, so in their set notation, but we've also covered operations that we can apply on these regular languages. Now, when I introduce finite state machines, one type of problem that they always give you is they give you a finite state machine and they ask you, is this string accepted by the machine? In other words, is this string recognized by the machine? In other words, in terms of sets, we're just asking, is the string that they give you, it could be A, B, is this string in the set of the language that machine recognizes? So is it in this set, for example? And it is, so you say yes. So what they can do is they can ask you that same thing, but instead of being given the actual machine, like the state diagram, they could just give you the set. But instead of giving you all of the strings in the set, and also instead of using set builder notation to describe the set, they'll just use set notation with these operations, and they'll ask you that question. So this is what it looks like. They could ask you to determine whether the string 0, 1, 0, 1 is in each of these sets. So each of these sets represent a language. So here is a language that contains the string 0 and the string 1. Is this string in the set? No, it's not. Because you see that 0 is an element of this language, 1 is an element of this language, but you don't see 0, 1, 0, 1 as an element of this language. But for here it's simple because they actually list out all of the strings of this language. But for part B it's a little different because they have 3 different sets, meaning 3 different languages. You're operating on these languages, and that's going to give you at the end of the day one language, in other words, one final set. So in this final set, what we need to determine is if this string is in that final set. In other words, by applying these operations, are we able to construct this string? If yes, then this string is in this set. If not, it's not. We can start by taking a look at this set, which contains the string 0, 1, 0, and clean star is being applied to it. We know that anytime clean star is applied to a set, again, this represents a language, so we can call it L, it's going to result in an infinite set. It's never going to end, because that set is just going to contain all of the possible strings we can create by using all of the strings in this set. There's only one string, but again, repetition is allowed, so you can use it 0 times, which gets you the empty string, or you could use it 1 time, which gets you 0, 1, 0, or you could use it 2 times, which gets you 0, 1, 0, 2 times, or you could use it 3 times, 0, 1, 0, 0, 1, 0, 0, 1, 0, or you could use it a billion times to build a string made up of a billion of these. And so you can see how it's infinite. So when they write this, that's a shorthand for this entire set. Because the set is infinite, we actually physically cannot sit here and write every single element of the set, every single string of the set, so they use this as a shorthand. But for the sake of understanding, let's keep going. Let's break it up part by part. So this set here is a set containing 0 as a string, and we're applying clean star on it too. We already did this here. L1 was actually the set containing 0, so you can think of this as L1, and we applied clean star to it. And again, it's just how many strings can we create using this string 0? Well, we can use it 0 times, so that gives us the empty string because we used none of the strings. Or we could use it 1 time, or we could use it 2 times, or we could use it 3 times, or we could use it 4 times to make a string, or 5 times, and so on. You could use it 6 times, 7 times, a billion times to make another string. And finally, this set, well, this is the set containing just a string 1. And so that's just the set containing just a string 1. So this here is the shorthand for this set, followed by this set, then followed by this set. So you could see why they don't actually write the sets and they just write this, right? So we applied these operations, but I bet you're forgetting something. These sets are next to each other. What happens when we have L1, L2, L3 just next to each other? Well, that's concatenation, right? L1, L2, L3. That's this operation right here. So if this is L1, this here, and this is L2, this here, then we have to concatenate those two first. This set comes first, so you put it at the top. This set comes second, so you put it at the bottom. It's already at the bottom. And we know that it's like the Cartesian product where you take every element at the top and you pair it with every element at the bottom. So if we consider this to be L1 and L2, so this is L1, L2 is equal to these sets, then L1 concatenated with L2 is going to be equal to the set containing this empty string paired with the empty string, so that's still an empty string. The empty string paired with 0, so that's 0. The empty string paired with 0, 0, so that's 0, 0. The empty string paired with 0, 0, 0, so that's 0, 0, 0. The empty string paired with this one, which is this one. The empty string paired with that one, which is that one. And then you move on to the next element. 0, 10 paired with the empty string is just 0, 10. 0, 10 paired with the 0 is 0, 10, 0. 0, 10 paired with 0, 0 is 0, 10, 0, 0. 0, 10 paired with 3 zeros is 0, 10, and then 3 zeros, right? So 0, 10 from here, the 3 zeros from there. And this goes on forever, not because concatenation goes on forever, but because the sets that you're concatenating are infinite sets. So there's infinite elements to pair up with infinite elements here at the bottom. But the point is, again, if this is L1 concatenated with L2, if this is L1 and L2, then now we have this set that we have to concatenate with this set. So let this be set L3, and so now I want L1, L2, L3, well that's just going to be adding set L3 here at the end. So now we're concatenating this set and this set. This is the set that goes first, so it goes on the top. This is a set that goes second, so it goes at the bottom. I'll just do this. So the concatenation of L1, L2, and L3, again, you take every element of the top set and pair it with every element in the bottom set. So we have the empty string paired with 1, that's just going to be 1, because you have nothing paired with 1, so nothing paired with 1 is just 1. Then you have 0 paired with 1, so that's 0, 1. Then you have 0, 0 paired with 1, so you have 0, 0, 1. Then you have 3 zeros paired with 1, so 3 zeros paired with 1. Then you have 4 zeros paired with 1, so 4 zeros paired with 1. Then you have 5 zeros paired with 1, so you have 5 zeros paired with 1. Then you have 0, 1, 0 paired with 1. So you have 0, 1, 0 paired with 1. And then you have 0, 100 paired with 1. So you have 0, 100 paired with 1. And this goes on forever. So at the end of the day, this here represents this set. And that's what they mean by this. When they're asking you to determine whether a string is in each of these sets, they're saying this is a set, but this is also a set. Even though you see 3 different sets, when you're operating on them, here we have clean star and then we have concatenation because they're directly next to each other. After you're done applying all the operations, you're left with one entire set, one final set. Same thing, all of these sets and all of those operations applied on them will result in one final set. So all of these are just one set, even though you see multiple sets. So at the end of the day, you just have to check that the string is in those final sets. But again, if this represents this one set, let's go back to the question. They asked us to determine whether this string 0101 is in this set, but again, this set represents this entire set. So they're really asking, is this string in this set? Well, it's not this one, it's not this one, it's not this one, or this one, or this one, or this one, but it is this one. This is string 0101, 0101. So we managed to find this string in this set, so the answer to this one is yes. Now, we didn't need to do all of this concatenation because the setup itself already shows us all of the pieces we can put together to construct a string. In this case, our goal is to see if we can construct the string 0101 by selecting a string from this set, followed by a string from this set, and finally followed by a string from this set. So if I start here, I have to select a string from this set. I can choose an empty string, I can choose a string 010, I can choose the string 0102 times, and so on. Which will I choose? Well, my goal is to construct the string 0101. So if I have the option to select 010, which is the first 3 symbols of my string that I want to construct, I'm going to choose that. So I'm going to choose 010. Then from this set, I can choose the empty string 002 times, 03 times. But notice that I already have 010. I'm missing a 1. So choosing 0 is not going to help. Choosing 00 is not going to help. This is not going to help, and so on. So maybe it's best if I choose nothing from this set. So far, I have 010. And finally, from this set, I have to choose a string from this set. The only string is 1. Is that going to help? Well, yeah, luckily for me, that's exactly the string that I need, so I'm going to choose 1. So I'm done with all of the sets I managed to create this string. Is this the string that I'm looking for? Yes, it's 0101. So I managed to find this string. But here's the thing. I only found 4 elements of this set. I only found 6 elements of this set. And the problem is, what if what I needed, which was 010 to start with, was the 5th element? What if it was the millionth element? Do I have time to sit down and find all of these elements up to the billionth element? No, I don't. Even if we went all the way over here, the string itself, 010, was the 7th element. What if it was the 9th element? What if it was the 10th? What if it was the billionth element? Do I have time to construct the entire set? No. So what do? Is there a quicker way to do this? And the answer to that is yes. Anytime you see the clean start applied on a set, you think, this is telling me I can use the strings in this set as many times as I want. So when you see the star, think as many times as I want. I can use the string 010 as many times as I want to create a string. And that's convenient because the first 3 characters of my string is 010. So if this is telling me I can use this string as many times as I want, including 0 times, or 1 time, or 2 times, or 3 times, or a billion times, then that's perfect because I decide I want to use it 1 time because I only need 1 of them. So 010, then it's directly followed by 0 as many times as I want. So far I have 010, I want a 1 next, I do not want a 0 next, but it's not required to have a 0 because as many times as you want includes 0 times, so I can just have 0 times and not include a 0 here. And move on to the next. It says that the string should be directly followed by a 1. There's no option here because there's no star, it's just a 1, so that 1 has to go here. So was I able to construct this string using these operations? Yes. So because of that, this string is inside the set. This third one says we can use 0 as many times as we want, which is great because I want a 0. So let me use it once. Then it says it should be directly followed by a 10. So 10, which is great because that's what I need. And then it says I can use 1 as many times as I want, which is great because I want 1. So I'll decide, hey, I'm going to use it 1 time. So I'll use the 1 time. Was I able to construct this string using these operations? Yes. So this string is indeed inside the set. For part D, it says our string has to start with 0. And already I know that this string is not in this set because it says that all of the strings created by these operations have to start with 0 and my string needs to start with 01. So this string is just not possible. So no. For part F, it says I can use 01 as many times as I want, which is great because I want a 01 to start with. So I'll decide I'll use it 1 time, so 01. And then it says directly followed by 01 as many times as I want. Again, well, I need another 01, so I'll do it another time. 1 more time, so that's 01. Was I able to create this string using these operations? Yes. So this string is indeed in this set. Now notice that this is repetitive because what it's really saying is, hey, you can use 01 as many times as you want. Okay, then I could use 01, used it 3 times. And then this is also saying, after you're done using it as many times as you want, you could do it again. Do 01 as many times as you want. Well then, okay, let's say I want to do it 2 times this time. Well then I did it 3 times the first time, 2 times the second time. That's 3 plus 2, that's 5 times. Well then I could have just done that in the first time. I could have just done 5 on the first time. 01, 01, 01. 1, 2, 3, 0, 1, 0, 1, 4, 5 the first time. So this here is repetitive. You don't need it. But nevertheless, these are your answers. Now that we're comfortable working with languages as sets, because that's what languages are, sets of strings, notice that even though this here is a shorthand for that long set that we had, mathematicians were like, yeah, this is still too much to write. So what they did is they came up with this new notation to describe a set of strings, and they called it regular expressions. In other words, instead of writing the set containing 0 star, they just say, okay, 0 is going to be the regular expression that denotes this set. So they'll replace this with 0 star. And then they'll say, okay, 1 will be the regular expression that denotes this set. So they'll replace this with 1. And then they'll say, okay, 010 is going to be the regular expression that denotes this set. So they'll say 010 and then parenthesis star, because the star is on this entire string, not just this 0. So then this here would be the regular expression for this. But I want to formally introduce regular expressions, so let's go ahead and do that. Again, a regular expression is a notation used to describe a set of strings. What else is just a set of strings? Languages. So we can describe regular languages with regular expressions. and there are some rules when it comes to regular expressions. Before that, we start by saying that R is a regular expression over the alphabet. All this means is that R is a regular expression over some set of symbols. For example, those set of symbols could be 0 and 1, meaning that the regular expression is only going to contain the symbols 0 and 1, and or the symbols of the operations that we introduced here, so the union symbol, the star symbol, and parentheses. The first rule is if you have a language containing no strings, then the regular expression that denotes this language is this right here. The second rule is if you have the language containing the empty string, then the regular expression that denotes this language is this symbol right here. And note that these here are the languages given the regular expression. So if you want to find the language of this regular expression, well, that is the empty language. If you want to find the language given this regular expression, well, then that would be the language with the empty string. The third rule says if W is an element of the alphabet, in other words, this could be a W, this could be a W because these are both elements of the alphabet, then W itself is a regular expression that denotes the set containing W, or the set containing the string W. So W is supposed to be an element of the alphabet. Here's the alphabet. Let's just pick one. Let's say it's 0. Well, if 0 is an element of the alphabet, then 0 itself is a regular expression that denotes the set containing 0, or the set containing the string 0. Same thing. That's why we can say that if we have a language that contains just the string 0, then the regular expression that denotes that language, because 0 is in the alphabet, would be 0 itself, this symbol right here. Similarly, if we have the language containing 1, so now W is 1, then 1 itself is a regular expression that denotes a set containing 1. So if I see this, the regular expression will be 1 itself, right here. So these are what we call the 3 rules, the 3 base cases. And you might be like, well, what if I have a language containing the string 0, 1? Can I say that 0, 1 is the regular expression that represents this language? Yes, but not because of this reason. This is true because this really translates to the language containing 0 as a string concatenated with the language containing 1 as a string. And then from there, we know that this is denoted by 0 because of this rule, and this language is denoted by 1 because of this rule, and so then we have 0, 1. Same thing if we had a language containing cat as a string, then yes, cat would be the regular expression for this language if C, A, and T were part of the alphabet, but not because of this reason. But because you have to recognize that the only way this could have happened is if you concatenated, if you put all of these symbols in the alphabet together like that. So that would have had to be the set containing C as a string, the set containing A, then the set containing T, one directly followed by another, which gives you the set containing cat. But then if you know that from here, this is really what it was, then using this rule, you could say, okay, well, we know that C denotes this set. We know that A denotes this set, this language, and we know that T denotes this language, and so then cat with C, A, and T all together is the regular expression for this set. And that's, of course, taking into consideration that the same operations we learned here, so union, concatenation, clean star, are the same operations we can use with regular expressions. Because the reason that cat denotes the language containing cat is only because of concatenation and the fact that we can use this rule. So again, these are base cases or base rules. So this rule here says if you have the set containing 0, of course, as long as 0 is part of the alphabet, then 0 itself is a regular expression that denotes that set containing 0 as a string. That's what this rule says. What this rule doesn't say is if you have the set containing cat as a string, that cat itself is a regular expression that denotes this set containing cat as a string. But regardless, this is true, even though it's not a base rule. And the reason why is because we prove it to be true by induction. And I actually kind of just informally proved it to you just now by using concatenation and this base rule. So the idea is the proof by induction, if you use this base rule and concatenation, you'll prove this same rule, but you just add a little star right here, the clean star. Star means take every element in this set, which is just 0 and 1, and use it as many times as you want to create all of the possible strings that you can create. So sigma star is essentially all of the strings that you can create by using or not using these strings. So I can use them 0 times, so I get the empty string. I can use them both 1 time, so I get 0, 1. I can use them both 2 times, so I get 0, 0, and then 1, 1. I can use them 2 times different ways. I could do 0, 1, 0, 1, and so on. In other words, sigma star are all of the strings that you can create by using the symbols in sigma. A better example would be using the literal alphabet. Instead of 0 and 1, what if sigma was A through Z? The literal alphabet, that's why we call it the alphabet. And so sigma star will be all of the strings that we can create using the symbols. In other words, all of the possible words in the English language. It could be A, it could be the empty string, it could be I, well, lowercase I because it's all lowercase, and it could be cat, and so on. And so we're saying if W is an element of sigma star, so we're saying any of these, we can call them W, then W itself, so if W is cat, we could say cat itself is a regular expression that denotes the set containing cat. So if I see cat, then yes, cat itself is a regular expression that denotes the set containing cat. And that's because of this rule here, this theorem that can be proven by induction. But it's not a base rule. You build up to it. This here without the star is the base rule. So keep that in mind. Now, what if we had these two sets together? What's the regular expression that denotes this? Well, we already know that this set here is denoted by 0, so we can replace that with a 0. And we already know that this set is denoted by a 1, so we can replace that with a 1. And so the regular expression would be 0 and 1 together. What if we had the set containing the string 0, 1? What's the regular expression that would denote that set or that language? Well, you would have to realize this is not what I like to call atomic. It's not like a set with a single string that contains only one symbol from the alphabet. It's actually a set with a single string that contains 2 symbols from the alphabet. And so our base rules don't cover this. And so that means we have to use some base rule along with an operation. And we have to realize, well, how could we have gotten here? Well, to get 0 and 1 together as a string, I would have had to have 0 concatenated with 1. Because the concatenation works where you put the first set at the top, put the second set at the bottom, and for every element in the first set, you pair with every element in the bottom set because there's only one element. It's 0 paired with 1, so you get 0 paired with 1 as one string, and that is this set concatenated with this set. So if we think of this as L1 and L2, L1, L2 concatenated with each other is just a set containing 0, 1 as a string. So great, we know that from here, that's how we get here, but then if we know that these are equivalent, since we were able to break things up to what I like to call the most atomic parts, we can use this rule that says if we have a set, we have a language that contains a string that only contains one of the symbols, one of the elements from the alphabet, then that very element is the regular expression that denotes that set, that language. So 0 denotes this set, 1 denotes this set, so we have 0 together with 1 is the regular expression that denotes this set, this language. What if we had the set containing 0, 1? Well, you have to remember that it starts atomic. So the question is, how did we go from this to this here? Well, notice that we have the element from this set together with the element from this set in one entire set. And that sounds like what operation? Union. Because if you take the union of these two sets, that just says, hey, put all the elements in a union, put them all together in one set. So 0 in one set, and then 1 in that same set. So now we know that these two are equivalent. We could forget about this and say, okay, we've broken it down to its atomic parts. I can use this rule that says 0 denotes this set, 1 denotes this set, and then I have the union. So then the regular expression that denotes this set is the union of 0 and 1. What if we had the set containing 0 as a string and then clean star applied to it? Well, this is atomic. This is just one set containing one string that contains exactly one symbol from the alphabet. So we could use that exact symbol from the alphabet to denote that set. In that case, that is 0. And then we could just apply the star to it. And so the regular expression that denotes this set here is 0 star. And if it was 1, it would be 1 star. If it was A, that would be incorrect because A is not part of the alphabet. Okay. Now we're going to take the same sets that we worked on over here and we're going to rewrite them using regular expressions because right now they're just in set notation. So we already did part A over here. We know that's 0 union 1. For part B, we have the set containing 0, 1, 0. Again, because of concatenation and the use of this rule together, the regular expression that denotes this set here is just 0, 1, 0 itself. So it's 0, 1, 0, then you can apply the star to it, but note that if you apply the star like this, the star is only applying to this 0 right here, and it's supposed to apply to 0, 1, 0. So what do? We use the parentheses operation that we learned, and we put parentheses here. And then we know using this rule, because 0 is in the alphabet, then we can use 0 to denote this set. So it's going to be 0 and then apply the star. And then because 1 is in the alphabet, we can use 1 to denote that set. And then this here is the regular expression for this. Now going a little bit faster, 0 denotes this set and then apply the star. 1, 0 denotes this set, and then 1 denotes this set, and then we apply the star. Do we put parentheses here? You can. It doesn't make a difference because it's not like you have a star here. And finally, 0, 0 represents this set. Then we have 0 represents that set, apply the star. Then we have 0, 1 representing that set. So this is the regular expression denoting this. Now, I do want to reiterate that the same operations we learned for the languages are the same operations we use for regular expressions, but instead of using the union symbol when it comes to regular expressions, we actually use this line, which means or. So I should change this one to be like this. So union we use with languages, this symbol we use with regular expressions, it means or. So what I like to do personally is kind of use this because that's what I'm used to all the way until the end, and then just anytime I see this, I replace it with this symbol like I just did. At this point, I wanted to give you an application of regular expressions. So one way you can use regular expressions is to answer the question, what is the language accepted by a given machine? And we actually did answer this question in the finite state machine part of the series. I gave you a machine, either a DFA or an NFA, and I asked you, what is the language accepted by this machine? And we talked about how there were different ways we could answer that question. We could either list the strings in the language that the machine accepts. If there's way too many strings, infinite amount of strings that the machine accepts, then we can describe that set using set builder notation. Or we can just use words. We could use plain English to describe all of the strings that the machine accepts, like, for example, all strings that end with 1, or all strings that end with 0, or all strings that contain 0, 1 as a substring. And finally, using regular expressions. But back then, you had no idea what regular expressions were, but now you do. So let's go ahead and zoom in here and try out this question one more time. So here we're told to describe the language of the machine below. We're given the machine. A great place to start is by reading in the input symbols. So in this case, it's just 0 and 1, meaning that the alphabet contains 0 and 1 because the alphabet is the set of input symbols. And what you want to do is input the symbols themselves as strings and see if the machine accepts those. So you could start there, start small. So let's say I want to input 0 first. If I input 0 as a string, well, I start here at Q0. I'm reading in the first symbol that's a 0, then I stay at Q0 because I'm done reading all of the symbols in the string and I ended in a non-accepting state, a state that's not double circled. This machine will not accept, it will reject this string. So 0 is rejected. Now let's try plugging in 1. I start at my starting state, I read in a 1, so if I read in a 1, now I'm at state Q1, I finished reading all of the symbols in the string and I ended in an accepting state. And because of that, 1 is accepted by the machine. Now you want to build off of what I like to call the atomic parts, the smallest parts, and let's build off from 0. So let's say I have 0 and then I just add a 1. So if we read in 0, 1, we start at the starting state, we read in the first symbol, that's 0, so we're still at Q0. Then we read 1, so then now we're at state Q1 because I finished reading all of the symbols in my string and I ended in accepting state, in a double circle state. The machine accepts 0, 1. So far the language of the machine consists of the string 1 and 0, 1. These are the strings that our machine accepts or recognizes. What if we took this and built off of this? So we take 0, 1 and then add one more 0. Well, if we have the string 0, 1, 0, we start here, we read in the first symbol, that's a 0, we're still at state Q0. I read in the next symbol, that's 1, so now I'm at state Q1. Then I read in a 0, so I'm still at state Q1. I finished reading all of the symbols, all of the characters in my string, and I ended in an accepting state, so therefore this machine indeed accepts 0, 1, 0. So the language of the machine also recognizes 0, 1, 0 as a string. And notice that after 0, 1, 0, we can actually do as many zeros as we want after that, because it's just going to keep on staying at this state. So 0, 1 with as many zeros as you want will always be accepted. So 0, 1, 0, 0 is accepted, and then 0, 1, 0, 0, 0, 0 would also be accepted, and so on. Now, let's go back to 0, 1. We know that adding as many zeros after that 0, 1 is always going to be accepted, but what if we add a 0 before that 0, 1? This is my string. I start here. I read in a 0. If I read in a 0, I stay at the state. I read another 0, I stay at this state. And then if I read in a 1, I finally go to the accepting state. because I ended in an accepting state, this string is also accepted by the machine. So then notice though that once you begin, you can actually have as many zeros as you want. So I could have 0, 0, 0, 0, 0, 0 as many times as I want, and then have a 1, and then have zeros again as many times as I want. So basically 0, 0, 1, 0, 0, 0, 0 as many times as I want. So that string would also be a string in the language that the machine accepts. Now, what if we build off this 1 and add a 0 after? Well, if I read in this string, I read in 1 first, so that means I'm at state Q1, and then I read in a 0. I'm still at state Q1 because I finished reading all of the symbols in my string and I ended in accepting state. This machine accepts this string, so 1, 0 would also be part of the language of the machine. And then again, a string like 1 and then as many zeros as you want after, so 1 and then as many zeros as you want after, will be accepted by the language of the machine. And notice that we can have a billion zeros after this 1, so this actually goes on forever. So what do we notice about all of these? Well, I notice that they all have a 1, but particularly they only have exactly one 1. They don't have 2 1s or 3 1s. They only have 1 1. And then the amount of zeros actually doesn't matter. So we could say that the strings, so these are strings, that this machine accepts are all of the strings that contain exactly 1 1. And you can see that in the state diagram. The only way you can get 1 1 is when you have as many zeros as you want, then you have exactly 1 1, and then as many zeros as you want after that. There's no other option to get a 1. And it's not like you can go back here, repeat the process, and get another 1, right? So using words, the language of this machine is going to contain all of the strings from sigma star. By the way, if sigma is a set of your input symbols, so that's just 0 and 1, then sigma star is going to be all of the strings that you can construct using these symbols, using the elements in sigma as many times as you want. So it's all of the strings that you can create using these symbols. So for example, sigma star could be the empty string because you could just not use these symbols. You could use 0 one time, you could use 1 one time, you can use both of them together to create a string. You can use 0 2 times and then 1 1 time to create a string, and so on. And so these are all of the possible strings you can create using the symbols, but that's not what our language is. Our language is all of the strings from this set with exactly 1 1. So it wouldn't be this. You don't see 0 here in this set. It wouldn't be the empty string because there's not a 1 there. It would be this string. We have that here. We have 0 1 here. We also have 0 0 1 as part of the language of the machine because it has exactly 1 1. And so that's the idea. We're saying out of all of the strings that could be made, we only want the ones with exactly 1 1. And notice that this could go on forever because you can put as many zeros as you want before you have a 1. You could do 4 zeros, 5 zeros, and so on. So this is an infinite set. So because it's too big and we can't physically sit down and write all of the elements in the set, we can use set builder notation to describe the set by saying that the language of the machine consists of W, and W will be an element of sigma star. So it's going to be one of the strings that could possibly be made from the alphabet, from all of the symbols that we're reading, such that W contains exactly 1 1. Another way people word this is by saying such that W contains 1 as a substring. So just part of the string somehow. It could be at the beginning, that's 1 as a substring, or it could be in between, or it could be at the end. The point is it's part of the entire string somehow. Now finally, how can I use regular expressions to describe the language of the machine? I believe this is the easiest, especially in the academic sense, because sometimes they'll have machines that just accept like so many random strings and you can't put it into English, like all strings that have exactly 1 1, or all strings that end with 1, or all strings that end with 0. And you can just describe the path to the accepting state by saying, okay, I start here. I can do 0 as many times as I want. So 0 one time, 0 another time, 0 another time. So that means I can do 0 as many times as I want. That's what the star means. Followed directly by 1 1. So I have to have a 1. And then once I do that, I can do 0 as many times as I want again. So 0 as many times as I want. And that's it. It's so quick and easy, and this means the same thing as this, and it means the same thing as this, and it means the same thing as this. Now, another application of regular expressions is that you can use them in set builder notation. So we could also say that the language of the machine is equal to, and then you just plug in the regular expression, but wherever you see a star, you replace it with a variable. So we could say 0 to the n times, and then a 1, and then we have 0 to the, pick another variable, m. So these variables represent how many times you're choosing to use these strings. So this is saying, hey, I can use 0 n times. N could be 0 times, it could be 1 time, it could be 2 times, but it can't be -1 times. That doesn't make sense. Yes, I'm going to use 0 -1 times. No. So we have to restrict, so we have to say such that n and m have to be greater than or equal to 0. It can't be negative. So it should be an element of all of the integers that are greater than or equal to 0. Because remember that the set of integers includes -1, 0, 1, 2, and so on. It includes all the negative numbers, 0, all the positive numbers. We only want from here on out. So we say, okay, we want this as long as it's greater than or equal to 0. And that's it. Now make sure to have more of these types of problems where you're given a machine and you're told to describe the language of the machine using regular expressions. And of course, these problems will be on Story Studies' website. The link is in the description box below. So far we've covered grammar, then finite state machines, then regular languages, together with regular expressions. But I want to come back to this right here because we don't just have regular languages, we also have something called non-regular languages. And these non-regular languages are going to be our transition to why we need Turing machines and why the Turing machines are useful. If languages that DFAs and NFAs recognize are called regular languages, then that implies that there are languages these finite state machines are not able to recognize. We call these non-regular languages. So if we have a language for which we're not able to design a DFA or an NFA that recognizes that language, then that language is not regular. So we call it non-regular. So to distinguish between regular and non-regular languages, I'm going to do an explicit example for both. So the regular language example should be just a warm-up because we've been working with regular languages up until now. So let's say that the language consists of the string a:b. That's the only string in this language. So if we try to construct a finite state machine, either a DFA or an NFA, we always start somewhere, and that somewhere is just a starting state. So we do an arrow for starting state, and we can call it state Q0. Now the idea is this is where I'm starting, and what I want to say is if I read in an A, well, that should take me to another state. Let's call it state Q1. If I'm at this state and I read in a B, well, that should take me to another state. Let's call it state Q2. And if I'm at this state and I read in a B, well, then that should take me to another state. Let's call it state Q3. And if I'm at state Q3, that's because I've taken this path, A, B, B. I've read in A, B, B. And A, B, B is a string in the language this machine is supposed to accept. So if I'm done reading this sequence of symbols, the state that I end up in should be an accepting state because I'm supposed to accept this string. So I should make Q3 a double-circled state. So this is not a DFA because remember that for a DFA, given your alphabet, remember that your alphabet is a set of all input symbols. So all of the symbols that you could ever read in this machine, that includes A and B. For every element in this set, for every symbol, there should be exactly one transition in every state. In other words, one arrow. So for example, in this state, I only have a transition, I only have an arrow for A, but I don't have one for B. So because of that, this is not a DFA. It's definitely an NFA, because for an NFA, I'm allowed to have exactly 0 transitions for a symbol in the alphabet. In this case, I have 0 transitions for B. I don't have any arrows for B, and that's fine for an NFA. So I managed to construct a finite state machine, specifically it's an NFA, for this language. But what if I had a language described by this expression? A to the n followed by B to the n. What this is saying is that this language consists of all of the strings that start by having A n amount of times followed by B n amount of times. Notice that the variables are the same, so these numbers will always be the same. And we can find some of these strings, and we can actually find some of the strings that belong to this language. A good place to start is the first number we're able to use, and that's 0, because we can't say, okay, I'm going to use A -1 times. That doesn't make sense. So if we used A 0 times and B 0 times to construct a string, then that string would be the empty string because we didn't use A or B. So there's nothing. What if I used A 1 time and B 1 time? Well, then that would be the string with 1A directly followed by 1B. So that would be the string AB. What if I use A 2 times and B 2 times? Again, these numbers are always supposed to be the same because n, they're the same. Well, this string would use A 2 times directly followed by B 2 times. What if I use A 3 times and B 3 times? Well, then this string would be A 3 times directly followed by B 3 times. And so the pattern is you could use A n amount of times and B that same n amount of times, so you'll have infinitely many strings in this language because you can use A 1 million times, B 1 million times, and so it's going to be A, B, 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 B. And you can do this for every number. And there's infinite amount of numbers, so you can see how this set goes on forever. Now let's see what happens when I try to construct a finite state machine. In this case, I'm going to go for an NFA because it's more flexible. for this language. A good place to start is a starting state. So I'll have a state, I'll call it Q0. And the same way that for this string, I had a state for every single symbol in this string, one for A, then another one for B, another one for B. I'm going to do the same for every string in this language. So let's start with AB. I want this machine to recognize or accept the string AB. So that means if I'm at the starting state and I read in an A, I want to go to another state, let's call it Q1. Then if I read in an A, if I happen to read in a B at that state, I'm going to go to another state and call it Q2. If I made it a state Q2, that's because I've read in an A directly followed by a B. And that is a string that this machine is supposed to accept. So therefore, Q2 should be an accepting state. So I should double circle it. Okay, great. So far my machine accepts the string AB. But what about this string? Well, this string starts with reading an A. That's fine. Now we're at state Q1. But after that, I'm supposed to read another A. So let's say I read in another A, well then I'm at another state, let's call it state Q3. Then after that, I'm supposed to read in a B. So I'll say, okay, if I read in a B, I'm now at another state, let's call it state Q4. Question, why don't I say if I read in a B, I go from state Q3 to state Q2? Because that would say if I read in an A, B, then I end up in an accepting state. And my machine should not accept the string because it is not a string in this language. And I don't have to look at the set to know that, because I know from this expression that all of the strings in this language should have the same amount of A's and the same amount of B's. Here I have 2 A's and only 1 B. It should be AAB if that's a string in the language. So AAB is not a string in the language, so I should not accept that string. So we shouldn't do this and instead go to a new state. Now so far at state Q4, if I get there, it's because I've read AA and B. But I want to be able to read AAB. So if I want to read another B, I would just go and make another state. And if I get to state Q5, it's because I've read it an A, and then a B. So I've read this string. So if I've read that string, which is part of the language, and this machine should accept that string, so state Q5 should be a string that machine accepts. So state Q5 should be an accepting state. So far my machine accepts the string AB and then AABB. So far my machine accepts the string AB and then AABB. But what about this string? Well, first I should read an A, that's good, now I'm at state Q1. Then I should read another A, well then that's good, now I'm at state Q3. Then I should be able to read another A. So from state Q3, I read in an A, let's say I'm at another state, called it state Q6. Then from there I should read in a B. So if I read in a B, let's say I'm at state Q7, then I have to read another B, so let's say now I'm at state Q8. Then I have to read in another B, so now let's say I'm at state Q9. And if I'm at state Q9, it's because I got there by reading an A, an A, an A, and then B, B, B. In other words, I read this string right here because the string is part of the language and this machine should accept the string, so state Q9 should be an accepting state. Now, hopefully you noticed the pattern. We have to do this for all of the strings, and there's infinitely many strings. In the worst case, we would have to have a state for every single symbol or character in every string we want to accept. In this case, in the best case, we have less than that, and you can see it here. Instead of having to start from state Q0 for every single string, I kind of reuse some of the states. But the point is, you're still going to have an infinite amount of states. It's not feasibly possible for us to sit here and draw a billion circles, a billion states, because there's infinite amount of strings. I mean, you can see that this path here represents the string AB, this path represents the string AABB, then this path represents the string A 3 times followed by B 3 times, and you can see how it keeps getting longer as the string gets longer. And we have infinite many strings, so we're going to have to do this infinitely many times. And a finite state machine doesn't have the power to do that. And so we realize that a finite state machine, so a DFA or an NFA, is not able to recognize all of the strings in this language. So again, we call this language and any other language DFAs and NFAs, so finite state machines don't accept non-regular languages. And so the question is, if finite state machines are not enough, we still have languages that we want to have machines accept them. Is there a machine that recognizes these non-regular languages? Is there a machine that's more powerful? In other words, is there a machine that will recognize non-regular languages but also regular? So it does the job of finite state machines and it's more powerful, it's more better because it also recognizes non-regular languages? And the answer to that is yes, there is a machine that exists that does that, and it's called a Turing machine. How is it more powerful? Because a Turing machine has infinite memory, unlike finite state machines that have finite memory, hence the name finite state machine. So if we go back over here, I basically imply that the reason why finite state machines are incapable of recognizing all of the strings in non-regular languages is because we need infinite amount of states, and with finite state machines, we don't have infinite amount of states, we have finite amount of states. So then if I'm proposing a Turing machine as a solution to this, you would assume that, okay, then Turing machines must have an infinite amount of states, right? Wrong. A Turing machine actually has a finite number of states. In fact, a Turing machine is just a finite state machine plus one more component, and that's infinite memory, what we call a tape. And this is the advantage of the Turing machine, because you have to look at it from another perspective. The finite state machine relied on all of its states to store information about the problem. And so because we only have a finite number of states but infinite amount of information, we weren't able to store all that information in these states. Whereas a Turing machine doesn't depend on the finite state machine to keep track of all of the information in the problem. It depends on its tape, on its infinite memory. So both a finite state machine and a Turing machine have finite number of states. It's just that a Turing machine, unlike a finite state machine, doesn't depend on the finite number of states to store all of the information needed for the problem, and instead uses its infinite memory. Hence why Turing machines are actually able to recognize all of the strings in non-regular languages, because it has a more efficient way to store information about a problem, again, unlike a finite state machine that has only a finite number of states to store information, which is not enough for regular languages. And the idea of a Turing machine is it simulates how humans compute, because after all, our brains are computers too. And by compute, I mean think. When I say humans compute, I mean humans think. And usually we're thinking or computing an answer to a problem, or we're thinking about a decision that we have to make based on a problem that we were given. And so these problems are regular and non-regular problems. And so as a human, let's say that this is you as a human, you have a pencil, you have pieces of paper. What do you do when you have a problem? Let's say it's a math problem. Well, you first write down the problem on your paper. So let's say that this is your paper, and let's say that your problem is represented by 1010, so the sequence of symbols. Now, once you have the problem written down on the paper, the next step is to read what's on the paper. And you don't read the problem all at once. You might think that's how it works, that you just take the problem all in at once, but you actually start reading from left to right, and you start from the first part of the problem. So that's this one here. Now notice that I drew a pointer or an arrow, and it basically tells you where you are in the problem. So I don't know if you or one of your friends, when you were first learning how to read, maybe in kindergarten or first grade, you used a pencil to trace or keep track where you were when reading a sentence in a book. So in the same way, we use this pencil to keep track of where we are in a problem. So right now, this pencil is pointing to 1. So it says, hey, we're right here. So not only can we use the pencil to write down the problem, but we could also use it as a pointer or as a scanner to say, okay, this is where we are, and so on. So we're pointing to this 1. That means that 1 is the input that's going into our head, into our brain. So that's the next step. We compute and think about the input that's given, and we make a decision based on that input and our current state of mind, or the current state of the problem. So not only does an input go in there, but also the current state of the problem. So let's say state as 0. And depending on the current state of the problem and your current input, you're going to have to think about or compute a decision. And so that thought process, that computation happens here in your brain. But once you make a decision, the output is a decision, the state of the problem changes. So not only do you get a decision what to write down, what to replace this with if you have to, but you also get a new state of the problem, so let's call it S0 prime, doesn't really matter what you call it. And not only that, but you also have to make a decision about where to move. Do we move here? Do we point the pencil to this next symbol? Or do we move to the left? So the direction where to move to is another part of the decision. Now, once we have the decision what to write down, we actually write the decision or the result. So maybe the decision was to replace this 1 with a 0. So then we would replace this 1 right here with a 0. So then it would be a 0. And maybe the move decision was to move to the right. So we move to the right and we move on and repeat the problem until the problem ends. Either you keep moving to the right, the problem is over, you have nothing else to read, or the decision after reading a certain input is to stop, to halt. If that's the case, you could completely stop what you're doing, stop your computation, stop your thinking, and not continue on with the problem. Now let's zoom in and go back to the original statement that I made. and that was that a Turing machine simulates how humans compute. And if we said that these are the steps that a human takes to compute, then we're saying that a Turing machine actually simulates these steps. And so the question is how? So the way that a Turing machine represents a piece of paper is by using something called a tape. And you can see why they call it a tape, because it looks like a horizontal piece of tape, and it's an infinite horizontal piece of tape, meaning that it goes on forever. This is what gives the Turing machine infinite memory. Just how we have infinite amount of pieces of paper to write down our problem, we have an infinitely long piece of tape. And what's interesting about this piece of tape is that it's partitioned into infinitely many pieces. And what's in these pieces, well, if you go back to the piece of paper, when you start off, it's empty, right? So when you start off with this piece of tape, what's inside each of these partitions is nothing. And so how do we represent nothing? With a B, so B for blank. So it represents the blank symbol, that there's nothing in there, it's blank. And blank is not the same as the empty string. It's not the same as the empty string, so don't get confused. Now, once we write down our problem in the piece of paper, that's the same as us taking the tape and writing down the problem anywhere on the piece of tape. In this case, the problem is represented by 0, 1, 0, and everything else is blank. And so if you keep on going forever, all of these pieces are also blank. Now, in the same way that we had a problem written down on the piece of paper, now we have a problem written down on the tape. And so once you have a problem written down, the next step is to read what's on the paper. And we used a pencil to point to where the problem starts. Now, if you have Garcia or you use the Discrete Mathematics and its Applications textbook, if you go to page 889, at the bottom of that page, you'll see that our convention in terms of where to start reading from a tape is to start from the leftmost non-blank symbol. In other words, the first symbol that you see that's not blank, starting from the left. In other words, start where you see the start of the problem, so in that case, that's 0. Now, a Turing machine doesn't actually call this a pencil. Instead, it calls this the head or the scanner. So the head, the scanner, the pencil is saying, okay, we're reading this in first. So what's going inside your head as an input is 0, but not only that, but the state of the problem also. So the state of the problem, let's call it as 0. And what goes out should be your decision, the decision that you make based on the inputs. But that decision is based on a certain thought process. And that thought process, we call it a finite control. It's just going to be a finite state machine. They could give it to you in terms of a state diagram, or they can give you the transition table. With Turing machines, they actually love to give you transition tuples. So they basically give you all of the information you need in like a tuple, and we'll do an example like that. But that's what it is. It's just a finite state machine with infinite memory. That's the tape. So if this is the input, then the output, again, depending on your thought process, is going to be what you're going to write, the next state of your problem, because the problem changes depending on what you write. Like once you write something, or once you're at a certain state, you might be at a new state. And then also where you're going to move to after reading into 0. So let's say we write 1, the next state is, well, whatever the next state is, and we move to the right. Well, then that means I replaced the 0 with a 1, and then this pencil now moves to the right, and now I'm at state as 0 prime, and I'm reading in a 1, that's my input, and then we just continue this process until the problem is over. There's just blank symbols, nothing else left to read in the problem, or the decision when reading one of these inputs is to stop, to halt, to not continue with this problem. So hopefully now you have a picture of what a Turing machine is trying to do and how it simulates how a human solves a problem. So now let's go ahead and formally define what a Turing machine is and then do some examples. So for a Turing machine, we define it as Tm, or just M, and it consists of Q, which is a set of all states. Then we have sigma, which is a set of all input symbols, also known as the input alphabet. Then we have this new symbol called gamma, which is a set of all tape symbols, also known as the tape alphabet. So gamma can be denoted like this, or with an I and then a little line, so like this. Now, what is the difference between these two? Well, let's go ahead and take this as our tape. If this was our tape, then sigma is a set of all input symbols. So these are all of the symbols part of your problem. So our problem contains 0 and 1. So the set contains 0 and 1. Again, we don't want to do repeats because sets contain unique elements, no duplicate elements. And then our tape alphabet, gamma here, contains all of the symbols on your tape, hence the name tape alphabet. So that would include the blank symbol and 0 and 1. Then we have little f. It's just delta, it's our transition function. So our transition function says that the input, whatever is going in our brain, is going to be a state from the set of all states, and it's going to be a symbol from the set of all tape symbols. So it's going to be one of these that we're reading in. That's going to be the input. So if we're here and we read in a 0, well then the input is 0, and the state could be, let's just call it the first state as 0. So that's the input here. So what it's saying is, given a state and given a symbol from the tape, you may or may not get, and I'm going to come back to this may or may not get, another state or the same state. It's just going to be one state from the set of all states. So this is what we would call our next state, so we would call that S prime. So then the output would be S prime. Then we'll get a symbol from the tape alphabet. So we'll get a symbol from the set of all tape symbols. And so the idea is that whatever symbol they give us, that is a symbol we have to write down, or we have to replace whatever symbol was here with this symbol. So let's say it's 1, then I would have to replace this 0 with a 1, or write down 1 with my pencil. So the next part of the decision is what is written down. And finally, it's going to give you either left or right. In other words, it's going to give you where to move. So it's going to give you where to move because you could either go to the left or to the right. So then this would be your output. That's what the transition function says. But with the Turing machine, our transition function is actually a partial function. What this means is that given this, you may get another state, what to write and where to move, or you may not. And if you don't, then that means that the machine decided to stop, so it's a halt. Now there are two ways we can halt. Either the Turing machine accepts and halts or rejects and halts. But to be more specific, one way we can halt, but it doesn't necessarily mean the Turing machine accepts or rejects, is if we finish reading the problem. So if we read in a blank, then we know the problem is over, and it's up to whoever designs the Turing machine if that means we want to accept or reject. Another way to halt, to be more specific, is if you're at a state, let's call it state Q2. So the state of the problem is state Q2, but you have an input, let's call it 0, and state Q2 looks like this. Because you're at state Q2, and you're currently reading in a 0, well, the Turing machine is going to be like, well, I can't process a 0 at this state. It's impossible. There's nowhere to go. There's no transition for 0. I don't know what to do. I'm stuck. I'm going to halt. So it halts. But we do not call this a halting state. We don't call this a final state, because by the textbook's definition, a halting state is one that has no transitions, no arrows. This state has an arrow, so it's not a halting state, but it can behave like one because obviously it's going to halt if it's reading in a 0 and there's no transition for 0. So moving on, Q0 is the starting state. In the same way we have starting states for DFAs and NFAs, and big F is the set of halting states or the set of final states. Again, you can have accepting states and you can have rejecting states, so A for accepting, R for rejecting. And then F would contain both of these, QA and QR, as long as there's no transitions, because you can halt at both of them. And so this goes to show that just because a state is a halting state doesn't mean it's an accepting state or a rejecting state. It could be either or. This halting state is an accepting state and this halting state is a rejection state. So keep that in mind. Now going back to what I said earlier, a Turing machine is just a finite state machine plus memory. But the version that Garcia teaches is where the finite state machine is a DFA. So a DFA plus memory is a deterministic Turing machine. And then a non-deterministic Turing machine is an NFA plus memory. And if you recall, when we did finite state machines, when we did DFA specifically, if we had a state, for every state that we had to have exactly one transition for every symbol in the alphabet, no more, no less. Now, you might think that with the deterministic Turing machine that it's the same for every state. We should have exactly one transition for every input in the alphabet. And that's true, but the version of Turing machine we're doing adopts the convention of halting at no transitions. So even though it's a DFA and we said, yeah, we're supposed to have exactly one arrow for every symbol in the alphabet, we can actually have 0. That's fine. That would just suggest that the Turing machine would need to halt, because if, again, they're at a state and they're reading in a 1, for example, and there's no transition for 1, even though 1 is in the alphabet, we have the convention that it's just going to halt. That is the little rule that we're allowed to use. So that's why you might see Garcia have a state, let's call it state S2, and then have the alphabet. Notice how I use the tape alphabet, not sigma, not the input alphabet, because remember that this is supposed to represent the set of all symbols that we're reading in, and it doesn't just include all of the symbols from the input, but also from the tape, so the blank symbol. So let's say it's 0, 1, and B, and let's say that the state has a transition for 0, but it doesn't have one for 1 or the blank symbol. This is still a deterministic Turing machine, even though it has no transitions for 1 in the blank symbol, because again, we're allowed to use the convention, the rule that if there is no transition for a symbol in a state, then the Turing machine is just allowed to halt. In other words, if I'm at this state and the Turing machine reads in a 1, it's going to be like, well, there is no transition for 1. I have nowhere to go. I'm stuck. I'm going to halt. So the Turing machine, again, is just going to stop. And it's still a deterministic Turing machine. So keep that in mind. For this first example, we're told to let T, so this is T in this case, be a Turing machine defined by the 5 tuples. Now, if you're not familiar with tuples as a data structure, well, I'm sure you're familiar with the coordinate pair where you have 2 items, but this is also known as a tuple. In fact, it's actually a 2-tuple because it has 2 elements, 2 items. So then a 3-tuple would be the same thing, but with 3 items. And so you'll see how a 5-tuple, it's the same thing, but with 5 items. So here we have 1, 2, 3, 4, 5 items. And so just like you had the set data structure where it was just a list of items contained within curly braces, a tuple, it's the same thing, it's just a list of items but contained within parentheses. And the other difference is that here order does not matter, right? A set that's 1, 2 is the same set as 2, 1. But here the order does matter because you'll notice the first item of every tuple is of the same type. It's a state. It's one of the states from the set of all states. The second item of every tuple is one of the symbols from the tape alphabet. The third item of every tuple is the next state. In other words, it's going to be one of the states from the set of all states. The fourth item of every tuple is again one of the symbols from the tape alphabet, from the set of all tape symbols. And the fifth item of every tuple is either left or right. It's one of the elements from this set. So the last part of the tuple tells you what direction to move to. And you can see why order matters now, because if I switch 0 and R, well, what this is saying is, hey, move to the 0. That doesn't make sense. It's either move to the left or move to the right, not move to the 0. That's not a direction. And now they're saying for each of these initial tapes, so we have part A, which is this tape, and I'll do part B later, determine the final tape when T halts, when the Turing machine halts, assuming that the Turing machine begins in the initial position. In other words, they just want to see what the tape looks like when the Turing machine stops. So to start, let's actually translate this data into a transition table. So for a transition table, let's have every column in the table represent the type of every item in the tuple. So for the first item in every tuple, that's just going to be the current state. So we're going to call that just state. The second item is always going to be what we're reading from the tape. So one of these symbols, hence one of the symbols, one of the elements from the set of all tape symbols. So we're going to call that what we're reading. And so this here is our input. Our output is going to be the next state. So we're going to call it the next state. It's going to be what we're writing. So it's going to be one of the tape symbols. So we're going to call that what we're writing. And finally, it's going to be the direction that we're moving to. So we're going to call that where we're moving to. And now you just take every tuple and make it a row. So the first tuple, we have state as 0. We read in a 0. Our next state is S1. Then we write a 0, and then we move to the right. For our second tuple, our current state is S0. We read in a 1. The next state is S1. We write a 0. We move to the left. For our third tuple, our current state is S0. We read in a blank. Our next state is S1. We replace this blank with a 1. We move to the right. For our fourth tuple, our current state is S1. We read in a 0. Our next state is S2. We replace that 0 with a 1. So we write a 1. Then we move to the right. For our fifth tuple, our current state is S1. We read in a 1. Our next state is S1. We write a 1. We move to the right. For our sixth tuple, our current state is S1. We read in a blank. Our next state is S2. We write a 0. We move to the right. And finally, for our last tuple, our current state is S2. We read in a blank. Our next state is S3. We replace this blank with a 0, and then we move to the right. And this is our transition table. Now, from a transition table, you can draw the state diagram. A good place to start is, how many states will you need? We'll just find how many states are mentioned. We have 1, 2, 3, 4 states. So we'll have 1, 2, 3, 4 circles, one for every state, S0, S1, S2, S3. Notice how S3 is not here, and that goes to show that if you have a combo of where the state is S3 and let's say you're reading in a blank, there is no output for that input for this Turing machine. Hence the partial function notation that sometimes you'll get an output and sometimes you won't. So if you ever are at state S3 and you read in something, there's no row, there's no tuple that tells you what the output is. And we'll get to what happens when we get there. But anyway, I like to start from the first row. It says if we're at state S0 and we read in a 0, then we transition to state S1. That's the next state. So we go to state S1 if we read in a 0, but then we also write down a 0 and move to the right. So the way we denote this is with an arrow and then 0/right. So we write down a 0 and we move to the right. You could use a slash or you can use a comma. The second row says if I'm at state S0 and I read in a 1, I transition to state S1, but I write a 0 and then I move to the left. So 0/left. The third row says if I'm at state S0 and I read in a blank, then the next state is S1, so same thing. If I read in a blank, the next state is S1, and then I write a 1 and then I move to the right. So you have 1/right. This row says if I'm at state S1 and I read in a 1, then I stay at state S1. My next state is the same state. So if I read in a 1, I transition to state S1 and I write a 1 and I move to the right. So 1/R. This row says if I'm at state S1 and I read in a 0, then I transition to state S2. So if I read in a 0, I transition to state S2, I write a 1, and then I move to the right. So we have 1/R. This row says if I'm at state S1 and I read in a blank, I also transition to state S2. So if I read in a blank, I transition to state S2, I write down a 0, and then I move to the right. So 0/R. And finally, this row says if I'm at state S2 and I read in a blank, I transition to state S3. So if I read in a blank, I go to state S3. As my next state, I write down a 0 and I move to the right. So it's 0/R. And so you can see the pattern in how we denote this. First, it's a symbol you're reading from the tape, so one of the symbols from the set of all tape symbols. Then what you're writing or replacing the symbol with in the tape, slash the direction that you're moving to. So that could be left or right. Now, we didn't need to do this. I just wanted to show you that they could give you the same information using tuples, using the transition table, or using the state diagram. And there's different ways that people format the transition table. Sometimes they'll do one state instead of having every single possible transition or scenario. They'll just have S0, S1, and S2, and then they'll have a column for each of the tape symbols, so 0, 1, and B, and then they'll put the next state right and move in each of these corresponding cells. But it's all the same. Now, to define our starting state, by convention, we assume that S0 is a starting state. So we'll put a little arrow there to emphasize that, and that is stated on page 889 in your Discrete Mathematics and its Applications textbook. And by the way, the variable doesn't matter. It could be Q0, it could be R0, it could be T0. The whole idea is that it has the lesser of all of these numbers. 0 comes first, so S0 is your starting state. Now, what are our halting states? Well, to put it simply, a halting state is a state that has no transitions for any symbol that you could ever read from the tape. In other words, it has no arrows. So if you look at your state diagram, state S3 has no arrows, therefore it's a halting state. Now, the specific reason why is because if you read in either the blank symbol, 0, or 1, because all of these are the symbols from the tape alphabet, and you're at state S3, well, the Turing machine is going to be like, well, let's say you read in a 1, I can't compute this because there's literally no arrow, there's no transition for when I read in a 1. So it's going to be like, I can't do anything with this, so it's just going to stop, it's just going to halt. Same thing for 0 and same thing for the blank symbol. Now you might be like, why isn't state S2 a halting state? Because by definition, a halting state is strictly one that has no arrows. This state already has one arrow. Now, it's not a halting state, but it can behave like one. If you look at this state, and if you read in a 0 or a 1, let's say I read in a 0 this time, the Turing machine is going to be like, well, there's no arrow for 0. There's no transition for 0. And I'm at this state, I don't know what to do because I don't know where to go. So it's just going to stop. It's going to halt. There's no rule for when you're at this state and there's a 0. So the machine is going to halt, but by definition, it's not a halting state because it still has one arrow, one transition for at least one of the symbols from the tape. Now, your textbook actually doesn't even define a set of halting states, and actually some other textbooks define 3 specific states. So Q0, the starting state, QA, the accepting state, and QR, the rejecting state. And the reason why is just because you halt doesn't mean you accepted or rejected. Halting could mean either or, either you accepted or rejected. So they kind of break it up into accepting halting states, rejecting halting states. So those are some things to keep in mind. Now we have everything we need to come up with a formal definition of the Turing machine. That means defining each and every single one of these items. So the set of all states Q is going to be the set containing all the states. So just all the circles we have S0, S1, S2, and S3. Sigma, which is a set of all input symbols, is going to be the set of all of the symbols in your problem. So the problem is 0, 1, 0, 1. The only symbols used in this problem is 0 and 1. Your gamma, also known as your tape alphabet, is going to be the set of all of the symbols that could ever show up on your tape. So that includes 0 and 1 because they're already written on the tape. So 0 and 1, and then also the blank symbol. So we add that here. The transition function we already defined using the transition table. Q0, which is a starting state, is as 0. And big F, which is a set of halting states, is going to be the set containing S3. And this is the formal definition of our Turing machine. And we actually didn't need to draw the state diagram or the transition table because after all, they're just asking us what does the tape look like at the end of the day. And this information was enough because this information is exactly what we wrote here and exactly what we wrote here. And that's my point. I wanted to show you that they could give you the information of the Turing machine using tuples, using a transition table, or using a state diagram. So you have to be comfortable in all three formats. In fact, the transition table can be formatted in different ways. Instead of having S0, S0, S0 all the time, so just having all of the possible transitions for that state, they just do S0, the next state is S1, the next state is S2, and then they'll do a column for every symbol that you could ever read from the tape, so 0, 1, and B, and then they'll put this information in the corresponding cells for each and every single state so that it's a little bit more compact and clean that way. This should be here as 0 and so on, so keep that in mind. Now that we're done with this, let me go ahead and move the state diagram over here. Now if we go back to the big picture, this is you as a human. There's going to be some input that's going to go inside your brain, and then there's going to be some decision, some output that you're going to make. Now that decision depends on your computation process. It depends on your thought process. So there's something going on here. There's a set of rules that you're following that affects the output given a current input. And those rules are these right here. So we call these rules the finite control, or also known as the control unit. So right now, these are the rules in the form of a transition table, but you could also just write this down in here, or you could write the whole state diagram in here of the finite state machine, hence the name finite control. So at this point, we have a piece of paper and our problem is written down on it. We have a tape and our problem is written down on it. Now the question is, where do we start reading the problem from? Well, here's my pencil. Do I start reading the problem from here, or here, or here, or here, 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 or here, or here, or even here? Well, again, in this class, we always start reading the problem from where the problem starts. So that would be here at the 0. In other words, we start reading from the leftmost non-blank symbol. So the first non-blank symbol that we see, so that's the 0 right here. That's on the bottom of page 889 in your textbook. So I'm going to leave this pencil right here, and it's saying, hey, I am reading this 0 right now. This is where I'm at. But again, the Turing machine doesn't call it a pencil, it calls it a head, or it calls it a scanner, because you're scanning a symbol from the tape and you're reading it in. So far, the input to my brain is what I'm reading in from the tape, so that's 0, and the current state of the problem. Again, with Turing machines, we always assume the starting state is at 0. So this is our input right now. We have a state from the set of all states, so we have as 0, and we have a symbol from the set of all tape symbols, so that's 0 in this case. Now what's going to be the output? Well, it depends on my thought process, so we're going to go over here. Given our input, what's going to be your output? Well, I'm at state as 0, and I'm reading in a 0. If I read in a 0, that's this first row here, my next state is S1, so I'm going to write S1. I'm going to write 0. In other words, I'm going to replace this 0 with a 0, and then I'm going to move to the right. So to start, here we were at state as 0. I'm going to replace this 0 with a 0, so I'm just going to write 0. So we use the pencil to write down 0 as well, and then we move the pencil to the right. So we move on here to the right. So again, hopefully you can see the transition function come alive. You have a state from the set of all states. You can replace this with an X if you want, instead of a comma. You have a symbol from the set of all tape symbols. And then for your output, you have a next state, which is, again, any state from the set of all states. You have a symbol from the tape alphabet. And then you have a direction where you're going to move to. So that would be one of the elements from this set, left or right. And so at this point, we're scanning something new. So now we're at state S1. So I'm going to change this to an S1, and we're reading in a 1 this time. Well, now what's going to be my output? Well, let me think, let me compute. And actually, to make things go faster, I'm going to replace the transition table with the state diagram because it's easier to spot things faster visually. So if I'm at state S1 and I'm reading in a 1, well, I stay to state S1. The next state is the same state. So the next state is going to be S1. I'm writing a 1, and then I'm moving to the right. So the decision here is to replace this 1 with this 1, so I'll just write 1 here, and then move to the right. So I'm going to move my head, my pencil, 1 to the right, and then the next state is going to be state S1 still. Now the input changed. Now I'm reading in a 0, so this becomes a 0 now, but I'm still in state S1. Now what is the output going to be given this input? Well, if I'm at state S1 and I read in a 0, well, if I read in a 0, I go to state S2. So my next state is state S2. I'm writing a 1, and then I'm moving to the right. So I'm going to replace this 0 with a 1. So I'm going to replace this 0 with a 1. I'm going to write a 1. And then I'm going to move the pencil, the head, to the right. So I'm going to take this and move it to the right. And the state that we're in right now, the state of the problem, is state S2. And now we're reading in another input. We're reading in a 1 this time, so this becomes a 1, and the state of the problem is now state S2. So this is our input. What's going to be our output? Well, if I'm at state S2 and I read in a 1, well, notice that state S2 can't read in a 1. So the Turing machine has no idea what to do. There's no possible path for reading a 1 in state S2, so it's just going to halt. It's going to stop. So this here is the final tape for when the Turing machine halts. So this here would be your final answer. Alright, so here's part B. It's the same Turing machine, you're just given a different tape. So where do we start? In the start of the problem starts here, the leftmost non-blank symbol, that's 1. By convention, we start at state S0. So we start at state S0 and we're reading in a 1. This is our input, what's going to be our output? Well, if I'm at state S0 and I read in a 1, that means I go to state S1. So my next state is state S1, and I write down a 0 and I move to the left. This means I replace this 1 here with this 0. So I'm going to write down a 0 here with this pencil, and then I'm going to move to the left. So I'm going to take my pencil and move to the left, and now I'm at state S1. So I'm going to write S1 up here. So now I have a different input that's going inside my brain. I'm reading in a blank symbol, so this changes to blank, and now I'm at state S1. So now this is the input. What's the output? Well, if I'm at state S1 and I'm reading in a blank symbol, well, if I read in a blank, I go to state S2, so S2 becomes my next state that I go to. I write down a 0, and then I move to the right. So I'm going to replace this blank symbol with a 0, so this blank becomes a 0. Then I move to the right, so I'm going to take my head, my pencil, move to the right, and now at this point I'm at state S2. So now I erase this, and now I'm at state S2 up here. And now my input is different. Now I'm reading in a 0, so I'm going to change this blank to a 0, and now I'm at state S2. The state of the problem is state S2. So given this input, what's going to be my new output? Well, if I'm at state S2 and I read in a 0, we'll notice that it's impossible to read in a 0 at state S2. So the Turing machine is going to be like, well, I can't do anything with the 0 at the state. I don't know what to do, so I'm just going to stop. I'm going to halt. So the Turing machine halts at state S2 because it can't read in a 0. There's no arrow for 0. And so this is what your tape would look like at the end of the day. That would be your answer, what they're asking for. Here we have example 2. We're told to design a Turing machine that replaces all 0s on the tape with 1s and replaces all 1s with 0s. The machine must halt when it's done. This means that if you have a tape and it looks something like this, 0, 1, 0, then your final tape should look something like this. You replace a 0 with a 1, 1 with a 0, 0 with a 1. It should look like this. So a good place to start with these construction questions is a state diagram, and a good place to start with a state diagram is to have a starting state. So let's have a state, call it S0 as our starting state. And the idea is, again, if we have a 0, so let's say we have 0, 1, 0, 1. If we start with a 0, well, we want to replace it with a 1, and then we want to move to the right because we want to read the next symbol. And then if we read a 1, we want to replace it with a 0, and then move on to the right because we want to read the next symbol. And notice how we'll be in the same state of the problem. We'll just be going back and forth until we read a blank, as in we finish with the problem. So once we read in a blank, we should be in a new state, and you can replace the blank with the blank and move to the right. But the idea is that you would be at a halting state, a state with no transitions, a state where the Turing machine will have to stop. So let state S0 be the starting state, but also the state that you stay in until you just stop replacing all 0s with 1s and 1s with 0s. So you want to stay in state S0 if you read in a 0, but when you read in a 0, you also want to replace it with a 1 and then move to the right. But also, if you read in a 1, you want to replace it with a 0 and then move to the right until you read in a blank, and then you go to a halting state. So let's call it SH, H for halting, and then we can replace this with a blank and move on to the right. And if I want to construct my transition table, well, I would just have my state, my read, my next state, my write, and my move columns. For state as 0, if I read in a 0, the next state is as 0, and then I write down a 1 and I move to the right. For state as 0, if I read in a 1, my next state is state as 0, the same state, and I write down a 0 and then I move to the right. And also for state as 0, if I read in a blank, the next state is state sh, and then I write down a blank and then I move to the right. Now we can test it. Let's say that our tape looks something like this, 0, 1, 1, 0, and then everything else is just blanks. It's an infinite tape. So we start at the start of the problem. We're starting at state as 0, and we're reading in a 0. So we're here at S0, we read in a 0. That means we replace that 0 here with a 1. So I'm going to replace this with a 1, and I move to the right. So now my arrow here moves to the right, and I'm at state as 0 still. So now I'm at state as 0, reading in a 1. So state as 0, I read in a 1, I stay at state as 0. I replace that 1 with a 0. So I'm going to take this 1 and replace it with a 0. And then I move to the right. So I move this arrow to the right. And once I move to the right, I'm currently at state as 0. I'm at state as 0 and I'm reading in a 1. Well, if I read in a 1, I replace that 1 with a 0. So I'll replace this with a 0. Then I move to the right. So I'll take this arrow to the right. And at that point, the state of the problem is still as 0. I'm at state as 0 and I'm reading in a 0. Well, if I read in a 0, I replace that 0 with a 1. So I'm going to take this, replace it with a 1. Then I move to the right. So if I move to the right, I'm still at this state as 0. And now I'm at state as 0 and I'm reading in a blank symbol. So if I'm reading in a blank symbol, I replace the blank with a blank. So this blank here, I'll replace it there. And then I move the arrow to the right. So I move it to the right. Over here is just another blank symbol. It's just blanks forever. And I'm currently now at state sh. So I'm at state sh and I'm reading in a blank symbol. But wait, state sh has no transitions for a blank symbol, so the Turing machine will be stuck and will be like, well, I don't know what to do with this, so it's just going to stop. It's going to halt. And so this is what the tape is going to look like once the Turing machine halts, once it finishes. And you can compare. This is the original tape. This is the final tape. 0 was replaced with 1, 1 with 0, 1 with 0, and 0 with 1. So you managed to design a Turing machine that replaces all zeros on tape with 1s and replaces all 1s with 0s. Now, to give a formal description of this machine, just to kind of complete the process here, the set of all states is going to be, well, the set of all states, all circles, so we only have S0 and SH, so it's going to be S0, SH. The set of input symbols are all of the symbols that are part of your problem. So your problem is only made up of zeros and ones, so 0, 1. Your tape alphabet is all of the symbols on your tape. So that's 0, 1, and the blank symbol, 0, 1, and the blank symbol. The transition function, we did a transition table. The starting state Q0 is S0, and the set of halting states, big F, is just going to contain SH, because that is the only halting state. It's the only state that has no arrows. Now, I do want to note that if you remove this part of the Turing machine, that's completely fine. But you might be like, well, wait, isn't this a deterministic Turing machine? So shouldn't I have for every state a transition for every symbol in my alphabet, in my tape alphabet? I have one for 0, I have one for 1, but I don't have one for B now because I removed it. But remember, for this version of a Turing machine, we're allowed to adopt the convention that if we are at a state and we're reading in a symbol and that state has no transition for that symbol, the Turing machine is allowed to simply just halt. So if I'm at this state and I'm over here reading in a blank, the Turing machine is going to be like, well, I can't read in a blank at this state. There's nowhere to go. I'm stuck, so I'm just going to halt. So instead of doing all that, just take advantage of the fact that you can just not have a transition for B, and so that suggests that when it reads B in this state, it will just stop, which is what it's supposed to do once it reads in a blank, because that means it's the end of the problem. So because we removed this halting state, we no longer have any halting states, so this set of halting states is just empty. And that's it for this problem. This is example 3. We're told to design 2 finite state machines, so a DFA and an NFA, and a Turing machine that recognizes this language. So this language contains all of the strings that start with 0 or 1 as many times as you want, but ends with 0. So some of the strings in this language would include 0 itself because it ends with 0. It would include 0, 1, 1, 0 because it ends with 0, and all of the strings before that are just 0 or 1 as many times as you want. It would also include 1, 1, 1, 0 because it ends with 0, and all of the strings before that are 0 or 1. In this case, is just 1. 3 times, and so on. Now note that the language is denoted using an expression. Do we know if this expression is regular or not? Not yet. We have to first see if we can construct a DFA or an NFA that recognizes this language, and if we can, then it would be a regular language, and hence the expression that denotes this regular language is also regular. But let's go ahead and start with an NFA because it's more flexible. A good place to start is a starting state, so let's have a starting state, call it Q0, and the whole idea is you can directly translate. You have 0 or 1 as many times as you want. So when you start, you can do 0 or 1 as many times as you want and stay at the same state, and the only way you could ever go to an accepting state is if you end with 0 after that. So you would have a transition if you read 0 to another state, let's call that state Q1, and that would be our accepting state, so we make it a double circle. Because it's saying, hey, the only way this machine can ever accept a string that we input is if after it picks 0 or 1 as many times as it wants, it needs to end with the 0. That's the only way we get here. So that would be the NFA. Now, it's not a DFA because remember that for a DFA, every state needs to have exactly one transition for every symbol in our alphabet. Our alphabet is a set of input symbols when it comes to an NFA. So all of the symbols we're inputting are 0 and 1. So I should have exactly one arrow for 0 here and exactly one arrow for 1 here, but I don't. And not only that, but for this state, I should have exactly one arrow for 0, but I have 2 arrows for 0. If I read in a 0, I stay at state Q0 or I go to state Q1, and so that's why it's not a DFA. So what would be a DFA here? Well, if you don't want to think about it, you could straight up just find the equivalent DFA by doing subset construction, and I'll have a video on how to do that if you're interested. It will be one of the practice problems on the website for subset construction, and the link to the website is in the description box below. But you could just think for a DFA, we can keep track of the last symbol we've read. So there's only 2 options. Either we read a 0 or we read a 1 because those are the only symbols we ever read. So let's have 2 states. One is a starting state. Let's call it Q0 and we'll call the other state Q1. Now the idea is at the end of the day, what do we want? Well, we want to accept a string if it ends with Q0. So not only is Q0 the starting state because of the 0, but let's actually treat it as in it's the state where the last symbol we read is a 0, and this state is the state where the last symbol we read is a 1. So if we end up in this state, that should be an accepting state. And the only way we get here is if we read in a 0, because remember, 0 itself is a string that this language accepts. But if we read in a 1, all of a sudden we're now at this state, in the 1 state, in the non-accepting state. And after we're here, I mean, we can read 1 as many times as we want, right? Because the whole idea is you could do 0 or 1 as many times as you want. But if you happen to have a 0 after that, if you read in a 0 at this state, well, then now you can go to the accepting state because you ended with a 0. But if you didn't end with a 0, you read a 1 after that again, it would just be a whole process until you end with a 0, and then you can have 0 as many times you want after that. So this says the exact same thing as this. It's just instead of this very simple way to do things, we're saying, okay, you can have 0 and 1s as many times as you want. It doesn't matter. Go to the loop. The point is it has to end with 0 at the end of the day, and that's the only way you'll get to the accepting state. And we can test it. Let's say I have string 0, 1, 0. I start at my starting state. I'm reading in a 0. If I read in a 0, I stay at this state. Then if I read in a 1, well, if I read a 1, now I'm at state Q1. If I read in a 0, now I read in a 0, I'm back at this state because I finished reading all of the symbols in my string and I ended in an accepting state in Q0. Therefore, this machine recognizes or accepts this string. And it should because we have 0 and 1 as many times as we want. And then we finish off with a 0. Now, because we were able to design an NFA or a DFA that recognizes this language is therefore a regular language, and this expression that denotes this regular language would also be a regular expression. Now, what would the Turing machine look like for this language? Because again, Turing machines recognize regular languages and non-regular languages. So any language that you can build an NFA or a DFA to recognize, there is a Turing machine that recognizes that same language as well. So the way to think about this is from the perspective of the tape. So let's say you have a tape 0, 1, 0, blank. Everything else is blank. It's an infinite tape. There's really 2 things that you have to check. Number 1 is that all of the symbols before the last one are 0s and 1s only. And then the second thing you have to check is that the last symbol is a 0. So the idea is that we start here, and all we really have to do is keep moving to the right and check if those symbols are 0s and 1s. And then once we read a blank, that means we passed the last symbol. So we want to go back to the last symbol, go back and make sure it's a 0. And if that's true, then the Turing machine can accept the string that was inputted. So a good way to start is a starting state. So let's have a state, call it Q0. And the idea is we just want to keep moving to the right if we read 0 or 1. So if we read in a 0, we want to go to another state. Let's call it state QR, as in R for right. So we're going to be at the state of just moving on to the right and keeping on doing that. Now to finish off the details, if we read in a 0, we want to replace with the 0 and move on to the right. And the same thing for a 1. If at the starting state we read in a 1, we want to replace it with a 1 and move on to the right. And we want to keep on moving to the right as long as we keep reading 0s and 1s. So we'll have a loop here. As long as we keep reading a 0 or a 1, we'll replace with a 0, move on to the right, replace with a 1, move on to the right. And we keep on doing this until we reach a blank symbol. So if we read in a blank symbol, we're going to go to another state, and I'm going to call it state QC, C as in check what the last symbol was. So how do we go back to the last symbol? Because remember, if we have something like 0, 1, 0 blank, if we reach a blank, that means we passed the last symbol. So we have to go back to the last symbol to check what it was. That means we have to move to the left. Because if right now we're here, we would have to move to the left. So we would replace B with a B, move to the left, and now I'm at the state where I'm checking what this symbol is. Remember, if the symbol is 0, it's going to accept. So if I read in a 0, I'm going to go to an accepting state. I'm going to call it QA. And since it's an accepting state, I'm going to double circle it. And if I read in a 0, replace with a 0, move to the right. But if this is a 1, then it's going to be going to a rejecting state. I'm going to call it QR. So if I read in a 1, I replace with a 1, move to the right. So let's test it with this string 0, 1, 0. We start at the start of the problem, and we start at state Q0. So I'm at state Q0, and I'm reading in a 0. So if I read in a 0, I'm replacing the 0 with a 0. So I'm keeping it the same because I just want to skip. I don't care about this right now. And I'm moving on to the right. So now this pointer moves to the right. And because I read in a 0 at this state, my next state is state QR. So now I'm at state QR and I'm reading in a 1. Well, if I read in a 1, I replace that 1 with a 1, so just keep it the same, and I move my pointer to the right. And because I read a 1, I stay at the same state, so the next state was QR. Now I'm at state QR and I'm reading in a 0. Well, if I read in a 0, I replace it with a 0, so it stays the same, and then I move on to the right. So now I'm moving to the right, and because I read in a 0, the next state is state QR. Because I'm at state QR and I'm reading in a blank, if I read in a blank, I replace it with a blank, so it stays the same. And I move to the left now. So this pointer here is now to the left. And because I read in a blank, that transitions me to state QC. So now I'm at state QC and I'm reading in a 0. Well, if I read in a 0, I replace it with a 0. So I just let it be the same thing. And then I move to the right. And because I read in a 0, the next state is state QA. So now I'm at state QA and I'm reading in a blank. Well, there's no way to read in a blank from state QA, so the machine halts, and because it halted in an accepting state, this machine accepts this string, which it should because the string 0, 1, 0 starts with 0s and 1s as many times as it wants. In this case, it's 0 one time and 1 one time, and then it ends with a 0, which is exactly a string in this language right here. So the set of halting states, if we were to provide a formal description, would include QA and QR. It's just, again, some halting states are accepting states, some halting states are rejecting states. Now, another way you can construct the Turing machine is by keeping track of the last symbol and just really focusing on that. And a good place to start, again, is a starting state. So let's have a starting state called a Q0. And from the beginning, the only paths that you could take are one that start with 0 or one that start with 1. Because you could either start with a 0 or a 1. And even if you choose to start with 0, 1, 0 times, you'll have at least 1 0. So either you start with a 0 or a 1. That's still true. So either you read in a 0 and you go to another state. Let's call it state QL0. As in, you're keeping track of the last symbol and you're saying it's going to be 0. So if we're here, it's because the last symbol is 0. So if we read in a 0, let's just replace it with 0, move on to the right. Or from the starting state, you can read in a 1 and go to another state. Let's call it state QL1, as in the last symbol is 1. So if we're here, it's because the last symbol we have read so far is 1. And so if we read in a 1, let's replace it with a 1, keep it the same, and move on to the right. Keep moving on. So the idea is once you read in a 0, the only way you can stay here is if, well, you keep reading a 0. So let's finish off the details. If you read in a 0, let's keep it a 0 and move on to the right. Keep going. Now, the only way you could stay here in the state where the last symbol I've read is a 1 is if the last symbol you read is a 1. So that would be if you read in a 1, you stay in the 1 state. So if you read in a 1, let's keep it a 1 and move to the right. Now again, if we're here, it's because the last symbol we have read is a 1. The only way to get out of here is if the last symbol we've read is a 0. So if we read in a 0 at this state, The last symbol we've read is no longer a 1, it's a 0. So now we would have to go to this state. So if we read in a 0, we would have to transition to the last symbol we've read is a 0 state. We read in a 0, we keep it a 0, we move on to the right. Now if we're at this state, it's because the last symbol we have read is a 0. And the only way we get out of this state is if we read in a 1. So the last symbol we've read, the symbol we've read most recently, is no longer a 0, it's a 1. So we shouldn't be in this state, we should be in this state. So if we read in a 1, we transition to this state. So if we read in a 1, we write a 1, move to the right. Okay, so at this point, it's as if the last symbol we have read is a 0, so it's like we're right here. At this point, it's like the last symbol we have read is a 1, so it's like we were right here. And then there would be blanks here. The only way we can get out of this is if we read something other than a 1 or a 0, a blank. So if we read in a blank, we go to another state. And if we read in a blank, that actually means we're done reading the string. We've read all of the zeros, all of the ones. And what this is saying is if we're done reading the string and we manage to get to this state with the last symbol being 0 and all of the symbols before the last symbol were zeros or ones, then this machine should accept this path, this string. So this should be an accepting state, so we'll make it a double circle state. And again, if we're reading a blank, you can replace it with a blank, move on to the right, just keep on going. Now, if we're at this point in time where the last symbol we've read is a 1, and we happen to read in a blank, that means the string is done. There's nothing after that. If we get to this state and the last symbol we read was a 1, then this machine should not accept this path. It should be a rejection state. So we'll call it QRR for rejection. Because again, our language should not accept any string that ends with the 1. It needs to end with a 0. So if we read in a blank, we can replace with blank and move on to the right. So this is another way we can draw the Turing machine. Now let's go ahead and test this. So let me come up with a little tape for you. We start here at the start of our problem. We start at state Q0 by convention. So we start here, we read in a 0. We're now at state QL0. That's going to be our next state. And we replace this with a 0 and we move to the right. So now my pointer, my head, my pencil points to this. Now we're at this state and we're reading in a 1. So if I read in a 1, I'm now at this state. I replace this 1 with a 1 and then I move to the right. So now my pointer is here and my next state is QL1. Now I'm at this state and I'm reading in a 0. If I read in a 0, that means I'm now at this state. So the next state is QL0. I replace that 0 with a 0 and I move on to the right. So now my pointer is here pointing to the blank. So now I'm at QL0. And I'm reading in a blank. So if I read in a blank, I'm now at this state. I replace that blank with a blank, doesn't really matter. Move on to the right to this other blank symbol, and that is an accepting state now. And so the whole idea is that the Turing machine accepted this string because all of the strings before the last symbol are zeros or ones, and the last symbol was a 0. So it should accept the string 0, 1, 0. And to be more general about it, the Turing machine halted at state QA, but it could have also halted at state QR. So again, halting doesn't mean accept or reject, it just means you stopped. But either you could stop because it accepted the problem, it rejected the problem, or it could actually loop on forever if it doesn't find a halting state, or it could halt simply because there is no transition for a state. Now, what if the tape looked like this? We have 0, 1 as a string. We start here, this is state Q0. At state Q0, we start by reading in a 0. If we read in a 0, we replace that 0 with a 0, then we move to the right. So now we move to the right, and our next state is state QL0, so QL0. We're at state QL0, and we're reading in a 1. If we read in a 1, that means we're now at state QL1. That's going to be our next state. So QL1 is our next state. And if we read that 1, we replace that 1 with a 1, and we move to the right. So this here moves to the right. So we're going to move it to the right once. So far, this is what we have. Now we're at state QL1, and we're reading in a blank. If we read in a blank, we replace that blank with the blank, and we move on to the right. So now this here points to here, and our next state is state QR, and now we're at a rejection state. And it's also a halting state because it has no transitions for any of the blanks that you read after, so it's going to be like, I can't compute this input, so I'm just going to halt, I'm going to stop. At this point, we've done 3 examples on Turing machines, so hopefully you feel comfortable enough to design a Turing machine for this non-regular language that I use to introduce or motivate the use of Turing machines. So let's go ahead and get started. For this example, we're told to design a Turing machine that recognizes the language denoted by a to the n, b to the n, where n is greater than or equal to 1. This means that all of the strings in this language are going to start with a n number of times followed by b n amount of times. And these n's are the same variable, so it's going to be a and b the same number of times. For example, the language consists of n being 1, so a and b used 1 time, so that would be the string ab. You can make n be 2, so you use a 2 times and b 2 times. You can have n be 3, so a 3 times followed by b 3 times, and so on. So these are the types of strings that this Turing machine should accept. And we already covered, back when I introduced what non-regular languages are, that this is basically the prime example of a non-regular language, because to do this with a finite state machine, you'll need infinite states, infinite memory, and we don't have that with a finite state machine. But with a Turing machine, we have the tape, which represents the infinite memory. So a Turing machine works to represent non-regular languages. So our tape would look something like this. We'll have a n amount of times, so n is equal to 3, and then we would have b n amount of times, and n is the same. So we know that this string is part of the language. We already know that because we see that a and b are used n amount of times, and the b's are used after a, right? You can't do b first and then the a's. But we have to, nevertheless, design a Turing machine that does that job for us. And here's how you do it. As always, we start here. And what we want to do is anytime we see an A, we want to replace it with an X so we know that we've been here before. And then we want to skip until we see the first B and mark that with an X. As in, for every A that we have, we want to find its corresponding B. We want to make sure that we have the same number of A's as we do B's. So let's start with the starting state. Let's call it state Q0. And at the starting state, so right here, the idea is if we read an A, we want to replace it with an X and then move our pointer or head to the right because we want to keep on going. And we want to just skip until we see our first B. So at the starting state, if we read in an A, we want to go to another state, but we want to replace this A with an X, and then we want to move to the right. So far we replaced this A here with an X, and then we move the pointer that was pointing here to the right. And this new state, I want to call it the skip state, because the idea is that you want to skip this until you see your first B. In other words, if we're at this state, because that's the state we're at right now, we're at the skip state, if we read in an A, we want to continue skipping. We want to stay in this state of skipping. So if we read in an A, I'm just going to replace it with an A to keep it the same and just keep on moving to the right. So right here, I read it in A, so I'm going to replace it with an A, so it basically stays the same, and then move on to the right. Here, I'm still in the same state, I'm reading in an A, so I'm going to replace it with an A so it stays the same, and then I move to the right, so I move to the right. And the idea is that you're going to keep on skipping until you see your first B. So the only way you can get out is if you read in a B, and if you read in a B, you want to mark it with an X. If I read in this B here, I want to mark it with an X, so I'm going to replace it with X, and then I want to go back to the beginning and repeat the process. So I don't want to go and move the pointer here to the right, I want to move it to the left. So I'm going to go to the left. So I'm going to take this pointer, go to the left, and by doing that, I'm now in another state. Now ideally, from here, we want to go all the way back to the beginning. But remember that with this version of the Turing machine, we can only move one direction, either left or right. So the only option we had is to just go back one step. So that's what we did, we moved back once left. But then from there, we're now at a new state, and we can call it the go back state. And so the idea is we want to keep going left. That means we want to skip anytime we see these A's. We want to continue in this state of going back as long as we see A's. We don't want to change them. So we'll keep them the same and then keep moving to the left. But the question is, okay, I'm here, I read in an A, I replace it with an A, and then I move to the left. Okay, so now my pointer is here. I'm reading in an A again, I replace it with an A, and then I move to the left, so now my pointer is here. Now we're at the beginning, that's great, but here's the thing. What if we had another X over here? What if the beginning was here, and we were right here, at this state, and we're reading this X? Well, when the beginning is here, and the only way you would think to skip this one is you would have to say, if I see an X, just keep it as an X, and keep moving on to the left, just skip it. But then that would skip this X here as well. And so the trick is to use this blank symbol, because remember that before your problem, there's a blank. So from here, skip, skip, skip until we read in a blank. So if we're at this go back state, remember that the goal is to go back to the start of the problem, which is here. But we're saying, okay, if we're at this state, we're going to keep going back. So we're going to keep going to the left no matter what we see, until we read in a blank, and that implies that the cell right after it is the start of the problem. So we want to move the pointer, the head, from here 1 to the right. In essence, if we're at this state, if we read in a blank, well, we want to replace it with the blank. It doesn't matter what we replace it with, but the point is we want to move 1 to the right. So if our pointer is here, now it's going to move 1 to the right, and then we want to transition to the starting state. And this is where we are right now. We're at state Q0, and we're reading in an X, but right now we don't have any transitions for X's. So we want to stay at this state until we read in another A. So if I read in an X, I want to stay at this state. So I'm going to continue staying at the state. If I read in an X, I'm just going to replace it with an X and keep moving on to the right until I read in an A. And then I do the process all over again. I'm at this state right over here. I'm reading in an X, I'm going to replace it with an X, and then I'm going to move my pointer to the right. Now I'm at this state. Now I'm here. I'm still at state Q0, but now I'm reading in an A. If I read in an A, I replace it with an X. I'm going to replace that with an X, and then I move my pointer to the right. So now I move my pointer right over here, and because I read in an A, now I'm at a new state called skip at this point. So I'm at state skip, and I'm reading in an A. If I read in an A, I replace it with an A so it stays the same, and I move the pointer to the right. Because remember, I'm just trying to skip all of the A's, everything, until I find the first corresponding B. So that means I want to skip this X as well. So if I'm at the skipping state, the only way I want to get out is if I read in a B. So I want to say if I read in an X, I'm going to keep it an X and keep on moving to the right. I'm going to keep on skipping until I see a B. So at this state, I'm reading in an X right here. I'm going to replace it with an X. So in other words, keep it the same and then move to the right. So I'm going to move it to the right, and I'm still at the skip state. So I'm going to write skip here. And I'm at the skip state, and I'm reading in a B now. So if I read in a B, I replace it with an X. So I'm going to make this an X here. And then I move my pointer to the left. So I take this, and I move it 1 to the left. Because I read in a B here, I'm now at the go back state. So right now I'm at the go back state, and I'm reading in an X. Well, if I read in an X, I replace it with an X. So it's still an X, and then I move to the left. I'm still at the go back state, but I'm reading in an A. If I read in an A, I replace it with an A and move to the left. So I replace this with an A and then move the pointer to the left. I'm still at the go back state. I'm reading in an X right over here. So I replace it with an X and then I keep moving to the left. I'm at the go back state. I'm reading in an X again. I replace it with an X and then I move to the left. I'm still at the go back state, but now I'm reading in a blank symbol. And if I read a blank symbol, that means now I'm at state Q0. I leave the blank as it is, but move the pointer to the right. Right now it goes from here to here. And now we start again at state Q0. So I'm at state Q0 and I'm reading in an X. So I replace it with an X and then I move the pointer to the right. I'm still at state Q0. So I'm here, I'm reading in another X. So I replace it with an X and then I move the pointer to the right. And I'm still at state Q0. So if I'm at state Q0, but I'm reading in an A this time, well, if I read in an A, I replace that A with an X. So I'm going to replace that with an X, and then I move the pointer to the right. So 1 to the right. Now that took me to this state, to the skipping state. So here I'm at the skipping state. And the idea is I'm skipping if I see an X and an A. So I see an X, I'm skipping over here. I still see an X, I'm still skipping. Finally, I'm still at the skipping state, but I'm reading in a B this time. So if I read in a B, I replace it with an X, like so, and then I move to the left. So now I take this pointer, move it to the left once, and now I'm at the go back state. So I'm at the go back state, and I'm reading in an X. So if I read in an X or an A, I just keep going left. So I go left, I read an X, I go left. I read an X, I go left, I read an X, I go left, I read an X, I go left. Still in the going back, in the going left state. But now I'm reading in a blank. Well, if I read in a blank at this state, I replace it with a blank symbol and then I move to the right. So now the pointer that was here goes here to the right, and we're now at state Q0. And we're staying at state Q0 in the state of just moving to the right as long as we read in an X. So here I'm reading an X, so I can move to the right. I read in an X, I still move to the right. I read in an X, I keep moving to the right. I read in an X, I keep moving to the right. But now I'm reading in a blank. Now, what does it mean for all of your symbols to be X'd out? That means that for each A, you found a corresponding B. So if all of your symbols are X's and then you get a B, that means you're done with the problem and this string was indeed part of the language so the Turing machine should accept. So right now we're at state Q0, I'm reading in a B. So if I read in a B, I'll just replace it with a B, move to the right, doesn't really matter. The whole idea is that if I read in a B, I go to an accepting state. Double circle it because it's an accepting state, and let's call it state QA, A for accepting. And so what this is saying is from the start of the problem, you're going to continue skipping to the right, so just going through the entire string as long as you see an X. And if you keep doing that and then you read in a blank, that means your whole string was gone through and you found a corresponding B to every A, so the Turing machine should accept that string. Let's try another one. We start at the start of the problem. This is state Q0. We're reading in an A. So we're at state Q0 and we're reading in an A. That means I replace it with an X. So I'm going to replace this with an X. And then I move the pointer to the right. So I'm going to move it here. Because I read it in A, now I'm at the skip state. So right now I'm at the skip state and I'm reading in a B. Well, if I read in a B, I replace it with an X. So I'm going to take this and replace it with an X. And then I'm going to move the pointer to the left. So now I'm going to go here. Because I read in a B, now I'm at the go back state. So right here I'm at the go back state. And I'm reading in an X. Well, if I read in an X, I replace it with an X so it stays the same. And then my pointer goes to the left. So now I'm here and I'm still at the go back state. Now I'm at the go back state and I'm reading in a blank. Well, if I read in a blank, that means now the next state is state Q0. So next state is state Q0. I replace that blank with a blank so it stays the same, and then I move this pointer to the right. So now I'm at state Q0 and I'm reading in an X. It stays the same and I move to the right. So now I'm here and I'm still at state Q0 and I'm reading in an X again. It stays the same and I move to the right and I'm still at state Q0. So now I'm at state Q0 and I'm reading in a B. But if you look, state Q0 has no transitions for B. It only has a transition for X, for A, and for the blank symbol. So capital B, not lowercase b. So the Turing machine is going to be like, well, it's impossible for me to read in this B at this state because this state has no transitions for B. It has nowhere to go for B. So I'm stuck. I don't know where to go. There's nowhere to go. So I'm going to halt. I'm going to stop. And because it halted at a state that was not explicitly determined to be an accepting state, then this Turing machine did not accept the string. And that makes sense because the string A, B, B is definitely not part of the language of this machine. Because the language says that all the strings should have the same number of A's directly followed by the same number of B's. In A, B, B, we have one A and yet two B's. So we have A to the 1 and B to the 2. And so these are two different numbers. They're supposed to be the same. So already we knew from the get-go that this was not going to be a string that this machine accepts. And so our Turing machine works. So here the Turing machine accepts the string AAA directly followed by triple B, but it does not accept the string A, B, B. Now, as for the formal description of the Turing machine, we'll start off with Q, which is a set of all states. So Q is going to be the set containing the states Q0, skip, go back, and the state QA. Then we have sigma, also known as a set of all input symbols or the input alphabet. That's going to be equal to the set containing all of the symbols from your input. So that could only ever be A or B. Or you can look at the tape at your problem. Here we had 3 A's and then 3 B's. Here we had 1 A, 2 B's. The only symbols that were ever inputted were A and B. So it's going to consist of A and B. Then we have gamma, which is a set of all tape symbols. That's going to be equal to the set containing all of the symbols ever written on the tape. So that includes all of the symbols from your input because your input, the problem, is written on the tape. So that's A and B. But it also includes the blank symbol because that's on the tape. And it also includes the X symbol because we use that on the tape as well. Q0 is a starting state. So Q0 is just whatever starting state that is. That's Q0. Then we have big F, which is a set of halting states. Halting states are defined as states with no transitions, no arrows. And so if you look at all of these states, the only ones that have no arrows is just this one. So that's going to be F is equal to the set containing state QA. Now, as for the transition function, you can use a transition table, or you could do the more condensed and simpler version, and it's just to describe the transitions of the Turing machine using tuples. So for every state and every input for that state, you're going to specify where you're going to replace that input with, and then where you're going to move, and then what state you're going to transition to next. So for state Q0, I read in an X. If I read in an X, I replace it with an X, and then I move to the right, and then my next state is the same state, so that's state Q0. Then for state Q0, if I read in an A, I replace it with an X, and then I move to the right, and then my next state is state skip. Also for state Q0, if I read in a blank, I replace it with a blank, and then I move to the right, and then I go to state QA. And you repeat the same pattern for the rest of the states, and you'll get these tuples here. And that's the formal description for this Turing machine. I'll see you in the next video. Now that we're done with Turing machines, I wanted to discuss a limitation of this version of the Turing machine that we're using, which is just a DFA plus memory plus this little convention or rule that I've mentioned before and I'll mention again in a second. But let's go back to big F. We said is a set of halting states, and we define halting states to be states with no transitions, meaning if we have a state, let's call it Q1, this is a halting state because it has no transitions, it has no arrows. State Q1 that looks like this is not a halting state because it has a transition, it has an arrow. But remember, we adopted this convention, this rule that says if a state has no transition for an input that you're reading, then the Turing machine is allowed to halt. So for example, let's say we have state Q1 and it looks like this, there's a transition for 1, but let's say I'm at state Q1 and I read in 0 as an input. This state Q1 has no transition for 0. So therefore, this rule here allows us to halt. The Turing machine is just going to halt because it's going to be like, well, I can't read in a 0 at this state. There's nowhere to go. I'm stuck, so I'm just going to halt. I'm going to stop. So in general, we can say that this version of a Turing machine halts when there's no transitions left. But again, it could also halt if there is no transition for an input at a certain state that you're in. So because this Turing machine only halts when there's no transitions left, this Turing machine is vulnerable to infinite loops because you could actually design the Turing machine so that there's always transitions for every input that you read and you just stay at the same state and you just keep on going left and right. For example, let's say I have a tape that looks like this. It's just 0, everything else is blank. If I have a state, let's call it state Q0, and let's say I read in a 0, I want to stay at state Q0, but I'm going to replace that 0 with a 0, move to the right. But then if I read in a blank at this state, I'm going to replace it with a blank, so I'm going to keep it the same, and then I'm going to move to the left. Okay, let's try this. We know that convention is to start in the leftmost non-blank symbol. This is the first non-blank symbol I see. Convention is to start at the starting state Q0, so we're at state Q0 and we're reading in a 0. Well, I'm going to replace it with a 0, and then I'm going to move to the right. So now I'm here at the right, and the next state, because I read in a 0, is the same state, Q0. So now I'm at state Q0 and I'm reading in a blank. Well, if I read in a blank, I replace it with a blank, so it stays the same, and then I move to the left. Okay, so now I'm here to the left. I'm right back where I started. Okay, great. I'm still at the same state, Q0, and I'm reading in a 0. Again, it stays the same. I move to the right. Okay, I'm still at state Q0, and now I'm reading in a blank. It says, okay, move to the left. So notice how it's just going to keep moving to the right, to the left, to the right, to the left, and it's never going to stop because that's the way we designed the Turing machine, specifically because we made sure that this state had a transition for every symbol in the tape that we could ever read. So it's never going to be the case that the state will have no transition for an input. We made sure that there was a transition for every input from the tape alphabet. And we also made sure that this state has transitions. It's not a halting state because it has arrows. In fact, it has 2. So if we said that this Turing machine only halts when there's no transitions left, so either this or this condition is met, and both of these conditions are not met, we can see how it's never going to halt. So in other words, the Turing machine has a few options. You either halt, and that could consist of you accepting or rejecting when you halt, or you just go on forever. You're just in an infinite loop, and the Turing machine will never halt. It will never stop. We're finally at the end. We've covered grammar, then finite state machines, then Turing machines. But remember our transition to learning grammar and finite state machines. We started with the big picture, or the big question we're trying to answer, and that is, can a problem be solved using a computer? But we said we're going to answer that question right at the end. And meanwhile, we decided to focus on a specific problem and seeing how we can solve that problem theoretically. And that led us to learning grammar and finite state machines as a skill. And now that we have those skills, we were able to easily understand Turing machines. And now that we understand Turing machines, we're almost ready to see if this question can be answered for any decidable problem. Remember in the beginning we said that the problems we're focusing on are decidable problems, ones that can be answered with yes or no. And I say almost ready because in order to see if we could actually answer this question, we need to learn a little bit of some vocabulary. So there's something called the Church-Turing Thesis. And the Church-Turing Thesis says, if a problem can be solved with an algorithm, so just a piece of code on your computer, any computer, then that same problem can be solved with the Turing machine. So if you have an algorithm that exists for a problem, there's a Turing machine that exists that solves that same problem. That's what this is saying. And the opposite is true. If you have a problem that can be solved with a Turing machine, then there exists an algorithm, piece of code, that you can write on any computer that solves that exact same problem. Now note, this has not been proven. That's why it's called a thesis. There's no proof for it, but there's a lot of evidence that supports the thesis, and honestly everybody just treats it like it's true. But again, there's actually no proof. So keep that in mind. Now, if we entertain this thesis and start thinking about some applications of it, one application might be if you have a problem you want to solve, you can start by finding out if it's possible to solve the problem in the first place. Before you spend time and days trying to solve the problem, you could see, well, is it possible to even do this so that you don't waste your time if it's not? And you do this by seeing if you can solve it with a Turing machine. Because remember, if we follow the Turing thesis, if you find a Turing machine that solves a problem, then there exists an algorithm that solves that exact same problem. So you already know that algorithm exists, so now you can spend time writing up some code trying to find the algorithm that solves that problem because you already know it exists. You just need to find it. So really what we're saying is if it could be solved on a computer, it could be solved in a Turing machine, and if it can be solved in a Turing machine, it can be solved on a computer. So the way that we're modeling a computer here is with a Turing machine. In essence, what we're saying is that the Turing machine is the ultimate abstract mathematical model of a computer that can theoretically perform any computation, solve any problem that any physical computer can, under the laws of physics, of course. So we cleared this part up, but what does it mean for a problem to be solved by a Turing machine? Well, remember when we learned about DFAs and NFAs, and we said that any language recognized by a DFA or an NFA is called a regular language. Well, in the same way, any language recognized by Turing machines are either called decidable languages or undecidable languages. Now, you might be like, well, what does this have to do with problems? Well, again, remember in the beginning, we decided that the problems we're going to be talking about are yes or no problems, and we found that any yes or no problem can be converted into a set membership problem, meaning it just becomes a question about a set. And then we did grammar and we learned that we call these sets languages. In other words, when we say problem, that's equivalent to a language. So problems recognized by Turing machines are either called decidable problems or undecidable problems. And we already went over this really in the beginning. We said decidable problems are those that can be answered with yes or no. And that's exactly what we have here. Problems that can be recognized by Turing machines are decidable if that Turing machine always gives you an answer. And not just an answer, but the correct answer. Either a yes or a no when you give an input. Otherwise, if it doesn't give you a clear yes or no answer, it's called undecidable because the Turing machine can't decide. In other words, it's decidable if it halts. It could either halt at an accepting state or at a rejecting state. So accepting would be the equivalent to yes, rejection would be the equivalent to no. But this has to be true for all inputs that you put into the Turing machine. So it always has to halt. Sometimes it can halt. Sometimes the Turing machine can give you yes, it can give you no as an answer. But sometimes if you put in another input, it might keep going on forever in an infinite loop. So because it doesn't always give you an answer, it's undecidable. So knowing this information now, we can really say that the question of can a problem be solved using a computer is the same as asking, well, is this problem decidable? Am I able to get a clear yes or no answer always, no matter the input? That's what it means for a problem to be solved, that you always get an answer, a yes or a no. So the conclusion here is, if we can design a Turing machine that is decidable, meaning that it always halts given whatever input you give it, either it gives you a yes or a no, an exception or a rejection, if we can do that for a problem, then by the Turing thesis, there exists an algorithm we can write. So what we're saying is, if there is a Turing machine, then the Turing thesis says that there exists an algorithm that solves that exact same problem the Turing machine solved. Hence, the problem is solvable if we could do that. Now let's go back to our classic example. Is n even? Right? That's a problem. I can give you any number. I want to know if it's even. And this is a very simple problem. We obviously know that there's an algorithm for this. But imagine if it was a more complicated problem. And this is you, and you're given this problem to solve. So you can go open up your computer, write some code trying to find an algorithm that solves this complicated problem. But you're spending days, and it's taking so long. So instead of doing that, what if you took the problem and you found out if this problem is n even could be solved using a computer in the first place? Because if the answer to that is no, then you already know it's not worth it to spend time writing code to find an algorithm that doesn't exist, because you know that it can't be solved. If the answer is yes, then you know it's worth it trying to write code to find that algorithm that you know exists because you know that the problem can be solved theoretically. And how do you do this? By taking this same problem and seeing if it can be solved using a Turing machine. And by solved, we mean finding a Turing machine that is decidable, that always halts given any input you give it. It always gives you either a yes or a no. And what better problem to test this on than our classic is an even problem? So we're going to go ahead and try to design a Turing machine that recognizes all even numbers. So recall we designed a grammar that will generate all even numbers as its language, so it will generate the set of all even numbers. And then we designed a finite state machine that will recognize all even numbers. Now we're going to go ahead and design a Turing machine that recognizes all even numbers. See if we could do that. A good place to start is to think about one input. So if I input, let's say, the number 23 into the Turing machine, what should be the output? Well, it should say no, or it should reject this number because this is not an even number. We want this Turing machine to only accept, to say yes to even numbers. How do I know it's not an even number? Because the last digit is not even. Meaning, if the last digit is even, then the Turing machine should say yes, should accept that input. And luckily for us, all numbers we could ever input are made up of the digits 0 to 9. And out of those 10 digits, only 0, 2, 4, 6, and 8 are even. So if the last digit is any one of these digits, then the Turing machine should accept the input, should say yes, this is an even number. Otherwise, if it's 1, 3, 5, or 7, it should say no, it's not an even number, it should reject that input. So our tape could look something like this, where 23 is written on it. Everything before and after our input are just blank symbols because it's an infinite tape. So a good place to start would be the starting state. So let's have a state called Q0. And the convention is we start at the start of the problem, so that's this 2, and we start at the starting state, which is Q0. And really, all we care about is the last digit. So no matter how big the number is, we want to skip every single digit until we get to the last one. But how do we know when we get to the last one? Well, as soon as we reach a blank, that means we finished reading in the input. But it also means that the symbol before that blank was the last digit of that input. So we could say, we'll stay at the starting state until we read in a blank, and once we read in a blank, I'll just keep it the same, a blank, and then I'll move to the left. So I'll go back to this last digit, and then now I can have another state, let's call it Q check, where I'm going to check if this last digit is even, and if it is, I want to go to an accepting state, QA, and if it's not, if it's odd, then I want to go to a rejection state, call it QR. In order for it to go to the accepting state, we have to be at this state, and we either have to read in a 0, a 2, a 4, a 6, or an 8. But because this is a Turing machine, we have to do so much extra work. We have to say, okay, if I see a 0, replace it with a 0 and just move on to the right. Just move on to the next state, which is the accepting state. And same thing, if we read in a 2, keep it a 2, just move on to the right. If we read in a 4, keep it a 4, move on to the right. If we read in a 6, keep it a 6, move on to the right. If we read an 8, keep it an 8, move on to the right. Otherwise, if we're at the state and we read in any odd digit, like 1 or 3 or 5 or 7, then we want to go to the state. So we want to keep it the same, just move to the right so we can go to the rejection state. If we read in a 3, keep it the same, just move to the right. If we read in a 5, keep it the same, move to the right. If we read in a 7, keep it the same, move on to the right. And so that's the idea. And over here, we really can call this a skipping state because we're staying in this state until we read in a blank, until we read in all of the symbols. And all of the symbols that we could ever read are all of the digits 0 to 9. So we would have to say if we read in a 0, if we read in a 1, a 2, a 3, a 4, all the way to 9, we would have to say, okay, keep it a 9, just keep on moving to the right, and so on. And that's a lot of work, which is why encoding is important. What we can do, instead of using the symbols 0, 1, 2, 3, all the way to 9, those are 10 symbols, how about we just use 2? We said that any number we can come up with are made up of the digits 0 to 9, but we could also represent any number in the world with 2 digits, 0 and 1. And that is known as binary encoding. If you haven't taken CompArc, that's where you learn it, but it's super simple. If you have the number 23 and you want to convert it to its binary, start with your powers of 2 and you start counting from 0. So 0, 1, 2, 3, 4, 5, and so on, and just 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the 0, anything to the 0 is 1, 2 to the first is 2, 2 squared is 4, then we have 8, 16, and 32. And then you want to do some spaces here. And you can keep on going, but with small numbers like these, you want to stop when the number here gets bigger, so we don't want to use this 32. We want to use 0 32s. And let's say I want to use 116. I want to use 0 8s because if I already have 116 and then I use 1 8, we have 6 and then plus 8. So 7, 8, 9, 10, 11, 12, 13, 14. So that's 24, which is more than 23. So I don't want to use any 8s because that's going to get me over. So 0 8s, I'll do 1 4 because then 16 plus 4 is 20. Then I'll do 1 2, so that gets us to 22. And then finally 1 1, so 22 plus 1, that's 23. So finally we got our number. So 23 in binary is 10111. So our tape can look something like this now. It's the same number, 23, it's just in binary. And it may look more complicated, but you'll see that the Turing machine will be much more simpler because the only symbols we have to worry about in the alphabet are 0 and 1, instead of all of the digits from 0 to 9. Now you might be like, well, wait, the number now is in binary. How am I supposed to know if it's even or odd? Well, in the exact same way that you knew that this decimal number was even or odd, you look at the last digit. If it's 0, then the number is even. If it's 1, then the number is odd. Now the math behind that is, well, let me give you an example. If we take the number 5, we know it's odd, right? But what is 5 in binary? We'll start with the powers of 2. Just write 2 as many times as you want. Start counting from 0, 0, 1, 2, 3, so on. 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 to the third is 8, and just do lines here, bits, for every place value. These here are place values. To get 5, well, I want 0 8s, because that would get me more than 5. I would want 1 4. I want 0 2s, because now that I have 1 4, if I add 2, that's going to get me more than 5. And then I would want 1 1, because now that I have a 1, I can do 4 plus 1 is 5. So 5 in binary is 101. If I didn't know that this number was 5, how would I know if it's odd or even? I would look at the last digit. It's 1, so the number is odd, which we know because it's 5 and 5 is odd. But the math behind that is, look at the place values. They're just powers of 2. It's 2, it's 4, it's 8. If you keep going, it's 16, it's 32, 64, and so on. All of these are even numbers. The only odd number here is this 1. In other words, what this means is, you will always have an even number. If you do 1 of this, or 0 of this, it doesn't matter. You'll always have an even number unless you have this 1. Because if you take 1 of this 1, it's going to take whatever even number you have and make it odd. Because if you have an even number and you add a 1, it will always make it odd. So that's the math behind that. But from here, a good place to start is a starting state. So let's have a starting state, call it Q0. And it's the same thing. We want to skip all of the numbers until we get to this last digit, because that's all we care about. We want to check if it's 0 or 1. So this state, you can call it skip until the end if you want. I'm just going to call it Q0. And in order to skip, if I read in a 1 or a 0, I have to keep on moving to the right. So I'm going to stay at this skipping state as long as I read in a 1 or a 0. So I'm just going to keep it a 1 and move to the right, keep it a 0 if I read a 0 and move to the right. That's all I care about, moving to the right. And I'm going to stay at this state of skipping 1s and 0s until I read in a blank. Because reading in a blank doesn't only suggest you're done reading the number, but it also tells you that the last symbol before the blank is the last digit of the number, which is what we care about. So once we're here, we just want to move to the left. So if we read in a blank, we want to replace it with the blank. We don't really care what we replace it with, and just move to the left. And we're going to go to another state, and we're going to call it QC, C for checking, because now we're here and we want to check if this is a 0 or a 1. If this last digit is a 0, that means that the number is even, and if the number is even, well, this Turing machine should accept all even numbers, so we should transition to an accepting state, and I'm going to call it state QA, A for accepting. And it should be a double circled because all accepting states are double circled. And to finish it off, well, if I see a 0, I'll just keep it the same and move on to the right so I can get to this state. Otherwise, if this last digit is a 1, well, that means that the number is odd. I only want this Turing machine to recognize all even numbers, not odd ones. I want it to reject odd numbers. So if I read in a 1, I should go to a rejection state, QR, R for rejection. And to finish it off, if I read in a 1, I could just keep it the same and move on to the right so I can get to this state. And so this here is our Turing machine. You could see how much more simpler it is because of the use of binary encoding. If we had used the decimal number system, which is just the regular number system we learned in kindergarten, we would have to have transitions for all of the symbols in the alphabet, which would consist of all of the symbols from 0 to 9. So that'd be 10 of them instead of just 2. So over here, we would have to do, okay, skip all of the symbols you could see, which could have been 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So we would have to have a transition for 0, 1, 2, 3, all the way to 9. And once we were here checking the last digit, we could only go to the accepting state if we read in a 0, or a 2, or a 4, or a 6, or an 8. So we would have to have one of these transitions for all of these numbers. And then here, we could only go to the rejection state if we read in a 1, or a 3, or a 5, or a 7. So we would have to have one of these transitions for all of those digits. And you can see how tedious that is, and how useful it is to only have 2 symbols you have to deal with. Now let's go ahead and test it. By convention, we start in the leftmost non-blank symbol. So the first non-blank I see is this one, the start of the problem, or the start of the input. And we start at state Q0. So I'm at state Q0, and I'm reading in a 1. Well, if I read in a 1, I replace it with a 1 and I just move on to the right. So now my pointer is here to the right. And I stay at this state because I read in a 1. So I'm still at state Q0. I'm at state Q0 and I'm reading in a 0 this time. So if I read in a 0, the next state it's state Q0, so the next state is state Q0. And then I replace that 0 with a 0 and I move on to the right. So now my pointer moves to the right. I'm at state Q0 and I'm reading in a 1 this time. Well, if I read in a 1, I replace it with a 1, so I just keep it the same, and I move to the right. And I'm still at state Q0 because I read in a 1. I'm at state Q0, I'm reading in a 1 again, I'm going to replace it with a 1, and then I'm going to move to the right. And I will still be at state Q0 because I read in that 1. And so the same thing happens, I'm at state Q0, I'm reading in a 1, I'm going to replace it with a 1, so I'm going to keep it the same and I'm going to move to the right. And because I read in a 1, I stay at the same state. So Q0 will be my next state. And now I'm at state Q0, but I'm reading in a blank this time. Well, if I read in a blank, I replace it with a blank. So in other words, I keep it the same, but this time I move to the left. So now I'm here. Because I read in a blank, I transition to state QC. So now my state is state QC. So I'm at state QC and I'm reading in this 1. Because I'm reading in a 1, I keep it a 1, so I replace it with a 1. And I move to the right, so now I go here to the right. So now I'm at the right. And because I read in a 1, I am now at the QR state. So over here, I'm now at QR. And because I'm at the QR state and I'm reading in a blank, well, there is no transition for a blank symbol. So the Turing machine is going to be like, well, I can't read a blank at this state. I'm stuck, so I'm going to halt. So the Turing machine halts at the rejection state. So therefore, this Turing machine says that this input, this number here, is not even. In fact, it's odd. Now let's test the number 2. 2 in binary is, well, let's use our powers of 2's. 2 to the 0, 2 to the first. That's 1, that's 2. Use your bits. Well, I would want 0 1s and 1 2 because 1 2 gives me 2. So 2 in binary is 1 0. So my tape could look something like this. The blank symbol, 1 0, the blank symbol, and it's an infinite tape. I start here and I start at the starting state. So the starting state stays here in the same state as long as I read in a 1 or 0. I just keep moving to the right until I read in a blank. So in other words, I skip this, then I move to the right, I skip this, then I move to the right. I'm still at state Q0 and now I'm reading in a blank. Because I'm reading in a blank, I move to the left now. So I go back over here, and because I read in a blank, now it's state QC. So I'm at state QC and I'm reading in a 0. Well, if I read in a 0, I move to the right, so now I'm here, and I transition to state QA, so now this is my state. So now I'm at state QA, and I'm reading in a blank. Well, there's no transition for the blank symbol. The Turing machine is going to be like, well, I can't read a blank symbol at this state, so I don't know what to do. I'm stuck, I'm going to halt. But it halts at an accepting state QA. So because it halted at an accepting state, the input that was 1 0, so 2, is even. So we were able to construct a Turing machine that is decidable, that can either decide yes or no, the input is an even number. It either accepts or rejects the input for all inputs that we give. So because we were able to construct a Turing machine that solves this problem, then if we entertain the Church-Turing thesis, that means that there exists an algorithm that solves this exact same problem. So it's worth it for us as a student to take this problem and spend time writing code trying to find that algorithm because we know that it exists, theoretically, following the Church-Turing thesis. So here's my computer screen. Let's write some code to try to find the algorithm that solves this problem, that takes in a number n and determines if it's even or not. So we could say if n, and then another way to think of if a number is even or not is if you could divide it by 2 and the remainder is 0, meaning it can be divided by 2, then it's even. And we know in programming that's just mod 2 is the same as 0. So we're saying if the remainder, when you divide by 2, is 0, then we know it's even, so we can print even. Otherwise, print odd. And that's our algorithm. So at the end of the day, the Church-Turing thesis says if there exists a Turing machine that solves a problem, then theoretically there exists an algorithm that solves that same problem, and vice versa. Now, if we're asked for a formal description of this Turing machine, we know that Q is the set of all states, so Q is going to be the set containing all of the states, which are just circles, so Q0, QC, QA, and QR. Then we have our input alphabet sigma, which is going to be the set containing all of the symbols from our input. Remember, we only use 0s and 1s to represent any number we input. So our input is only made up of the symbols 0 and 1. Now our tape alphabet gamma consists of all of the symbols that could ever be on the tape. So that includes all of the symbols from the input, which is 0 and 1, but then it also includes the blank symbol, so B here. Then Q0 is our starting state. Well, our starting state is state Q0, so that goes here. And then big F is a set of halting states. Those are states without any transitions, without any arrows, so that's state QA and QR. And again, some textbooks say define the accepting state, so that would be QA, define the rejection state, so that would be QR in this case. And then as for a transition function delta, or little f, you could do a transition table or you could do tuples. So one tuple could be for state Q0, when I read in a 1, I replace it with a 1, so I keep it the same, and I go to state Q0, so I stay there as my next state, and then I move to the right. Another tuple would be for state Q0, when I read in a 0, I keep it the same, so I replace it with a 0, and then my next state will be state Q0, and then I move to the right. Another one would be add state Q0. If I read in a blank, I replace it with a blank, and then I transition to state QC and I move to the left. And then you can do the same for the rest of the states. And that's it. This is the formal description for this Turing machine. At this point, we've done an example of a decidable problem, one that always gives you an answer, not just any answer, but the correct answer for every single input you pass into the machine. In other words, we did an example of a problem that's solvable by a computer. But what's an example of a problem that's undecidable? So the opposite, unsolvable. And remember, just because we say that a problem is unsolvable, it doesn't mean that for one input, there's never an answer. It could be that you pass in an input and you actually get an answer. Okay, you solved this specific case of the problem, but for other inputs, you may pass into the machine and not get an answer. So overall, the entire problem is unsolvable. You haven't solved it. Solved it means that, again, for every single input, every possible input you can pass into the machine, you always get an answer. If that's not true, it's undecidable, it's unsolvable. So that's an interesting question. What are some problems that can never be solved using a computer regardless of how much memory or power we have? Well, a classic example of that is called the halting problem. So the idea here is we'll have a Turing machine, let's call it H for the halting machine. So this machine is super cool because what you could do is as its input, you can pass in another machine, another Turing machine, let's just call it TM, and the input to that Turing machine. So for all you know, that Turing machine could be this one right here, and its input could be 1, 0 with 3 1s. So you pass that into the halting machine, and this machine is supposed to tell you whether this Turing machine that you passed in, or this program that you passed in, will either halt or not halt given that input. And to give you a more relatable and intuitive example, let's say you're on your computer and you're on VS Code and you're writing up a program, an algorithm, where you give it an input. And let's say that you press the run button, but it takes a really long time, and it almost feels like an infinite amount of time. Wouldn't it be nice if you had another program, right, just another algorithm, where you could pass this inside as its input, so your program and the input, you're passing all of this into this program, and it could tell you if that program with that input will ever finish running or it will keep on running forever. Wouldn't it be nice to know? So that's the idea. Here, a Turing machine, we know, is a theoretical model of a computer, of an algorithm, of a program, of a piece of code right here. So you can pass in your program with the input for that program, pass it in to a halting program, a halting machine H, that would ideally tell you if that program with that input will ever stop running or not, if it will just keep on running forever. And it will always give you the correct answer for every possible input that you can pass into this machine. Meaning that this problem, will a Turing machine given an input halt or keep on going forever, would be solvable if it met those 3 conditions. It would be a decidable problem if this machine actually did exist. But the question is, does this machine exist? And the answer to that is no. Turing actually proved that this machine actually can't exist. In other words, that this problem actually can't be solved. Hence, it's an undecidable problem.